Right, Vincent, should we get started?
Yes, let's get started.
Right. Welcome, everyone. It's great to have everybody visit us for the last day of ICCV. So this is the second workshop on learning 3D representations for shape and appearance, 3DReps V2. My name is Fidler. I'm an assistant professor at Brown, and joining me today is Vincent Sitzman to host session 1 from MIT. And you'll be hearing from the rest of the co-organizers throughout this workshop in different sessions. So what is 3DReps? The 3DReps workshop started off at ICCV last year. And the idea for us was, there was definitely a resurgence in research in computer vision on 3D vision in particular, driven by advances in neural networks and convolutional neural networks and so on. So we were kind of seeing a really increased amount of work that was being done in the community, as evidenced by this plot here of keywords from submissions to CVPR 2019 and 2020. So that was our initial motivation, to kind of have gather people working on all of these different 3D problems in vision, and to kind of bring them all into the same space so that they can learn from each other and talk to each other. Obviously, over the last year, since the first 3DReps workshop, this resurgence has continued. So here's a similar plot from CVPR 2021, which clearly shows that 3D continues to be a very popular topic and a topic of increasing and wide interest within the community. So that's our goal, to kind of, to bring together people working in the computer vision community and all of these different topics that are loosely connected to 3D. So the first 3DReps workshop was held at ICCV last year. We had a great lineup of 7 invited speakers. We had 14 invited posters, a panel discussion with all the invited speakers, as well as an interactive session, which allowed participants, both poster presenters and the panelists and the invited speakers, to interact with each other. If you missed the first version and you'd like to rewatch some of the comments and talks from last year, please visit our website, the link for which is available on my slide here. We had great feedback from the first version of this workshop. As you can see from some of these Twitter posts, participants particularly seem to enjoy the interactive components of the workshop. And we've tried to keep that the same as last time for this workshop as well. Okay, so once again, our goal really for the 3DReps workshop is to kind of bring together different researchers working on different kinds of 3D vision problems. So representations for shape, for appearance, 3D reconstruction, robotics, and so on and so forth. So we kind of want to bring all of them into the same room so that we can initiate this discussion and talk to each other about what we're all working on. So that's really the goal for this workshop. And we've changed a few things since last time. So again, we have a great lineup of 7 invited speakers this time. We've increased the number of posters, so we have both invited posters as well as submitted posters. So we have 20 posters being presented in this workshop today. In addition, we also have mini panels for the poster participants. So we'll have 3 breakout discussions that focus on different themes, and I'll tell you a bit more about that in a second. We also have a great panel discussion at the end of the workshop with all the invited speakers. And finally, we tried to bring together a more diverse collection of topics, both to the posters as well as the invited speakers. So you will see that we cover posters in robotics, digital humans, graphics, and so on and so forth. So we've tried to increase the diversity of topics that are covered during the workshop today. And of course, we are keeping the interactive sessions that were well received last time. So we will have a gather.town session to kind of let participants interact with each other, to do our best to simulate what would happen in a real conference setting. Okay, so the workshop program is available on our website, the URL to which you see on the top of the slide here. So it's available, you can check it out, but I'd like to highlight some key components of it. So we have 4 sessions. Session 1, which is this session, will have 2 invited talks, and it'll have opening remarks. We'll have following this session 1, we will have poster and breakout sessions where the poster presenters will present their posters, and then we'll have the mini panel discussions with the poster presenters. Following that, we have session 2 and 3, also containing invited talks, remarks by one of the co-organizers, as well as the panel discussion. Okay, so invited talks, as I said, we have a great lineup of speakers spanning vision, robotics, cognitive science, graphics. So I highlighted which of these speakers are presenting in which session. So you'll see session 3 is the last session of the workshop. Session 1, for instance, we have Yaron and Andrea presenting in this session. The posters and breakout sessions will be held from, the posters will be from 10:30 to 11:45 Eastern time. This is 11:45 a.m. on Eastern time. And this will be on gather.town, which is a virtual platform that kind of tries to simulate and keep things as realistic as possible. And following this, we'll have breakout sessions in the same Zoom room. So we will be doing the breakout sessions, mini panel discussions in the same Zoom room that you're all in. And that'll be from 11:45 to 12:30 p.m. Eastern time. There are going to be 3 breakout sessions. The first one is going to be on humans and robots. The second one is going to be on surfaces and points. And the third one is going to be on generation and recognition. And you're welcome to participate in any one of these breakout rooms. You can kind of switch between them if you like. But we do ask that the poster presenters who've been assigned to breakout rooms, please join the breakout room that you've been assigned to. All right, so we also have some opening and mid-workshop remarks by our co-organizers, Sanja Fidler and Leo Guibas. We're really looking forward to that, kickstarting with Sanja's remarks in a few moments. And finally, in session 3, we also have a panel discussion, which involves all the invited speakers, and this will be moderated by our co-organizer, God. Just some final housekeeping items here. Please use Zoom chat to type in your questions. We will be monitoring the Zoom chat to take any of your questions for the invited speakers. So we will relay them to them. We also ask that you please use your full name in your Zoom name. And finally, please mute the microphone. But you are welcome to switch on your video. I think this is something that the invited speakers will much appreciate. For the posters, we are using gather.town. You should already have the URL. We will post it on the Zoom chat later today. But here's the URL in case you'd like to take a screenshot. And this is an interactive session, which again tries to simulate the real conference experience. I'd like to thank my co-organizers again for helping organize this workshop. And I'm really looking forward to the rest of the workshop. Yeah, let me hand it over to Vincent now to get us started with the rest of the workshop today.
Thanks, Shuran. So actually, my only job right now is to introduce Sanja as one of our co-organizers. Sanja will have a few opening remarks. And I'm looking forward to that. And after that, we're going to get started with the first talk of the session.
All right, should I go ahead?
Yes, please, Sanja, go ahead.
All right, thanks, Jonathan and Vincent. I see that you guys have me down for 15 minutes, and I'll be much shorter than that, so you guys can have a really exciting workshop ahead. Yeah, so like Shrinath mentioned, 3D is becoming increasingly more important. It has kind of re-emerged as a field in the last just few years. And there's so many domains that critically depend on or rely on 3D. For example, robotics, medical imaging, AR, VR, entertainment such as movies and gaming, architecture and simulation, which is robotic simulation, which is a topic that I'm personally very excited about. And 3D sensors are constantly improving. They're becoming like more and more widely available. There's all these cool new sensors in iPhones that you get these days. But at the same time, we're also seeing incredible results when using no 3D sensors at all, right? Just inferring 3D from just cameras. So different problems require different ways of utilizing 3D information, or maybe have a different requirement for representation, right? So for example, a representation that is excellent for rendering isn't necessarily ideal for detection or navigation, right? And then in some cases, we have 3D as input, such as information available from 3D sensors like depth or point clouds, or have as input 3D content, such as CAD models, if you want to do some tasks on just processing CAD models, which may be meshes or maybe some other representation. We may also want 3D as the output, right? Such as for content creation or semantic tasks like 3D detection, for example. So different tasks or different settings likely need different representations, right? So for example, there are many ways to digest a mesh, but it's a lot more tricky to output a mesh with arbitrary topology, right? And we know that implicit representations these days can easily fit shapes of arbitrary topology, unlike meshes, but may have other issues. For example, capturing thin structures, open surfaces, or maybe they're just not as fast for rendering yet. Then NeurFLEC methods that utilize 3D radiance fields parameterized by neural networks achieve remarkable construction quality. However, they're still kind of relatively slow to train, right? You cannot really use them for interactive applications yet, I would say. And also I haven't seen a result that kind of easily disentangle intrinsic properties all that well yet. Then certain representations easily allow us to express symmetries, rotations. Some can easily be manipulated, and some can easily be composed. Some representations, such as TET meshes, also easily support physics-based simulation, and therefore they're perhaps better supporting modeling and time. And then kind of recently, we also have seen this hybrids between explicit and implicit representations, which I think is a very exciting way forward as well, and enjoy properties of both explicit and implicit representations. So this year's emphasis of the workshops is on 3D representations, and especially across disciplines, vision, graphics, neuroscience, robotics, and geometry. And we have a very exciting schedule with speakers across these fields ahead. And the schedule was really prepared by Srinath, Vincent, and Or. And on behalf of all the organizers, I would just like to thank all the speakers and attendees for joining, and let's get started.
Thanks so much, Sanja. That's a great introduction. So 3D representations are indeed getting more and more important. And our first speaker today is going to be Yaron Lipman, who's going to speak in a moment. And Yaron is a professor in the Department of Computer Science and Applied Mathematics at the Weizmann Institute of Science in Israel. And he's also currently a visiting scientist at FAIR in New York City. And Yaron, of course, has made contributions in geometric and irregular learning, deep learning for 3D geometry processing, shape comparison, shape analysis, optimization, lots of exciting stuff. Recently, also lots of great and very exciting contributions in the learning of neural implicit representations. And in fact, one of his students, Lior, is also presenting a poster on one of the projects that Yaron might also talk about. So go check that out later as well. And Yaron has received multiple awards for his work. I'm not gonna all list them here, but we are really excited that Yaron is joining us for our workshop, and looking forward to your talk, Yaron.
Thank you, Vincent, and thank you all the organizer for inviting me, and thank you, Sanja, for the nice kind of introduction to this day. So my talk is going to be about different representations, but all within the implicit representation framework. So it's going to talk about two different implicit representations and how we can kind of use their kind of relationships and in order to introduce interesting inductive bias or certain guarantees into our algorithms. So the talk is generally going to be about the problem of learning geometry from raw and partial data, where in the role of partial data, we're going to have one of two things, either two-dimensional images. By the way, I assume that everybody can see my this red dot that's hovering around.
Yes, we can see your slides and the red dot perfectly.
Great, thank you, Vincent. So either two-dimensional images, which have like camera parameters and are taking a certain scene from different viewing directions, or three-dimensional data, which is like can be seen as like a point cloud or triangle soup or something of that sort. So giving this type of data, we want to learn the geometry. This is in general not a new problem. It's the classical problem of surface reconstruction, but of course deep learning gave us kind of new opportunities to progress. So the first thing that I'm going to discuss is the representation. So the way we represent the surface or think about the geometry is going to be two-dimensional surfaces. Here they are visualized as this one-dimensional curve in 2D. And when we talk about implicit representations, there are currently two popular ways of representing a surface implicitly. So first of all, what is implicit surface? Implicit surface is instead of kind of encoding different points on the geometry on the surface, we represent it using a volumetric function, which lives in the entire space or some ambient space. And the surface is defined as all the points x for which u is 0. So u is the implicit representation. So as a zero-level set of some function. Now, clearly for a given surface, there are different ways of representing it as a zero-level set of a function. And two popular choices are the occupancy function and the sign distance function. So here's a quick definition. So the occupancy function, at least in my talk, is going to be something like the indicator function of the surface. So inside we're going to prescribe the value 1 and outside the value 0. And for sign distance function, which is also pretty popular, we're gonna define the function as the distance to the surface times sign. The sign is going to be a positive if we're, let's say, outside the surface, and negative if we're inside the surface. So it both encodes the interior and exterior and also the distance to the surface. Now, classical surface reconstructions basically suggested or worked with the convex collections of such candidate implicit representation, in particular even linear. So you can take if you think about a volumetric grid or an RBF, you can think about their linear, the span of these bases, like linear combination of these bases, where the coefficients in the linear combinations are the learnable parameters. And in that space, you look for your solution. So this kind of encapsulates many of the classical algorithms for surface reconstruction. And of course, in recent years, again, I apologize, this is not like an exhaustive list of all the work in that space. But anyway, in recent years, people have suggested to use a neural network as a model, a function space for this implicit representation. So instead of a linear space, we take an MLP, which is we cannot longer kind of do many things that we could do in the linear space, but it gives us a very rich space, and we are not afraid anymore of optimizing non-convex losses. So in some sense, it's kind of freed our mind to think more broadly about representation of implicit surfaces and an algorithm of how to optimize them. Now, in my work, in this talk, what I want to kind of emphasize is kind of the trade-off between the two different representation. On the one side, it's the occupancy functions, and the other side is the side distance function. And in fact, what I want to kind of emphasize is the benefits in each, and maybe thinking about them in a unified way can actually benefit algorithms and guarantees and theory of things we can kind of develop regarding this in this space. And what I'm actually, in order to kind of flesh this idea a little bit more, I want to introduce this notation. So by phi, I'm going to denote the Laplace cumulative distribution function. So the exact shape of this thing is not super important now. You should only imagine like this monotonic function that goes from 0 to 1. And by psi, we're going to describe its inverse function. And we're going to remember that these Laplace CDFs come with this parameter beta, which is going to play an important role later. And as this beta goes to 0, it becomes kind of more and more steep. So the distribution is more and more concentrated around 0, around the center. Everything is going to be centered here. Now, what we're gonna see is how can we kind of go from one representation to the other and what we can gain with it. Okay, so the first direction, which is in some sense the easier direction, is to start with a sign distance function W, and then here there's a minus. That's just kind of it's a conventional thing because I defined SDF to be negative in the inside, but it doesn't really matter. We can compose the sign distance function with the Laplace CDF, and what we claim is that as beta goes to 0, the output U is going to converge to an occupancy function. Why do we say that? So let's take a candidate point. Let's take a point here inside the shape. So it has some negative value, and so it's going to be, when I compose it with the Laplace CDF, it's going to end up here. And now, we take a minus of that, so we end up with something positive. And then as we take beta to 0, this is converged to 1. And the same kind of argument goes if we take a point outside, then as beta goes to 0, it converges to 0. So this is kind of squishing all the different level sets of the sign distance function to an occupancy function. The other direction is much more delicate. So if I take an occupancy function, so even the way I define occupancy function is not even continuous. So how can I apply the inverse operation and get a sign distance function? So clearly we cannot, but my point is that for certain approximations of occupancy function, we can apply the inverse Laplace CDF and get something which approximates the sign distance function. But this is no longer, if the first thing that I've shown is true for any kind of squishing function, this is true only for very certain function, like the inverse of the Laplace. And I'm going to show how we can use that as well. But the blue is much more rare than the red in a sense. Now, I'm going to instantiate each of these directions in a different kind of work. The first, using SDF for occupancy, is going to be manifested in this volume rendering of fluid and implicit surfaces, and the other direction is going to be in this paper of surface reconstruction for point clouds, which I'm going to talk only shortly at the end. So the first work is this volume rendering of implicit neural surfaces, which actually think about the SDF to occupancy direction. And it's a joint work with Lior Yariv, Giata Ugu, and Yoni Castan. And as Vincent already said, Lior is going to participate in the poster session, and she's happy to take any further question about this work. So the specific problem in this work is we're giving a bunch of two-dimensional images, like shown here on the left. And our goal is to kind of infer the geometry of the object or the scene and the light field. And I know the light field is something which, at least this has too many meanings. Some people kind of refer to it as the radiance field. So in a second, I'm going to define it. But anyway, the goal is to extract these two things from a bunch of images. And we're going to assume the images are coming with camera parameters. So in order to kind of explain this algorithm and what's new about this work, I'll review volume rendering a little bit. And I think it's going to be useful for people who want to enter the field. So the volume rendering, we have two main players that represent the scene. The first player is the density. So this is a volumetric function. And if you think about really specifically this image, then you can think about this is the density of bone, let's say, in the scene. So where there's no skull, the density is 0, and maybe where's the skull, there's some density. So the density is in some sense kind of the rate or that light particles reflect from it. So in some sense, it's like a very big number inside and very small number outside. So the density represents the geometry of the scene. And on the other side, we have the light field or the radiance field. This is a function of two variables. First, the location, and the other is direction. And basically, what it encodes, it's the amount of radiance or light that is reflected from point X toward direction V. These two things together are used in volume rendering to produce a rendering of a scene. So let's see how that works. So basically, what we need is to see how can we combine the density and the light field in order to decide the color of a single pixel. So the first thing that we do is we're shooting a ray starting from the camera position C in direction V. V is like a unit length vector described in this direction. And what we're actually going to do is we're going to accumulate the amount of light along this line. But in order to do that, we have to introduce maybe the single most important quantity volumetric rendering, which is the opacity function. So the opacity function can be seen also as the cumulative distribution function. It is basically, intuitively, if we're shooting a particle from the camera, it reflects the probability of the particle kind of reflecting off until a distance t from the camera. Okay, so it's kind of monotonically increasing, starting from 0 and reaching to 1, assuming that our ray at some point kind of crosses some density. And this is the definition. So it's kind of, it started from 1. So when t equals 0, this is like 0, and x of 0 is 1. So at t equals 0, this is 0. And as we traverse more and more stuff in the scene, this integral kind of increases. So we have a negative number, and the exponent decreases really fast, and this converges to 1. So this is why it started from 0 and goes from 1. And this can be seen as a cumulative distribution function of a particle. And indeed, in order to decide what is the color of the pixel, we can take the expectation with respect to the CDF of the light field. So we kind of accumulating all the light reflected from points where we have density along this line. And of course, one of the main issues and the things that we think about in this work is that this expectation is not trivial to approximate. What usually is done is that we sample the line, like the ray at some points shown here in black, and we provide like a numerical approximation of this expectation. This is like an empirical approximation. And it's important to note that the points xi are representing the opacity or the density. So the gradients of xi are controlling the density and the geometry, and Li is playing in the role of itself, right? So like controlling the light field. Now the main, in a second I'll go back to this approximation, but just to complete the story, once we have this approximation, we can compare it to the ground truth pixel color, and we can basically optimize that to get both our geometry and the light field. So this is the general framework. And we all know NERF as a seminal work that did a big step in this space. What NERF did is chose this density sigma to be a kind of a generic multi-layer perceptron, like a generic function in the space. And the challenges are how good this approximation really, how good is this approximation to represent the color of the pixel. So when we take the density as a general function, it's very hard to come up with precise sampling that provides good approximation of the opacity. And in particular, we see two types of phenomena in NERF. First of all, if we look at the geometry of the density that is being learned, this is like a level set of the density, then it's often very, very noisy, although the renderings are very smooth. So in some sense, these equations allows a very complicated decomposition of a pixel intensity. So the points can be chosen by the network in a way which kind of, you can cancel noise in the geometry by a noisy light field or radiance field. And you can place lights in a different location. So basically what happens here is that there's many, you can think about there is non-unique decomposition of radiance and geometry or density. And within the space, every method kind of picks its own decomposition. So this is one issue. A second issue is that it's not clear if you work with general densities, it's not clear where do you need to sample to make sure that your opacity, you're not missing like parts in the opacity, like thin parts of the surface, or you're not overextending other parts. So when you talk about general function, it's very hard to control approximation in general. The key idea in this work is to replace this generic density representation by an MLP by a very specific family of densities. And again, this is the density is going to be a transformed version of a sign distance function. So here's for example a scene. You see here a surface. There's the sign distance function, and this is like the transformed version. So this is exactly I showed before. What we also have like a coefficient here, because density is not exactly occupancy, right? It can have some. It's up to a normalization. It is, but it can have like scalar. So the interesting thing is that this, first of all, this family of densities does not lose universality. So any surface can be thought of represented as a sign distance function to that surface. So this does not sacrifice the generality of this representation. It does in terms of like homogeneity of the density, but not in the terms of the surface it can represent. However, there are several gains from this representation. The first of all is it injects a really concrete prior for the geometry. So you get surfaces which are much more smooth. You see that the images are pretty similar to NERF, maybe a little bit similar like PSNR, maybe a little bit lower. But you see that these two images, although they look very similar, are kind of computed from very different densities. So this density introduces this nice smooth inductive bias to the surfaces. And another interesting benefit is that using this form of density, you can actually come up with theoretically proven bounds for approximation of opacity as a function. And then you can make sure that you produce samples which really come from the opacity function to an arbitrary degree of approximation. And in order to see that, I want to use like a couple of slides to derive the bound on the opacity approximation using this family of densities. So again, the way we approximate opacity is not new. It's basically using the rectangle rule as before. What is new is that the fact that we use this family of densities allows us to bound this error. Okay, so here's again the definition of the opacity, and the way people approximate opacity is they replace the integral inside the exponent with a rectangle rule quadrature approximation of this thing. So how does the rectangle rule work? So we have point samples along the ray, like shown here. And now for approximating, for example, the contribution to the opacity of an interval t0 until t, we basically multiply the length of this interval times the sampling of the density at the initial point of the interval, like the starting point of the interval. So when I describe it like that, it's clear that the error of this approximation really lies in how much sigma can change within an interval. So we only know the endpoints of the interval, but we want to know how much sigma can change. And in order to bound how much a function can change in an interval, one way to do it is to maybe come up with a bound on its derivative, and then the bound of the derivatives times the length of the interval provide a bound on the approximation of this rectangular rule. So basically, let's use this form of density. And what we need to do is to use like the chain rule in order to differentiate the density with respect to t. So what we see here, this is the Laplace PDF, right? That's the derivative of the Laplace CDF at minus the distance, and the inner derivatives are taking the inner product of the gradient of the sign distance function and a unit norm vector. So these are two. The sign distance function is always a unit norm gradients. So this thing is bounded by 1, right? So we end up with this term here. So it's like the PDF of the Laplace sampled at some plus or minus distance to the surface. So in order to bound this, all we really have to do is to come up with a minimal with a lower bound of the absolute value of the distance to the surface in an interval where we only know the endpoints. Okay, so that's the interesting part. There are 2 points. We know the distance to the surface are those 2 endpoints, and we need to lower bound the distance to the surface at any interior point. If we have a general function, we can never lower bounds because we don't know what happens between any 2 samples. But here it's not an arbitrary function; it's a distance function. So we know, for example, that the surface needs to be outside the union of these 2 spheres, right? Because otherwise the distance would be shorter to these points. So you can say that a lower bound to the distance in this interval is this non-trivial black bold line. And this provides the lower bound to the distance. And it's actually provided a non-trivial bound to this whole approximation. So let's take a look at the bound. So basically, I'm not giving here the specifics of the bound. It is like a sum of exponential. It's not very pretty, but it's important to note that it is depending on 2 things. The first is on the samples, of course, and the other is on the beta. And in order to understand the trade-offs, here's a very nice animation Lior made. So what we see here is when we increase the number of points. So in blue here, what you see is the opacity. So you can appreciate the fact that it's very concentrated around the intersection point. And here you see the samples. So when the samples increase, the lower bound kind of decreases, but you can clearly see that taking uniform samples is not efficient because the error always concentrates around the intersection of the ray and the surface. But nevertheless, when we increase the samples, the bound decreases. The other part that is bound depending on is this beta. So beta is the smoothing of the sign distance function. So when we increase beta, we get a smoother opacity, and then the bound also decreases. So these are two interesting properties of this bound, and you can think about different ways of using it. In the paper, what we do is we come up with a sampling method that basically always keep an error approximation of epsilon. This is a fixed thing. And now we take beta, like smoothing out the surface, the geometry. So we get the approximation we want, epsilon, and we keep decreasing beta until we reach some value of beta. The important thing here is that we never miss parts of the surface or the geometry. We might smooth it out, but we'll never ignore it. So the opacity is always a good approximation of the geometry. Okay, yeah, this is, I think I showed that before. This is how the difference in rendering looks when you sample according to this algorithm. So to Vincent, I'm sorry, can you tell me just how much time do I have? Because I'm not sure when I started, because it wasn't like
We have 9 more minutes until 9:40.
Okay,
oh, sorry. Wait, I think. Yeah.
Okay.
Sorry, until 9:50. You have 20 more minutes. Sorry.
Oh, wow. A mini course. Okay. So anyway, thank you. So just to kind of summarize the training process, it's pretty easy actually, or simple. So there are two networks. One network is approximating the SDF to an unknown surface that is being learned, which also represent the density according to this transform. And the radiance or light field here, the loss actually comprises of only two things. The first is an RGB loss, which is what I described before, comparing the rendered pixel and the ground truth pixel. And this iconal loss that kind of encourages W to be a sign distance function. So in some sense, this kind of incorporates the inductive bias of the surface inside. Note that this does not require any masks or something like that like we needed before in surface-based training. Another interesting difference is that the light field is taking as a function of not just X and V, but also the normal to the sign distance function and a global feature, which allows, this is something which allows a better disentanglement of shape and appearance as we'll see in a second. Okay. So here's a bunch of results. You can kind of appreciate the fact that the rendering of NERF and Vol SDF is pretty similar, but if you look at the geometry, there's a big difference. The inductive bias injected by this representation of the densities by SDF provides a much smoother and plausibly looking surfaces. Yeah, the numerical, I'm not going to go over that. You can see the paper for details. And this is also on blended MVS, which kind of provides also an interesting non-trivial background. And I think one very interesting thing is I discussed in the beginning of the talk that there is kind of a question of if you have a light field or radiance field and you have a density, then these two are kind of combined in a non-trivial way to yield the pixel value. And there are many different ways. It's like a matrix of factorization, if you like. There are many different decomposition to light and density that's going to give the same image. Okay, so one way to kind of validate the decomposition of images to density and light would be what we call disentanglement of geometry and light field. So what happens here is that, maybe I'll let it run as we talk. So we have here, we train independently two scenes, training the radiance, the light field, and the density for two different models completely independently. And this is like the top row that you see here. On the bottom row, what we did is just we switched between, we took, for example, in in this dog statue, we took the density from the top right and the light field from the top left. And what you see is that the appearance, the material, the lighting from the top left image kind of translated into the geometry of the top right. The fact that you see here a little bit of grayness is because also these are like in different places in space. I think they're in different elevations from the floor. But in general, in areas which correspond to the main statue, you see the material is transported pretty nicely. On the other hand side, this is like the geometry of this with the light field of this, and you see the nice kind of material properties that translated. If you're going to do that for other, like for nerf, you're not going to get this nice decomposition. So in some sense, this is a type of validation of the decomposition or the learning process to geometry and light field. Yeah, I'm not going to use all the time, not to bore people too much, and be fair also to the other speakers. I'm going to use maybe 5 more minutes or so to describe the other direction, because I kind of think it nicely complements that idea. So in the other direction, the problem is slightly different. We use the other direction for the problem of surface reconstruction in the more classical sense. So you have a bunch of you get a point cloud as input, and your goal is to come up with a implicit function where the zero level set kind of is a plausible approximation from the sampling. I'm gonna explain. So the whole point in this work is just introducing a loss, where the training is you train an occupancy function. So U is going to be an occupancy function, and there's a loss here which kind of I want to break down now. So the first term, which I think is the most, I don't know, it's not interesting. It just or at least we can skip it for now. It's just making sure that the value of U near the input points is around half. Okay, so it's like asking that the half level set of the occupancy function goes next to those input points. I think the interesting part is this integral. And this integral is basically is motivated from some physical problem of fluids in a container. What we have here is the first is a potential function. You see U is composed with W, and W is a double wall potential as shown here, where the minimal points are 0 and 1. So basically what does this integral does, it kind of asks each point to decide whether it's inside or outside the shape, right? Because the minimum is either outside or inside the shape. However, if you just think about this loss, this is a little bit like a sign agnostic loss. This is not enough, because you can have solutions like this shown here on the right? Because you can go through the points like this. This term asks you, and each point decides whether it's inside or outside, and you get something not plausible. A really interesting addition to this loss is this perturbation with this Dirichlet term, the squared gradient. And what happens is that this term kind of regularizes. So you have many solutions to the first two things, and this thing kind of forces you to minimize the area of the half level set. So it kind of pushes to a minimal area solution. So here's and one more thing I want to say, that there is a specific choice of this double wall potential, which also leads interesting connection to the sign distance function. So let me just summarize this thing. So there is this loss which I just introduced. There is a parameter epsilon, and as epsilon goes to 0, the function that is being optimized is getting closer and closer to an occupancy function. As you see here, like this is going to be 1 in the middle of the shape, inside the shape, and 0 outside, and the level sets are going to shrink and shrink along the boundary. It's going to pass through those input points. And if you do this inverse Laplace transform to this function, you get an approximation of the sign distance function as shown here on the right. And here, my point here really is that basically the fact that we're using the loss on the occupancy function allows us to introduce this minimal area inductive bias. And the only reason that this works is because all the level set are concentrated around the 0 level set. So this is why this is approximate the distance. If you want to incorporate minimal area to the sign distance function, I believe it will be much more challenging, because you have to single out the level set you need, and it's going to become a discontinuous thing. So here, the point in all this discussion, in the view of my global point in my talk, is that, for example, if you talk about occupancy, you can introduce inductive bias like minimal surface much more easily than if you work only with sign distance function. Okay, so this to show different benefits, this is kind of lead me to the conclusion. So when you think about the occupancy and the side distance functions together, then you get benefits like injective and useful inductive bias, like we did in the volume rendering work, or theoretical analysis like approximation or minima. I meant here like minimal surfaces. And again, I finished this talk as I finished other talks before. To me, the most bothering thing about these type of methods is the time that they take. You need to overfit like a whole network for a new scene or a new reconstructions, and there are many people working in this space trying to make things much more efficient, and I think that's a really good future direction. If we're able to do this type of high quality reconstruction in real time, I think this will drive the field forward. Yeah, and with that, I'm going to end. Thank you so much for inviting me, and looking forward to this interesting day.
Yaron, thanks so much for the talk. It's always a pleasure to hear you talk. For all of the participants of the workshop, please type your questions in the chat, and we will then carry them and post them to Yaron. Meanwhile, I already have one question. So you already raised the issue of speed, but I think your work, VolSDF, already somewhat improves the rendering speed at test time. Is that correct? Because you have a better sampling strategy.
That's a good question. So I think that we, in a sense, there is a trade-off between obviously quality and speed. I think I would say that in this work, we were more interested in making sure that the samples reached a certain epsilon. I guess that you can always play with the bounds and improve also the speed. I don't think we really answered the question of how to come up with fast sampling. I think that's still an interesting future work that people can think about. I think the only point I want to make is that I think we always should keep in mind what we're approximating, and try to keep in mind the approximation bounds, or something that gonna kind of put us in the track where we actually know what we're approximating, or leading to colors which are really a good approximation of the pixel. So I would say not really. I don't think we're doing something fast, even in the test time.
Cool. Thanks so much. Here's one question from Shimon Weiner. I hope I'm pronouncing that right. Thanks for the great work. One of the things we noticed with both VolSDF and noise approaches is that there's a very limited capacity to resolve small scale details. Did you think of any approaches where you would incorporate perceptual patch-based losses, or another remedy to this problem?
Yeah, oh, it reminds me, I forgot to mention, there are a couple of concurrent work, and noise is one of them. I think Lior mentions the other one, I forgot the name.
UNICEF.
UNICEF, yeah, thank you for that. Yeah, they're all working in similar space. I think they have a different kind of emphasis, but I think they're all great work. So yeah, that's a good question. To be honest, I'm not sure I understand. So there is some limitation. I like to call it a condition number with this implicit representation. There seems to be a fixed ratio of details, like big to small, that we can represent with these things, and going to kind of a local representation kind of improves things. I would take this question a little bit more to the conceptual level and ask, is it really true that we have kind of a limit of the amount of details? So if you represent only a small piece of the surface, you can go to represent really nice details. And if you go to the macro or global scale, you can represent the shape. And it seems that together, there's going to be some limit of how fine details you can go. And I think understanding this is one key to move forward in these small scale details. So yeah, patch-based or local is one. I would be interested if there's like a holistic solution with just a different training, different representation of implicits, or a different loss.
Awesome, thanks. Any more questions from the chat? No, then I have another question. So you've been really pushing this boundary of single scene reconstruction. And this is fantastic work all around. Do you have any thoughts on? I would argue personally that the generalizing across scenes has seen somewhat less progress than single scene reconstruction has seen. And I know Andrea is going to talk about that, which I'm very excited about. But do you have any thoughts on this, or any insights that you have gained in your research on single scene reconstruction that apply to that?
So great question. First of all, I completely agree. The interesting end goal would be to train on a collection of scenes and generalize to new scenes. In some sense, I think the single scene work gives us, in some sense, kind of an upper bound on what we can hope to achieve with multi-scenes. And I think it's good that we're able, at this point, we see the type of results that we get from a single scene. And I think definitely the next step for the community and people who are looking for interesting projects is try to see how close to a single scene quality we can get from generalizing to unseen scenes, to training. I think that's a wonderful challenge. And maybe I can also take it to another level, whether we can take like images of some geometries in the wild and train a shape space from that, or a generative model. And I know there's some work also in that space. So yeah, I completely agree. Yeah, I think it's a very interesting direction of work for future work.
Cool. Thank you so much, Yaron, for taking the time and for giving the talk. It's always fantastic. And unfortunately, it's Zoom, so we can't all loudly clap, but I'm sure everyone's clapping at home. So thanks so much, Yaron, and enjoy the rest of the workshop. Thanks for coming.
Thank you. Thank you.
And now I'm going to hand off to Srinath, who's going to introduce our next invited speaker.
Thanks, Vincent, and thanks, Yaron, for the great talk. Really exciting stuff. So it's my pleasure to introduce our next invited speaker, Andrea Vedaldi. Andrea is a professor of computer science and machine learning and co-lead of the visual geometry group in the engineering science department at the University of Oxford. His research focuses on computer vision methods to understand the content of images automatically, with applications to organizing and searching vast image and video libraries and recognizing faces and text in images and videos. Andrea is also a research scientist at Facebook AI Research, and he's done extensive work in 3D computer vision, and his work has been recognized by Best Paper Awards, for instance, at CVPR last year. Personally, I've really enjoyed reading many of his papers, and I'm looking forward to his talk today. So Andrea, take it away, and I will give you a 5-minute warning.
Okay, excellent. Right, let me see whether this is actually working. You can see my slides?
Yes, we can.
And you can see the mouse pointer as well.
You can see the pointer as well, yes.
Okay, great. Okay, so thank you again for the introduction. So I'm going to present today a few, some of the work we have done recently in Oxford, but also in Facebook AI Research. And this is all about, of course, learning 3D representations, given the workshop. So my starting point is this. Of course, as Sanja was also mentioning before, there has been a sort of resurgence in computer vision on 3D understanding. So for a long time, the attention moved to understanding semantics, and that means classification, detection, segmentation, etc. And in that case, the goal of semantics is really to give an interpretation of general images and try to put a label onto them. Now we'll be moving back towards 3D understanding, of course. And a point that was just made is that a lot of this work has been more specifically targeting a single object, a single scene. And perhaps if you're lucky, you can move towards a single object category. All right. So this is the sort of things that we are able, or we're currently researching as far as 3D understanding goes. So maybe a handful of categories. So the first question I would like to discuss here really is, how are we going to scale 3D understanding beyond what we are targeting right now? So the first thing I'm going to present is this work, which is actually not entirely my work. I would say not even primarily my work. Is work by my colleagues in FAIR London. And this is a data set, but I think it's a very useful, important data set that will allow us to make some progress in this area of understanding 3D scenes or 3D objects beyond just a handful of them. Okay. So what we're going to talk about is common objects in 3D. Now, this is just a slide to try to put this work in context. So what kind of data do we have in as far as understanding 3D object categories that go? So we have lots of high quality synthetic data. So maybe the most famous example is ShapeNet. And that is great. That has been a very important, useful data sets, but of course that's synthetic data. So you cannot expect that to be sufficient to generalize per se to the real world. On the other side, we had data sets that maybe started from the task of semantic understanding. So they have this sort of generality built into them, on this idea of spanning complex reality and have examples from real life. And some of them have been extended over time with some kind of 3D information. Could be, for example, a hint of viewpoint, or maybe 2D geometry, like, for example, segmentation mask of the objects which are contained in those images. And that's all fine and great, but these are also very, very hard images to learn from. So first of all, the ground truth data that you have, as far as 3D goes, is generally quite limited. Typically, you don't have a complete, full, and accurate 3D model of the object or the objects in the images. And secondly, the data itself is so diverse. You have a single image, typically, of each one of those object instances, and they're taken from different viewpoints, different lighting. It's very, very unconstrained. So it makes learning geometry actually quite hard. So the idea of Code 3D was to be somewhere in between these two spaces. So it's not quite as unconstrained as, MS Coco, for example. You're still going to focus on one object at a time, each image. But in fact, we do not have images, we have videos. And these videos go around each object. So you can have a 360-degree view or understanding of the object appearance, from which you can deduce much, much more easily the shape of the object, okay? So this is a little introductory video to the data set. So on the left, you see the sort of video that we have captured, okay? And to the right, you see some of the reconstruction that we have got using more or less standard neural rendering techniques. Not exactly, so you're going to discuss a bit more detail what's going on here later, okay? Now, the idea of this data set is to give you a large variety of objects to play with. So there are about 50 categories that have been taken from MS Coco. There are reasons why we did that. We selected objects from that particular object, catalog, if you like, or categories. One of them is that you already have pretty good pre-trained models for 2D understanding, and now you can extend them to 3D. All right. The other thing is that this is a large video collection. So we are, I think, approaching now about 50,000 videos. So this is not something that is easy to collect either. All right. So how have we got those videos? Well, we wanted to have something. We could have collected them in the lab, not really in our lab, but by paying people to do it, I guess, in a lab conditions. But instead, what we decided to do was to do what we call inverse annotation through a mechanical Turk. So we provide the annotators with a label, like, for example, Apple, and their goal is to collect data about that object, which is pretty much the opposite of what typically happens. So you give them an image, you want to know that's an apple, right? And the instruction said, take the object, put it in the middle of a table or something like that, and take your cell phone and do a video going around it. So it's not completely unconstrained because you have pretty specific instructions for the annotators, but these are still not computer vision people, right? So the object will be collected on random backgrounds, and the videos will be decent quality, but not as high quality as you would expect if the stuff was collected in a lab. And then what we did was to simply, quote unquote, take these videos and perform 3D reconstruction using standard tools, like, for example, CodeMap, and selecting among all the videos what we have collected, the ones for which this process of 3D reconstruction actually worked to a decent level of accuracy. So you have some 3D ground truth, or pseudo ground truth, really, which is not completely perfect, but at least the stuff that we provide to you should be of decent quality that you can trust it, all right? It's not complete, but it's reliable enough to work with this. Now, what can we do once you have this data set like that? Well, you can glue lots, and now I'm going to show one thing, or one-centric experiments that, in fact, my colleagues have done. So the problem here is to take a bunch of training videos and learn a model for a specific object category, like, for example, hydrant in this case. And then the next thing we want to do is to learn a model that is able to capture the object category as such, right? So we want to learn the category, not just a single instance in 3D, in such a way that if now we're given a small number of new views of a new object, all right, we're able to synthesize in so one go, if you like, without having to go back to the full data set, a 3D reconstruction of that object so we can see it from any possible angle. So again, it's the problem of new view synthesis, just like NERF solves, if you like. But the difference here is that the model is pre-trained to work specifically well for one object category. So it has to learn somehow a model of that category. And the idea is that while NERF typically requires dozens of images. This thing could also work out of just a couple, maybe 5 images or 10 images. All right. Now, of course, I don't want to go through the NERF story once more, just briefly to fix the notation. As you know, to render an image, what we do is we shoot an array, and then we query along the rays different 3D points, which are denoted by X here. And for each point, we pass that through multi-layer perceptron MLP that is going to tell us the density or the occupancy of matter at that point, and then the color as well. All right, so we get scalar that tells us whether that point is occupied, and the color, so that we can paint the image with the corresponding color if the ray hits the object at a particular point as specified by the density. All right, very, very simple. Okay, so that's NERF. Now, how do we learn NERF? Of course, you take a bunch of training images, pick one of them, pick a camera. You have your NERF learned representation that we assume in this case has already been learned to a certain level of accuracy. You render that with respect to that camera, just doing this ray casting process I just described. You generate all the pixels in the image, or at least a certain number of them, and then you compare what you got to your ground truth, which is supposed to be that object seen from a particular viewpoint. You minimize that, and that basically learns this representation, this model. Sometimes, and in our case, we'd use that. We also have an object mask, which for Code3D was obtained automatically by using a segmenter trained on MS Coco or one of those data sets. All right. Now, suppose that we want now to model more than one object. So it's not just one apple that we want to reconstruct, but is in fact all possible apples. All right, that's already quite different. So how can we do that? Well, in the case of NERF, of course, you're able to only learn one neural network that encodes one specific scene. Here, an approach would be to learn different networks for different apples, but that's, of course, not what we want to do. Instead, what we do is, the easiest thing we can think of doing is to extend the MLP with another parameter Z, which is a code that captures the specific details of that particular apple, right? So now we have still an MLP, a single one, but by changing Z from Z1 to Z2, we're going to encode the appearances of 2 different objects of the same category, okay? So this we call an autodecoder, because the idea is that once you have this machine, you need to optimize those parameters of this encoding for the object identity, specifically for each video you want to model, all right? So now, so once we have this naive autodecoder, so what would be a problem there? Well, so the problem is that we need to recover this Z parameter for encoding a given video or a given sequence of images, right? So how do we do that? Well, again, so we could try to optimize it. So we could try to tweak Z using gradient descent until the output of our model matches what we see in the images. And that's one way of doing it. But that's what the autodecoder does, and it's inefficient. So the alternative would be to use instead an autoencoder, meaning that we also have another CNN or model or network that takes the image as input or the given images you have and figures out the encoding for you in one go, right? That would be much faster and much more useful and interesting if you could do that. So you can try, and it doesn't really work, right? So we tried that. That's the obvious thing to try first, and it just wouldn't learn. It was very, very hard to get this encoder to give given a few views of the object to automatically come up with the right code to encode a given apple or a given object instance you have. So what we needed to do was to change the way the autoencoder works a little bit to make its task somewhat easier. So what we did was, instead of inputting into the MLP X and Z, where X is 3D point and Z is this code that is specific to the object, we would input directly an encoding, okay, of the 3D point through some code Z. And that code Z is actually pulled directly from the training images you have, or in fact, not training images, from the example images you have, or that new object you want to reconstruct, okay? So what this means is that given a new image that we want to, for which you want to get the 3D model for, we extract some features using a unit. Then you're gonna sample a target camera, the camera for which you want to generate a new view. You're gonna sample points along that ray. Those points we're gonna project back onto the target view, and from that we're gonna pull features, and those features will be what does ZX actually is. All right. It's almost like you condition the position of 3D points you want to reason about, you're going to pull the relevant information from all the input views you actually have at your disposal in a sort of dynamic manner. All right. We call this word condition ray embedding or embedding. Okay, so now here's a cool video that the first author did that shows this process. Let's see what okay, I think you can see it now. So again, that's our 3D object. Those are the views that we have as input from which we extract the different resonant features in this case, I believe. Then we get a new view that we want to render. So from that, we shoot rays into this volume, just like that. Along those rays, we sample 3D points, just like NERF, but those points now we reproject onto the input views we have, like that. And then we pull information from those views back to those 3D locations, right? Like that. And this is what is fed into the MLP to decide whether that point is occupied or not, and what is the color of that point. The pooling is conditioned also on the angle of the rays formed with the incoming directions, because that's going to suggest which directions are more relevant for rendering a particular point. Okay. All right, so that's the idea. And these are some results of this particular model. Sorry for the flashy bit there. That was just a bug, I think, in the visualization. And so these are examples that were obtained by inputting just a few images for each one of those new object instances in the different categories. And you can see that, yeah, results are okay, I guess, not super exciting just yet, But that's a lot better than what you can get if you don't have this word conditional ray embedding, in which case things wouldn't work at all. In fact, we run very extensive experiments on this. So what you see here is just the base model here is NERF. You can also change that to be SRN or something else. And you see here the important thing was to add this way of encoding the sort of information from the images you have as input. And that is what really brings you a nice improvement in terms of reconstruction error, in this case of RGB. And then this is also a measure of how well you can reconstruct the depth, which gives you an idea of how well the geometry is reconstructed instead. All right. So using this trick was actually very important. Now, of course, you can improve that. This is the work that was presented here at ICCV, by the way, where we introduced, or in fact, my colleagues introduced this idea of NERF former. And I guess by saying that, I just gave the method away. But anyway, so there are some limitations to what I just discussed, in that the way information is pooled is extremely simplistic, right? You just look at your images, pull the features and aggregate them in a simple manner, doing some sort of weighted averaging, all right? But of course, you can do better if you learn the aggregation mechanism. So one thing you can do is, as you go along the ray, use a transformer to aggregate information along that dimension, okay? But as you move between different views, you also get more information to pool, right? So now you have another dimension that you wish to pool, which is the view dimension, and you can use a transformer for that as well. So now you have a transformer that operates along the ray and a transformer that operates across a view. And what we do is we simply alternate these two pooling operations. So we start with the features, then we pool across the views, and then we pool across the rays, right? So across the rays, then across the views, then across the rays again, and then across the views. So you may wonder, why don't we pull everything together into one go? Well, it's just an issue of scalability. So this is a good trade-off between being able to put information in all different dimensions without having something which has the complexity of pooling is of course quadratic. And if you have too much stuff to pull at the same time, it's just gonna explode, all right? So that's another former. And yeah, so you try this, and at least for what concerns the reconstruction quality, so the new view synthesis quality, it works quite a bit better than everything else we have tried. In terms of depth error, actually is comparable to SRN plus our WC embeddings. So that's less clear. So probably this is overfitting a little bit onto the appearance, improving that more than it does improving the geometry. Maybe some of the stuff that Yaron discussed in the previous talk could be used here to actually make the geometry crispier and better. Okay. And so here you see some of the results that the former got compared to NERF and compared to SRN. And you can see that, yeah, it just basically looks sharper. All right, and some more. And can I ask how much time I have left, please?
You still have 10 minutes.
10 minutes, okay. So now I would like to switch gear and discuss something else altogether. So this is a problem of learning unsupervised geometry correspondences into the geometries. Now, you may wonder why I'm talking about that. Well, because that's actually a very, very important problem. So if you want to learn about object categories, you need to be able to establish correspondences between different parts of different objects, because otherwise you don't learn the right abstraction, right? In a certain sense, correspondences are a way of encoding abstractions because they put together stuff that is equivalent in some sense, all right? So correspondence is really fundamental. And so one problem we faced was, if you have a collection of 3D shapes, in this case, decent 3D shapes, which are meshes, how do we establish correspondences between them without using supervision, all right? And in a way which is fast and efficient. So we introduced in CVPR this year a method which is called neuromorph, all right? Which does this. So first of all, neuromorph is a neural network that takes as input two meshes, which have different number of vertices and topology and etc. Doesn't really matter. So you have two meshes. The network takes them, all right? And what it spits out are two things. One is a set of correspondences between the meshes, like in a feed-forward manner. And it also spits out an interpolation sequence so that you can go from one mesh to the other in a sort of continuous manner, which is actually intuitive, all right? So the interpolation makes sense at some level. Now, this is, again, a feed-forward network that is actually quite fast. So it takes two meshes as input, and as output gives you immediately these two pieces of information. So this is the first thing that neuromorph does. The second thing that it does is that you can learn this network in an unsupervised manner. So what you put in are just a bunch of 3D meshes, okay? For example, of people and animals. Yeah, it's quite robust. And what you get out is the network that does this correspondences and interpolation without you having to label anything, okay? Now, these two things are actually quite difficult to do together, but it turns out that if you try, it actually works pretty well. So what's powering this method? Well, first of all, you can see here the basic ideas. So we're going to establish a bunch of correspondences between the two meshes in such a way that when we try to move one mesh onto the other in a smooth manner, where smooth is going to be defined in a few minutes, then we get that the source points land on the corresponding, or the points that have been found to be corresponding in the target mesh, all right? So what network does is estimates trajectories for all the input vertices in such a way that at the beginning of the trajectory, when t is equal not 0, then you get your input mesh. When x is equal 1, you get something which approximates the target mesh, well, through a matrix pi, which is this matrix of correspondences. Of course, the vertices in this mesh will not correspond to vertices in that mesh necessarily. So you need to find how they correspond as well, which is the second thing that the network estimates, all right? And the third thing that we do is to make sure that the trajectory which is being computed is actually sufficiently regular. Now, there's quite a bit of detail here, but I'm going to skip most of it. Suffice to say that the model itself is also very simple. It's all based on using this edge convolution. So we call this EdgeNet. What this does, and let me go directly onto this scheme that summarizes it, is I take my input mesh, my main input mesh X, my input mesh Y, through this relatively simple network. I'm going to label each vertex with a feature vector for the first mesh and for the second mesh here, in such a way that when I compute the cosine similarity between vectors, I get out my correspondences through a softmax that makes the correspondences sum to 1. Makes the strength association sum to 1, so you can interpret that as a probability distribution. All right. Again, so all this does is for each mesh computes a feature descriptor, which is then used by pairwise comparisons to determine which vertex in one mesh goes onto the other mesh. And second, the other thing that we need to output is an interpolation between vertices. So here the idea is also very simple. What we start from is a linear interpolation, which only says, so if this vertex has to go on to that one, based on the matrix pi we have estimated, we're just going to linear interpolate between the two, which doesn't quite make sense. So we have a third network of the same nature, actually the same kind, that takes as input the input vertices, the residual of the sort of linear interpolation, if you like, and the time, and it outputs a correction that makes the trajectory more realistic or more sensible. All right. Okay, that's it. That's the method. You put everything together, so you have the correspondence network, this trajectory network that fixes the linear interpolation and gives you something a bit more sensible. And because all the right priors are incorporated into this thing implicitly, then this actually can learn from supervised data. The regularity means simply that stuff needs to deform in a way which is approximately rigid locally. So we have the an Arab deformational regularization, and we also have something that makes sure that the correspondences, they don't collapse, all right? Now you try this, you train unsupervised on a bunch of data, and it turns out to get state-of-the-art performance on unsupervised correspondences right out of the box. So that's already very good. So this means that this method does two things: interpolation and finding correspondences between meshes. And this gives you right away state-of-the-art correspondences to a level of quality that is actually comparable to the correspondences that you can learn if you actually use supervision. All right. So this is unsupervised, but the correspondences it learns are comparable to using supervision for them. And you can see here some examples of correspondences where we're putting correspondences fairly different meshes. In this case, this pig with this camel, or this, what's that, a buffalo, I guess, with a bear. And the bear has been corrupted, meaning that some of the vertices are actually missing. And you still find correspondences which are somehow sensible. And if you look at the sort of mistakes that this is able to correct compared to other prior work, for example, it tends to fix ambiguities when you have symmetric part of the bodies. This appears to confuse them less. So you see here that at the left paw of the pig is mapped correctly by the method to the left paw of the camel, whereas a prior method would actually swap them. All right. We run experiments on a data set of we call here Galgo human cats, but let me go very quickly through those. I just wanted to give you some examples of the interpolation you get. Now this looks crazy. We're interpolating a cat into a human, so it does look pretty. So the intermediate meshes don't look nice, but semantically, the correspondences that have been established, they are correct. All right, that's the important thing. And here you can see an example application in which, if you have digitized a human, you have, for example, markers, you can map the human motion automatically without supervision onto the motion of different meshes. Okay. So one last thing I would like to discuss very, very briefly, if I have time. Okay, great. So that's the third thing is, all right, so we have seen scaling up to object categories, learning without supervision, a correspondence between 3D meshes. But what about learning 3D objects in the first place from raw data? That's really one of the key things we want to do in the next 5 years, all right? And so here's a paper that has been accepted last week in 3DB. So the slides are a little bit rough. Apologies for that, but here we go. So this is a data set that some of you, like for example, Sanja, should be fairly familiar with. So this is Epic Kitchen, all right? So our question was, all right, so we have this data. This is great. There are objects there, but 3D objects really. How can we learn from that? I mean, it seems crazy, right? This is a lot harder than the typical data sets used to learn one object at a time that are nicely shot, et cetera, even harder than Code3D, much harder in fact, all right? So what can we do about that? Well, what we wanted to do was not to solve the entire problem in just one go, but we wanted to be able to separate the objects at least, right? So what we did was a method using neural rendering, which takes the video to the left, and to the right, what this is gonna give you is a visualization of the object where you remove the background, you remove the foreground, and you remove the viewpoint, okay? Once you have that, it gets a lot easier to reason about the objects in the video, all right? And again, this is an example of an application of neural rendering, not so much for rendering, but for semantics, for understanding the content of the video, all right? So how does this work? It's very simple. So we take NERF where you have 3 different volumes. One volume represents the background. So that's just an MLP that takes as input a transform point GX. The point X is the 3D point and G is the camera viewpoint. In this case, the camera is mounted on your head. We have another MLP for the foreground, which takes as input also time, because the foreground can change. These are objects that have been moved around by the actor. And we have a third volume, which is actually the actor itself, so that you can capture stuff like your hands, all right? And this one is very similar to the foreground one in the sense that it depends on time, but as you will notice, X is not multiplied by G, or you don't apply G to it, meaning that the MLP is relative not to the word, but relative to the camera, okay? So this is actually a very important point. So the thing is that the object, unless you're not moving them, they're anchored onto the 3D word. So it makes sense to use that as a reference frame. But for what concerns your hands, well, your body is attached to your head usually, right? So as you move in the video, that's the reference frame you want to use, the one of the camera, not the one of the word. This helps separating the two different types of information. And time, well, the background is supposed to be static, so that does not change. So there is no time there. Time only goes here and there. And there are some tricks and also to encode time in a way which you get some sort of smooth change, all right? So again, this is a summary of the different ideas we put here together. It's actually relatively straightforward and it's inspired by prior work like NERF in the wild. we just extend that using slightly different priors and adding another volume, which is the active volume, which was missing in that paper. And the goal also is completely different, all right? There are a bunch of other nice technical tricks in the paper that I don't have time to discuss, but if you're interested, just have a read. And I think there are maybe one or two things that are useful in general for neural rendering. And here again, you can see just last slide, I promise, one video of the sort of reconstruction you can get. So to the left, you see the input video. On the top, what you see are the videos that have been reconstructed from the viewpoint of the camera, which is egocentric. And you see here the reconstructed video where you combine the three streams, and then you see the static background, the object background, the object stream, and the actor stream, where you have the hands essentially, all right? And then because it's nerf, now you can change the viewpoint, in particular, you can fix it, right? And so here you see the same rendered from a fixed viewpoint now, all right? So you can see that you can sort of separate the background from the foreground from the actor, okay? Now, this is just the beginning. You see it's not perfect. So for example, here occasionally you see still the hands, which shouldn't happen. So there is miles to go before is, so there is quality that can be got here that we didn't get yet. But I think this sort of ideas is very important because it suggests that this neural rendering can be a proxy to semantics. And that I think is very, very powerful because it will allow you to learn for very complex data that you would not be able to learn if you were to only look at that data in 2D, all right? I think this is absolutely fundamental. All right, and this is a summary. So I show you three things. This new data set, which was done by my colleagues in Fair London and a little bit myself as well, I guess, but mainly by them. Neuromorph, which is this problem of finding correspondences, this network that can learn them in a sort of unsupervised manner for very different 3D shapes. And then neural diff, which is this new method that we have introduced to try to extract a proxy to semantic information from complex egocentric videos. And the egocentric videos, of course, are exploding. I should just probably mention Ego for Data, that came out also from Facebook and a consortium of universities just a few days ago. That is going to provide tons of this kind of data. So I think this kind of method will be very useful when you apply them to the interpretation of that data, which doesn't have actually a lot of 3D priors yet, or 3D information yet. Okay, that's it. So if there's any questions, I'm very happy to answer them.
Thank you so much, Andrea. It's a great talk. And personally, I really appreciate that many of your work kind of takes a step towards using real data and using less supervision and maybe no supervision at all. So that's something that I really appreciated. So we do have a couple of questions from the audience. I'm just going to relay them to you. First from Anish Madan. Can neuromorph be used for registration of meshes? Consider giving a mesh X as the mean pose of a human body and mesh Y as some human body mesh with a different pose and shape.
I would say yes, meaning you would learn the method from a collection of human poses. And then you could just select any of them as a reference and you could align everything back to that one. So yeah, sure, you can do that. But there's nothing special about the canonical shape when you learn the network. That's just one of the many meshes you would have in your set.
Thanks. We also have another question from Or. So Or asks, how is using different categories affect neuromorph? Would humans correct? Would it be better if we trained only on human shapes, or are different categories helpful?
This is a good question. I don't have a precise answer to that. My feel also, this is, the experiments date back several months, so I might not be completely remember the details of the experiments right now. But if I remember correctly, it was easier to learn from a homogeneous category as opposed to a set of mixed categories where you would include also animals and humans. Having said that, it was surprisingly robust. So there is a line of work we have been doing in Facebook London, which is about unifying the understanding of deformable objects. So one goal there would be to find a model for all possible mammals or even all possible animals that understands all of them in the same sort of conceptual space, if you like. In some cases, we did notice that by fusing information from different species was better than learning from a single one. But for humans, you have so much information and ground truth and labels for that one specific case that maybe you're just better off learning with the strong supervision you have for that particular category. If you want to learn more categories for which you don't have that, then putting them together, I think, is very useful, actually.
Great, thank you for that. We still have some time for questions, and while we wait for participants to ask more questions, I had a couple of questions about the Core 3D dataset. Great work. Me and my students, we've already downloaded the dataset, and we're kind of looking at it already. And one quick question I had was, so when you say that the 3D reconstructions are available, what form are these 3D reconstructions in? Are they point clouds, meshes, or the weights of a neural network?
Yeah, so first of all, for all the videos, you're going to have reconstructed cameras. So the videos that we provide are the ones for which Colmap work with a certain level of reliability. By the way, there are some scores in the data set that's going to tell you which cameras are more believable than others. So you can even rank by quality. But the ones that are provided in the data set are the ones for which the camera did work to a reasonable degree of accuracy based on some metrics that David Novotny came up with. Then for a subset of those videos, Colmap did a good enough job of also returning a partial point cloud, so you get that as well, right? So Colmap has a way of generating dense point clouds as well as the sparse ones. And we just use that to, oh, in fact, I should say they use that to get them. So you're gonna get that. So cameras for all the videos, for some of the videos, you're gonna get more or less sparse point clouds, or not complete, not decently dense, but not entirely dense. And you're going to get quality indexes for both the cameras and the depth maps as well, or the point clouds as well. So you can filter your data based on that. And I should say, new versions of the dataset with better ground truth and more videos will come out, we hope, on a regular basis. So stay tuned. This is version 1.
Great to know. And also a minor clarifying question from Vincent. Do you use foreground background masks to enforce reconstruction loss? So this is in the Core 3D results that you presented.
Yes, I think that was actually the case, indeed. So in fact, that's not entirely unsupervised, right? So good point. That's why I will be working on some neural diff, in which case you don't have any mask supervision. Of course, the point is to find the masks in the first place.
Got it. And maybe one more question about the data set. And again, do you make use of depth for any kind of supervision to train your NERF-like models?
Okay, so I believe this was tried, and we never observed a benefit yet, which is extremely strange because you would expect depth to be very useful, if nothing else, to cut down training time, right? Because it basically gives a ballpark solution right away. So I don't think we understand that well enough to be able to say, but when we tried before to use depth for supervision compared to not using it, that was not helpful. I think that's not the last word, though. I think it must be helpful somehow.
Got it. Thank you. Let's see. I don't believe we have any more questions from the audience. If you do, please type in your questions in the chat box.
Of course, I forgot to say, if you want to work with us, we have a bunch of positions open, as you can see here on the slide. So yeah, if you want to get in touch.
Absolutely. But this was an amazing talk. Thank you so much, Andrea, and for the discussion as well. I'm not sure if you're going to be able to make it to the panel discussion later today, but if you can, we of course will be great to see you there as well.
Okay, I really hope I will be able to make it. So hopefully see you later.
Okay. Thank you so much. Appreciate it.
Thank you. Bye-bye. And thank you for inviting me.
All right. So so this is the end of session 1. Next, we're going to move on to the poster and the breakout sessions. I'm just going to share my screen. Give me a moment. All right, so the first event that we're going to have during the poster and the breakout session is, of course, the poster presentations themselves. In order to facilitate or to kind of simulate what would happen at a real conference, one of our co-organizers, or Litany, has created this gather.town space, which has 20 posters. So we've laid out 20 posters to simulate like a real conference experience. The URL to that, we will post it on the chat box, but also it's on the slide that you see here on the screen.
I just posted it. Yeah.
Awesome. Thank you, Or. Meanwhile, as we move to gather.town for the more interactive session, I'm going to leave all the videos from the posters playing in this particular Zoom room. So, if you join into the Zoom room later, you're welcome to, of course, come by to the poster presentation, but we are also going to be playing the videos for all the posters here. All right, so with that, let's move to the interactive gather.town session. See you all there.
We present LEAP, a neural network architecture for learning articulated occupancy of people. Our method is able to represent multiple persons and to generalize well to unseen humans. All these subjects are represented by LEAP. Neural implicit representations have been proposed to model rigid 3D objects. They are continuous and allow for differentiable interpenetration tests with the environment. However, they are designed for static scenes and do not generalize to deformable objects, which makes them unsuitable for representing articulated 3D human bodies. One special case is neural articulated shape approximation work, shortened NASA, that takes a set of bone transformations of a human body and represents the 3D shape of the subject with neural networks. While demonstrating promising results, their occupancy representation only works for a single subject and cannot encode multiple body shapes. Therefore, the widespread use of their approach is limited due to expensive per-subject training. We follow the good practice of traditional body modeling techniques and build our occupancy model in the canonical pose. Our second idea is to learn a generalized linear blend skinning function to transform any query point to the canonical space, where we can conveniently perform a reliable occupancy check. The input to our system is a set of bone transformations. They are first transformed by 3 encoders to a global feature vector that incorporates information about the human shape, structure, and pose. This feature is then customized for each bone by per-bone learnable linear layer. On the other side, the input query point is projected to the canonical pose via the inverse linear blend skinning network that predicts skinning weights as an intermediate step. These sparse weights are used to create a local point feature vector as a weighted average of the bone features. Lastly, an occupancy multi-layer perceptron predicts whether the query point is located inside the human geometry by taking as an input the estimated canonical point, the associated local point feature vector, and an additional feature that is based on a cycle distance. For this additional cycle distance feature, we introduce another linear blend skinning network that maps the estimated canonical point to the posed space, thus defining a cycle as distance between this new point and the corresponding input query point. The cycle distance benefits the generalization of our method and produces significantly fewer artifacts. The displayed close-up animation shows that our model captures the pose-dependent deformations in the canonical pose. Compared to the baseline, the reconstruction quality of our method is significantly better and is able to express details such as fingers and face. Our method outperformed the baseline across all settings and evaluation metrics by a large margin. Lastly, we propose an efficient point-based loss that can be used to resolve collisions with the environment. A recent work, Place, generates realistic human bodies in scenes. However, it requires a pre-computed SDF to avoid collisions with geometry and often generates unrealistically penetrated humans when multiple people are generated in a single scene. Our method is able to effectively prevent intersections with other people and the mesh-based geometry without requiring an SDF. Our approach is robust and resolves even complex penetrations with the environment, which cannot be resolved with mesh-based intersection methods. Thank you.
Hi, I'm Zhenyu. I'm glad to present our work, Synergies Between Affordance and Geometry, 6-off grass detection via implicit representations. In this paper, we study the problem of 6-off robotic grasping in dense clutter. It's an important part of robotic manipulation and has many applications including bin picking, part assembly, and logistics. In this problem, we are given a partial observation of a clutter of objects, and we need to predict a 6-off grasp pose which can grasp one object and move it out of the clutter. Robotic grasping is a long-studied problem. Pioneer work solved the problem with geometric analysis. These methods give analytical solutions, but they usually require a full 3D model to compute geometric properties, which are not available in real world. Recent trends are end-to-end grasp learning with deep neural networks. These methods show high grasp performance, but they do not include explicit geometry reasoning. As a result, they often have limited generalization beyond training data. There are also some works that combine geometry reasoning and grasp prediction. They first reconstruct the 3D shape and then predict the grasp. These methods can operate on raw visual observations, but the grasp performance is subject to the 3D reconstruction quality, and 3D reconstruction itself is a difficult problem. Inspired by previous works, we believe the underlying reasoning in grasp affordance prediction and geometry understanding are not isolated. By grasp affordance, we mean likelihood of grasp success and grasp parameters. There are synergies between affordance and geometry reasoning. For example, when we want to grasp this mark given this observation, we know the graspable region is near the handle, so we would reconstruct the handle in our mind, and based on the reconstruction, we can predict how to grasp this mark in detail. In this paper, we exploit the synergies between affordance and geometry and propose to jointly learn grasp prediction and 3D reconstruction. The first thing we need to do is to find a unified representation for grasp affordance and 3D geometry. Inspired by recent progress in 3D vision community, we use implicit neural representations. Implicit neural representations are neural networks that map from 3D coordinates to quantities at the points. The quantities can be occupancy, sign distance function, and so on. Implicit neural representations are continuous and differentiable and can adaptively allocate computation. Then let me introduce the detailed architecture for our method Giga. First, we encode the input observation into a structured feature grid. The feature representation is shared for affordance and geometry reasoning. For affordance prediction, given a grasp center, we query the local feature at that point. After passing the local feature and grasp center into the learned affordance implicit function, we predict the grasp quality, orientation, and gripper width. It is a similar process in geometry prediction. We predict occupancy probability at a random query point. We collect our training data in a self-supervised way using Pi-Bullet simulator, and we set up two scenes, packed and pile. In the simulated experiment, we compare our method Giga with two baselines. The first one is VGN, the sort of grasping in dense clutter. The other one, GigaF, is an ablative version of our method where geometry learning branch is removed. Since we are learning a continuous affordance function in Giga, we can query at a higher resolution than VGN. We denote these results as GigaHR. We evaluate the grasp success rate and declutter rate of all methods. Both metrics are better when they're higher. Giga is better than GigaF. It indicates geometry learning facilitates affordance learning. GigaHR is further better than Giga, which indicates the continuity of implicit neural representation enables higher precision. We also visualize the learned grasp affordance and predictions. Giga is able to predict more accurate and diverse grasps, especially in occluded regions. In real robot experiments, Giga first grasps the small object behind because grasping it is unlikely to induce collisions and gradually declutters the scene. Meanwhile, VGN gives up after 2 consecutive failures. We further visualize the 3D reconstruction results. We compare Giga with GigaGeo, which discards the affordance learning branch and only learns 3D reconstruction. The reconstruction of Giga focuses more on graspable parts of objects like the handles. In summary, we validate that the synergies between affordance and geometry can help improve grasp prediction, especially in occluded regions, and these synergies also drive the reconstruction to focus more on action-relevant parts. We also show that implicit neural representations serve as continuous and compact representations for both affordance and geometry. With structured feature grids and local implicit functions in Giga, we can combine voxel grids with neural implicit functions. Our codes and pre-trained models are available on this website. Please feel free to try them out.
Hi, I'm Lior Yariv from the Weizmann Institute of Science, presenting volume rendering of neural implicit surfaces, which is a joint work with Jiatao Gu, Yoni Kasten, and Yaron Lipman. The motivation for this work is to learn the geometry and appearance of an object from a collection of its images. An increasingly popular approach for tackling this problem is differential rendering, where the idea is to simulate the rendering process in a differentiable way and minimize a loss comparing the ground truth pixels intensities and the rendered ones. One specific approach is volume rendering, where the 3D scene geometry is represented using a volume density function, and the appearance represented as a radiance field. It has recently been shown that representing both the density and light fields as neural networks can lead to excellent prediction of novel views by learning only from a set of images. The pixel intensity is given by the volume rendering equation, that is the expected light along the ray according to the opacity. The opacity indicates for each depth t the probability a light particle will be occluded after traveling distance t from the camera. In essence, volume rendering is all about approximating the integrated light radiance along this ray. This integral is approximated using a numerical integration scheme at some discrete samples. Since the opacity changes in a concentrated region near the object's boundary, the choice of the samples point has a crucial effect on the approximation quality of this integral. However, the main challenge remains approximating the opacity function, which tends to have very high derivatives. This neural volume rendering approach, presented in NERF and developed by many follow-up works, modeled the density function sigma with a general-purpose multi-layer perceptron. Although producing plausible renderings, looking at level set of the density function learned by NERF reveals a noisy geometry reconstruction. Secondly, it is not clear how to sample a general-purpose density function while making sure no parts of the geometry are missed or overextended. Our solution is to represent the general-purpose MLP densities with densities from a certain family. We define the volume density function as Laplace's cumulative distribution function applied to a signed-distant function d, and alpha and beta are learnable parameters. Intuitively, the density models a homogeneous object with a constant density alpha that smoothly decreases near the object boundaries, where the smoothing amount is controlled by beta. The geometry is represented implicitly as the zero-level set of a neural network D, describing the signed-distant function for each point in space to the surface. This simple density representation has the following benefits. First, it provides a useful inductive bias for the learned geometry, and provides a principled way to reconstruct the surface as the zero-level set of D. Second, as we show next, this density definition allows bounding the approximation error of the opacity, leading to an accurate sampling of the viewing ray. We consider the approximation error when approximating the opacity function using the rectangle rule, computed according to some given samples. To bound the error of the rectangle rule, we need to bound the derivative of the density between two samples. To obtain such bound, we use the signed-distant function's unique property of gradient with norm 1, and the fact that the surface has to reside outside the union of these two spheres. Hence, the minimal distance to the interval is furnished by the black bold line. This gives us an error bound for the opacity approximation, where in order to reduce it and get a good approximation of the opacity, we can either add more samples or enlarge beta, since smoothing the opacity will make it easier to approximate. With those observations, we suggest a simple algorithm to reduce the number of required samples in practice, where we iteratively reduce beta and upsample more points while maintaining the desired error bound. With the final opacity approximation, we produce a set sample to be used in the volume rendering numerical integration. To recap the training process, given a set of images with camera parameters, our system consists of two fully connected neural network D and L, and our training loss consists of two terms, the color loss and the icon loss, encouraging D to approximate a signed-distant function as in IGR. Motivated by IDR, we incorporate also the level set normal and a global feature vector in the radius representation to achieve geometry appearance disentanglement. Let's look at the results. We demonstrate the efficiency of all SDF by reconstructing surfaces from the DTU dataset, which contains multi-view images of different objects with fixed camera and lighting. Note how VolSDF produces smoother, more accurate surfaces compared to NELF, while avoiding artifacts in the renderings. We also evaluated VolSDF on the blended MVS dataset, containing scenes with complex backgrounds. Furthermore, we showed the unsupervised disentanglement of geometry and radiance field by switching the radiance fields and densities of two independently trained models. This result provides strong empirical evidence for R decomposition to densities and radiance fields. For more information, please check our paper. Thank you for listening.
With neural scene graphs for dynamic scenes, we propose a new learned scene graph representation that represents dynamic multi-object scenes and decomposes a scene into its individual object representations. Recent methods such as neural radiance fields or NeRFs have shown impressive results in the reconstruction task for static scenes, but they fail to represent dynamic scenes, as you also can see here on this kitty scene in the left corner. Just adding a temporal component to the input, what we did with NeRF, does not solve this challenge either and still suffers from severe ghosting. With our method, neural scene graphs, we are not only able to reconstruct dynamic multi-object scenes, but we also can manipulate individual scene components, as you can see here, where we took a video from the kitty data set and rotated some objects. To describe how we represent a dynamic video, let us look at this particular frame. Assume we have a camera model, then we represent the scene using a scene graph. A scene graph is an acyclic directed graph with objects as nodes and transformations at the edges. This concept from graphics allows us to describe the transformation from the camera to an object by traversing the graph and collecting the respective matrices. For example, here we add a node for a truck in a graph and the projected bounding box, and the frame can be seen on the upper right side, where we now try to reconstruct that frame that I showed before. Given a scene graph as described, we can now synthesize an image by tracing a ray through the scene for each pixel in a rendered image, and then calculate the intersection points with all nodes, as you can see here with that bounding box. To do the ray tracing at the intersection, we sample points at fixed distance in the box. On the right upper side, you also see that pixel in the image that we want to reconstruct. To reduce the complexity in a large scene, object representations of the same class, such as trucks in our example here, are described by a single shared representation model. We model the shared representations independent from each object size, and those embed the model in a coordinate system bounded between -1 and 1, to which you get by having a scaling transformation from the individual object node to the shared scene representation of that object class. Next, we discuss individual representation models. Although not limited to an individual object level representation, we choose neural radiance fields for all local representations to reconstruct the color and opacity values. All sampling points and respective ray directions that we got from these intersections calculated before can be efficiently transformed into this shared coordinate frame using the transformations along the scene graph's edges. The object radiance fields are slightly adjusted to account for changes in global scene illumination by adding the global location as an additional input, which is P in that equation above. And to distinguish unique objects of the same class, such as multiple trucks, we add a jointly trained latent vector L for each individual object. With our neural scene graph structure, we are able to describe multi-object scenes by adding each object's 3D location and size. So we just repeat the steps that we did for this truck for all other objects, such as for those cars here. We just add the 3 cars and later evaluate just a single radiance fields for all cars, which makes this approach quite efficient. For statics part of the scene that do not change over time, we just add one background NeRF. In our case, with those front-facing scenarios with Kitty, we use fixed number of parallel planes between near and the far clip. We then calculate again the intersections and reconstruct the frame, as you can see here. After we constructed a single frame, we can now look at dynamic scenes. For that, we adjust all the transformations according to that frame and also add new nodes to the scene graph, as you can see here with that car that is now appearing and the new transformations to all those nodes seen in the frame. The scene graphs in all our experiments were trained on videos either built from object tracking results using off-the-shelf trackers or manual labels. After we evaluate the sampling point along array, we add up the obtained color and opacity values in the volume renderings equations known from NERV. So as shown before, we can do some kinds of manipulations such as rotations, translations, etc. And note that the transformations preserve global light transport. The specular highlight moves in accordance with the fixed scene illumination. We can also have novel view synthesis by changing the camera angle. With neural scene graphs, we present a method that efficiently decomposes a dynamic scene and represents it with multiple dynamic static scene components. I'm really looking forward to great discussion on that topic.
Hi, I'm Song Yo, and I'm super excited to present our 3DReps 2021 paper, Shape as Point, a differentiable Poisson solver. This is a joint work with Max, EE, Michael, Mark, and Andreas. What do you mean by shape as point? In short, SUP. For any shape, we can either represent it as dense geometry, for example mesh, as shown on the right, or an oriented point cloud on the left. The proposed method SUP is a differentiable version of classic Poisson surface reconstruction algorithm. And SUP is a new type of 3D shape representation. It allows us to efficiently connect the points with the mesh through an implicit indicator grid. The core of our SUP representation is a versatile and differentiable Poisson solver. We call it DPSR. Given some oriented point clouds, our Poisson solver can output a dense regular grid, indicating whether a point is inside the underlying shape or not. We can then easily run Marching Cube on this integrated grid to obtain a mesh. Solving the Poisson equation is the cornerstone of our SUP representation. Here we provide the iteration of this equation using a 2D circle as the shape for illustration. This shape can be represented as an implicit indicator function, and here we calculate the gradient of this function. Now the premise of the Poisson equation is that the point normals are an approximation of the gradient. By taking the divergence operators on both sides of the equation, we can get a partial differential equation that we can solve as following. To solve the linear Poisson equation, we discretize the function values as well as the differential operators. In order to efficiently solve the Poisson equation, we choose to use spectral methods. Spectral methods transform the original signal into spectral domains so the derivatives can be computed analytically. A very important point is spectral methods leverage the fast Fourier transform operations that are well supported for GPUs, TPUs, as well as mainstream deep learning frameworks. Moreover, the solver itself is extremely simple and can be implemented in only 25 lines of code. Let's first see how we apply SUP in optimization-based surface reconstruction. First, we need to input an initial oriented point cloud. To demonstrate the flexibility and robustness of our model, we initialize the point cloud from a sphere. We can then pass this initial point cloud into our differentiable Poisson solver, DPSR, and obtain a dense indicator grid. From the indicator grid, we can extract a mesh using Marching Cube, then sample points from the mesh, and calculate the chamfer distance with respect to the given target unoriented point cloud. This is the forward pass of the optimization pipeline. As for the backward pass, we backpropagate the chamfer loss through the sample mesh points P mesh to optimize the source point cloud P. All terms in the backward pass equations are differentiable, except for the Marching Cube steps, so we cannot directly backpropagate the loss. However, the gradient for this part can be efficiently approximated by the inverse normals of the sample mesh points. Now, every step is differentiable, including our DPSR, so we can update the source point clouds under the optimization pipeline. Here, we show the optimization process of SUP. We consider a cost-to-find strategy to speed up the optimization process and also a point resampling strategy to eliminate outlier points that drift away from the surface, enforcing a more uniform distribution of points. After showing optimization-based reconstruction, we are wondering, can we further leverage differentiability of the proposed Poisson solver for deep neural networks? Next, we will show that we can plug our solver in the pipeline of a 3D reconstruction deep model and enable end-to-end training of neural network parameters. Here we show the learning-based pipeline of our model. Input some noisy unoriented point clouds. The goal is to learn a network to predict both offsets and normals of these points. So this cleaned oriented point cloud as the output from the network is then passed into our DPSR and obtain an indicator grid. To learn the network parameters in a supervised manner, we assume having watertight and noise-free meshes for supervision. We can simply sample surface points and normals from the ground truth mesh and run our Poisson solver to obtain an indicator grid, which will be served as the supervision signal. Finally, we can calculate a L2 loss over the ground truth and the predicted indicator functions, and takes the advantage of our differentiable Poisson solver to learn the network parameters. During the inference, the network output oriented point cloud is passed into our DPSR, and we can then extract a mesh from the predicted indicator grid. Now let's look at the results of learning-based 3D reconstruction. We train and evaluate on ShapeNet, and here we show the comparison on two types of inputs. On the top is the point clouds with high noise levels, and on the bottom we can see the point clouds with strong outliers. Here we show the comparison to ConfoNet. As can be noticed, our method produces 3D reconstructions with better geometric details, and the inference time is over 5 times faster. More information, including code and data of our method, can be found in our project page. Thank you for watching.
In this work, we present unconstrained scene generation with locally conditioned radiance fields. This is a joint effort by Terence de Vries, Miguel Angel Bautista, Nitish Srivastava, Graham Taylor, and Joshua Susskind, representing a collaboration between Apple, the University of Guelph, and the Vector Institute. Our work is primarily motivated by the success of 2D generative models such as StyleGAN. These models have demonstrated extraordinary ability to synthesize realistic-looking images, but perhaps even more useful is their ability to disentangle the patterns and features that define the underlying data distribution itself. By leveraging the representations learned by these models, many challenging downstream tasks, such as inpainting, super resolution, or image manipulation, can be solved with very little or even no additional training data. Inspired by this success, we ask ourselves, is it possible to learn generative models for the more challenging case of unconstrained 3D scenes? Specifically, our goal in this work is to learn a distribution over complex, realistic, indoor scenes. In order to successfully accomplish the task of generating realistic-looking scenes, we expect that the model will need to develop a low-level understanding of how scenes are constructed, which we call a scene prior. Learning such a scene prior could be useful for a variety of difficult downstream tasks, such as content creation for augmented and virtual reality, scene completion, scene editing, mapping and navigation, or as a world model for reinforcement learning. Our model follows an adversarial learning framework, where the generator tries to map noise to realistic-looking outputs that will fool the discriminator, and the discriminator tries to distinguish between real and fake samples. Here, we show the architecture for a standard 2D image-generating GAN, with a convolutional generator and discriminator. To generate 3D scenes instead of 2D images, we can replace the convolutional generator with a conditional MLP that parameterizes a radiance field. The MLP maps 3D coordinates and latent codes to color and density values, allowing us to render images by sampling points along camera rays and combining them via volumetric rendering. During training, we sample radiance fields and render images from them at random camera poses. The rendered images are then evaluated by the discriminator, similar to a standard 2D GAN. This architecture has been shown to work well for generating centralized, single objects, but for large complex scenes, we find performance to be limited. A limitation of this approach is that each scene is represented by a single, large radiance field, which may be difficult for the MLP to encode with high fidelity. To improve the expressiveness of the generator, we map the global latent code Z to a 2D grid of local latent codes W using a convolutional decoder. These local latent codes can be interpreted as a latent floor plan representing the scene. Conceptually, this strategy decomposes the large scene-level radiance field into many smaller local radiance fields, which are more manageable for the MLP to represent. Additionally, we replace the global coordinate system with a local coordinate system aligned with the local latent grid. This substitution makes the local latent codes spatially independent, such that they can represent the same radiance field irrespective of their global position. This adjustment encourages feature reuse and allows latent codes to be moved around for scene manipulation. We evaluate the effectiveness of the approach architecture on 3 scene datasets: Vizdoom, Activision dataset, and Replica. We find that the scene decomposition scheme of GSN is effective, allowing it to outperform concurrent radiance field-based generative models such as Graph and PyGAN on all 3 datasets. In contrast to previous 3D GANs, which restrict camera pose to a viewing sphere centered around the generated object, GSN trains on a wide range of camera poses, allowing for unconstrained scene exploration during inference. Here we demonstrate some scenes sampled from our model after training on the replica dataset. In addition to unconditional scene synthesis, we can also use the prior learned by GSN to invert observations and fill in missing parts of the scene. Given a trajectory of images through a real scene, shown on the left, we invert GSN's generator to find a scene radiance field that minimizes a reconstruction error. We can then render from this radiance field to complete the rest of the trajectory, as shown on the right. Finally, we demonstrate how the latent floorplan W can be used for spatial scene editing. In this example, we mirror the local latent grid, resulting in a mirrored version of the scene when rendered. In summary, we've introduced generative scene networks, a generative model which learns to synthesize radiance fields of indoor scenes, and allows for unconstrained scene exploration. We show that decomposing large radiance fields into a collection of many small, locally conditioned radiance fields improves generation quality. Finally, we demonstrate that GSN learns a useful scene prior, which can be leveraged for several useful downstream tasks. Code and training data can be found on GitHub at the link provided. Thank you.
We present ASDF, Learning Disentangled Sign Distance Functions for Articulated Shape Representation. We investigate a differentiable category-level articulated object representation. We represent articulated objects with separate codes for encoding shape and articulation. During inference, given an unseen instance, our model first infers the shape and articulation codes via backpropagation. With the inferred shape code, the model can generate shapes and unseen articulations by only changing the articulation code. We visualize generated shapes of holdout instances in multiple categories selected from the shape-to-motion dataset. Each column shows the input and generated articulated shapes of different refrigerator instances. Note that for different instances, the door articulation axes are placed differently. The proposed method is able to model refrigerators with different kinds of door types using a single network. Similarly, for eyeglasses, given a single instance with some unknown joint angles, the temples can be articulated by only modifying the joint angle inputs. For washing machines, our method also successfully captures different body shapes and generates valid articulated shapes. We built our work on deep sign distance functions, where a sign distance is predicted for a random sampled point. To model articulated objects, our first insight is that shapes articulated from the same instance should share the same shapecode, as illustrated with the brown staplers here. Shapecode sharing encourages that the shapecode only captures part geometry. To capture the articulation variances, we further input the model with articulation codes. The insight is that even though the shapes look quite different for different articulations of the same instance, a good representation should capture this variability in a low-dimensional space. Specifically, during the training stage, we first randomly initialize one shapecode for each instance and concatenate the shapecode with the sampled point. And then the concatenated shapecode and sampled point are input to a shape embedding network to form a shape embedding. To model articulation, each sampled point is also concatenated with the articulation code and passed through an FC layer to produce an articulation embedding. Then the shape embedding and articulation embedding are jointly input to another multilayer perceptron to estimate the sign distance. Here we name the combination of the shape embedding network and the articulation network as our articulated sign distance function f theta. If part labels are available, a linear classifier is added to the last hidden layer of the articulation network to simultaneously output the part label. As noted with the red color, shape codes and disentangled sign distance function parameters are jointly optimized during training. During the inference stage, given one shape, the articulated sign distance function parameters are fixed, and the shape codes and joint angles, as shown in red, are jointly inferred via backpropagation. To generalize our model to auto-distribution and unseen data, we further propose a test time adaptation step to adjust the model parameters during inference. The idea is we adapt the shape embedding network to better fit the observed instance. In the same time, the parameters of the articulation network and the inferred shape and articulation codes remain unchanged. Note that due to the separation of the shape embedding network and the articulation network, the disentanglement is still maintained when the shape embedding network is adapted. With the inferred shape codes and updated shape embedding network, new shapes can be generated by only changing the input articulation. We task our model with reconstruction from real-world depth images. Quantitative results show that our method reconstructs better shapes than the baseline. Note that on top of reconstruction, our method can also generate new shapes with other articulations. We test the trained models on partial point clouds generated from different numbers of depth images. Visually compared to the baseline, our reconstruction results preserve rich details. Quantitative evaluations show that our method outperforms the baseline by a significant margin. Here we also showcase our method against deep SDF in terms of interpolation. Our disentangled space ensures that the interpolated latent space produces faithful interpolation results. Our source code is available.
Hi, I'm Abdullah Hamdi, and I'm going to present our ICCV paper, MVTN, Multi-View Transformation Network for 3D Shape Recognition. This work is from our IVL group at KAUST, led by Dr. Bernard Ghanem. 3D point clouds are widely used for 3D representation in computer vision due to compactness, flexibility, and because they come naturally from sensors like LiDAR and RGBD cameras. On the other hand, humans don't have 3D sensors. We are naturally looking into objects from different angles. We rely on the images projected to our eyes to identify the 3D world. Multi-view approaches are the oldest form of deep learning for 3D understanding, with the introduction of MVCNN in 2015. The benefits of multi-view at the time were clear, leveraging the 2D computer vision architectures and methods like CNNs, leveraging large labeled and diverse 2D image datasets like ImageNet, and providing a simple 3D processing pipeline. A line of works continued the development on multi-view, like RotationNet and most recently ViewGCN, which we used in this work. But these methods use heuristic approaches for selecting fixed views and mostly rely on pre-rendered image datasets. Such heuristics may not be optimal to get the best possible results. We aim to do a dynamic setup, relying on online rendering to enhance the downstream tasks by learning to regress viewpoints adaptively for each shape. Actually, this active setup is how children learn about objects, by changing the viewpoints and interacting with the 3D world. Our MVTN is trained end-to-end with the multi-view network without extra supervision. This is the MVTN pipeline. It consists of a differentiable renderer R that renders the object S according to some scene parameters U to get the multi-view images X. The goal of MVTN is to predict the parameters U, which are the azimuth and elevation angles in this work, for every object S. We extract coarse features from the object and learn an MLP to predict the scene parameters. The pipeline is trained end-to-end with only the task loss, which is cross entropy for classification. Here we show how these learned viewpoints for the car object differ from fixed circular or spherical viewpoints. We used PyTorch 3D for both differentiable mesh rendering, when mesh data is available, and differentiable point cloud rendering, when only 3D point clouds are available. The datasets we used include ModelNet 40 for classification and retrieval, ShapeNet Core 55 for retrieval, and ScanObjectNN that consists of realistic 3D scans of objects, which has 3 variants. Our ModelNet 40 results show competitive performance. The highlighted setup shows our implementation with PyTorch 3D Renderer, which shows our MVTN achieves higher overall accuracy than state-of-the-art VuGCN with 93.8%, and even higher than Point Transformer from this ICCV. On the realistic ScanObjectNN dataset, we achieve state-of-the-art on all the 3 variants, with up to 6% improvement in the case where background is combined with the object. On 3D shape retrieval on both ModelNet 40 and ShapeNet Core 55, MVTN sets new state-of-the-art performance on both datasets in terms of retrieval mean AP. Here, we show some qualitative examples of shape retrieval. We also evaluate the robustness of our MVTN approach to rotation by randomly rotating the object in test time around gravity axis. MVTN performs better than strong baselines specialized to this task of rotation robustness. Another robustness aspect we study is the occlusion, which is an important factor that affects scanned data. To simulate occlusion, we crop the object from its 6 faces with different percentages, 0 to 75%, and from different directions. Here we show how the objects are affected by cropping them with different occlusion ratios and from 4 different canonical directions. These occlusions are introduced in test time. Here we show the average test accuracy in ModelNet 40 over the 6 canonical occlusion directions, plus minus x, plus minus y, and plus minus z, for different occlusion ratios. MVTN shows more robustness in this setup than the baselines. We can plot the test accuracy versus the number of views used in training MVCNN. Using the learned MVTN views achieve consistent 2% improvement over fixed or random baselines across multiple number of views. Please check the paper and code for more details. Thank you.
We present GangCraft, a method for unsupervised 3D neural rendering of Minecraft worlds. GangCraft is trying to tackle the problem of word-to-word translation. It is an extension of the 2D image-to-image translation problem to 3D. And instead of just converting a single image, it produces a 3D world that can be rendered from arbitrary viewpoints consistently. And particularly, GangCraft converts semantically labeled voxel world to a photorealistic world without any paired supervision and using only widely available data. So now let's quickly look at some results. This is what the input semantic voxel world looks like. And this is the output of GangCraft. As you can see, it has converted the input semantic voxel world to something that looks much more photorealistic. In fact, pretty close to real life. Here is an example of a desert world where it's full of sand. This shows that GangCraft can handle scenes that have significantly different label distribution compared to training data. Here is another example where the world is completely covered by snow. GangCraft can render the same world in different ways based on the style conditioning images. Here we can see the style of the 3D world changing according to which style conditioning image we select. Let's look at it again. Things go from morning to sunset, and the sky also changes between cloudy and clear. Here we compare GangCraft with baselines. In contrast to image-to-image methods like Munit and Spade, GangCraft produces with consistent result. At the same time, the image quality of GangCraft is also beyond the other two with consistent baselines. Here is how GangCraft works. Our goal is to render a semantically labeled voxel world, such as the one used in Minecraft, to a realistically looking world. It would be an easy problem that can be solved by supervised training if there exists paired 3D data. However, 3D data is unavailable for large natural scenes, and we do not know what would a Minecraft world looks like in reality. Lastly, the distribution of various attributes between Minecraft scenes and real images are often very different. For example, in a desert world, most of the visible voxels are deserts. However, when we look at a large collection of internet images, desert only account for about 5% of pixels. This mismatch can make the unsupervised training rather tricky. To overcome these issues, our solution is to use pseudo-ground truths and adversarial training. Here is how we generate the pseudo-ground truths. Given a semantically labeled voxel world, we sample camera locations and obtain segmentation map. These segmentation maps are fed to a pre-trained image-to-image translation network to obtain pseudo-ground truths. The image-to-image translation network was trained on a large collection of real images and is able to produce something that looks rather real. Here are some examples of segmentation maps and their corresponding pseudo-ground truths. Such pseudo-ground truths are not view consistent, but our method is designed to be robust to such noisy training data and still produces good-looking results. Here is how GaNcraft is trained. We sample a camera, cast rays, and project the voxel to the camera to obtain a segmentation map. We pass the segmentation map through a pre-trained image-to-image translation model to generate the pseudo-ground truth. In our model, each corner of the voxel is assigned a learnable feature. We sample n points from the voxel along each ray. For each point, we compute the point feature by trilinearly interpolate from the corner features. We pass the features through an MLP and blend the output features to obtain the feature for a single pixel. We do it for every pixel to form a feature map. We then pass the feature map through a convolutional neural network to obtain the final output image. Both the MLP and the CNN are conditioned on the style of the pseudo-ground truth image. This helps explain away the view inconsistency of pseudo-ground truth images, and allows us to sample different styles at inference time. As for losses, we apply GaN loss, perceptual loss, and pixel-wise losses between the output and the pseudo-ground truth image. We also apply a GaN loss between the output image and the randomly sampled real image to improve realism. Please refer to the main paper for further details and quantitative results.
We present a new method for 3D surface reconstruction based on neural implicit surface representation and volume rendering. In this project, we want to reconstruct the surface of a scene or object given several pose images as input. Recent neural volume rendering methods, such as NeRF, have shown impressive results on novel view synthesis. However, it lacks constraints on surface geometry and thus cannot be used for accurate surface reconstruction. In the meanwhile, existing neural surface reconstruction methods, such as IDR, require foreground masks as supervision to make training converge to a valid surface. Furthermore, IDR easily gets trapped in local minima and therefore fails to reconstruct objects with complex structures. This is mainly because it only considers a single surface intersection point for calculating the color of each ray. In contrast, NeRF is more robust in this case with complex objects because the gradient in volume rendering method will be backpropagated to all the sample points. However, NeRF is incapable of extracting accurate surfaces due to its lack of surface constraints. Therefore, to address the above issues, we propose a new neural rendering scheme called NEWS for accurate and robust multi-view surface reconstruction. Here we first show a comparison. Our method achieves the best reconstruction quality. Instead of standard volume rendering or surface rendering, our basic idea is to perform volume rendering on top of surface representation with neural scientists and fields. In this way, we can have the best of both worlds, that is, an accurate surface representation using the neural SDF model and a robust network training. The key to learning an accurate SDF representation from 2D images is to build an appropriate connection between output colors and SDF, that is, to derive an appropriate wave function on the ray based on the SDF of the scene. Our idea is constructing wave function following the framework for volume rendering with aid of density function. However, deriving the proper density function from an SDF is not trivial. Intuitively, one would first construct a bell-shaped density function phi, such as the PDF of logistic distribution or Gaussian distribution from the sign distance fields, which we call S-density here. For volume rendering, the naive approach of simply applying the standard volume rendering methods to the S-density would lead to geometric bias in the reconstructed surfaces. That is, the wave function used for blending colors in volume rendering does not attain a local maximum at the ray surface intersection point, as shown in the right figure. To extract high-quality surfaces by volume rendering, there are two requirements on the wave function. First, unbiased, that is, the wave function attains the local maximum at the ray surface intersection. Second, occlusion aware, that is, if a ray has multiple intersection points with thin surfaces, the first hitting point should contribute most to the ray color. We then construct a straightforward way of constructing an unbiased wave function without volume rendering. This wave construction is unbiased, but not occlusion aware. Then we design a wave function that is both occlusion aware and unbiased in the first order approximation of SDF by combining the following two equations. One is occlusion aware but not unbiased, and the other is unbiased but not occlusion aware. We combine them to design the unbiased and occlusion aware wave function. Please check our paper for the detailed derivation. Here we present our designed wave function. As shown in the right figure, the derived wave function is both unbiased and occlusion aware. Here are some results. Given a set of post 2D images of an object as input, we can reconstruct the high-quality surface of the object. Here is a comparison for a setting of using mask supervision. Our method outperforms IDR and NERF in reconstruction quality. Here we show more results of some scenes from the DTU dataset. Here are the results on the blended MVS datasets. We show the ablation study by testing three different kinds of grid constructions described by naive solution, direct solution, and our solution. The quantitative result of naive solution is worse than our weight choice in terms of the chamfer distance. This is because it introduces a bias to the surface reconstruction. If direct construction is used, there are severe artifacts. One limitation of NUS is that it cannot correctly reconstruct textureless regions, such as the inner surface of the right brick. Thanks for watching.
Hi everyone, I'm Romain Loiseau, and I'll present you the work we did with Tom Monnier, Mathieu Aubry and Loïc Landrieux, entitled Representing Shape Collections with Alignment-Aware Linear Models. Imagine you have access to a large, unstructured collection of 3D models and want to understand its content better. Browsing through the collection and identifying groups of related shapes would be a time-consuming approach. We propose a principal approach to automatically group shapes and summarize them using a prototype shape associated to a linear deformation model. Our goal in this paper is to summarize and understand large shape collections, such as ABC and ShapeNet, by offering an easily viewable summary of them in an unsupervised manner, allowing us to perform downstream tasks such as few-shot semantic segmentation. This is a difficult problem, because the distance between shapes may be difficult to define using standard 3D point cloud distances, such as chamfer distance. For example, we want the distance between all of those chairs to be 0, even if they differ by a rotation. It's also difficult to compute the average of several shapes. For example, chairs can have arms or not, and the average will end up fuzzy. To answer these issues, we introduced linear shape models, a powerful and expressive data structure in three-dimensional space that allows to meaningfully summarize sets of shapes. At first, we can simply define a linear shape model as a center shape defined as a 3D point cloud, which we train by minimizing the reconstruction error of the base model, which is an unsupervised task. At this point, the reconstructed model is the learned center shape. On the right, you can see a few learned models on two datasets. To handle the problems of alignment between shapes, each model is then associated with an alignment network, which will learn to align our center shape with a target input point cloud. By doing so, the learned shapes become smoother and can better reconstruct input shapes. We then propose to learn to deform our center shape along a displacement field, To each point is associated a direction in which it can move by varying an amplitude, defining for each point of our center shape a direction in which points can move, which both improves reconstructions and enables us to visualize our linear shape models as continuously indexed sets of shapes. For example, by learning such families on ShapeNet, we discovered a plane which can be continuously deformed from an airliner to a jet. Our final model is then composed by several models, each having an alignment network and several displacement fields. Here, a direction controls the length of the table legs, while another their width. Applying our method on ShapeNet, for example, enabled us to summarize this dataset, to see at a glance that it's composed by several types of chairs, tables and airplanes, without having to look at all the dataset to know what's inside. This can be particularly useful when considering large collections of scans or CAD models, such as the industry dataset ABC. As our models are in the 3D space, they are quite easy to annotate. By doing so, by either manually or using a few training examples, we can propagate the points labels to inputs to perform semantic segmentation of those. We showed state-of-the-art performances for these tasks on ShapeNet. To conclude, we presented an unsupervised method to represent large point cloud collections as an extension of the deep transformation invariant clustering framework for 3D tasks, which learn linear shape models. We showed state-of-the-art performances for few-shot semantic segmentation and introduced a way to easily summarize large datasets of 3D shapes. Thanks for your attention.
In this paper, we introduce a new method for initializing and training shape-implicit neural representations with sinusoidal activations for unoriented point clouds guided by its gradient vector field divergence. Given an input unoriented point cloud, our goal is to find the surface on which these points were sampled on. One way of representing this surface is the implicit representation. This means that the surface is the zero-level set of an unknown function. In recent years, a popular choice for this function is a neural network that learns either an indicator function or a signed distance function. Most recent work share a similar architecture which feeds each individual point into an MLP to predict its function value. When training with a set of points, the output will look like this. Here, the colors represent different distance values at grid points and the arrows their gradient's direction. Most shaped neural implicit representations differ from each other in their choice of initialization and loss function, as well as activation function. In this work, we focus on the recently proposed sirens, sinusoidal activation function networks by Sitzman et al. So how can we train a siren without normal vectors? The original siren loss function includes a zero-level set term pushing points on the surface to have zero value, an interterm which penalizes points close to the surface for getting low values, an iconal term pushing the gradients everywhere to have a unit length, and a normal term which pushes the gradient direction to match the normal direction for points on the surface. We propose to replace the normal term with the Laplacian term, which pushes the divergence of the gradient vector field to be low off the surface and does not require ground truth normals to train. The intuition for this term lies in the divergence theorem, which states that integrating over the outward flow in a volume using a triple integral of the divergence is equivalent to a double integral of the flux through its encapsulating surface. In the context of neural shape representation learning, this intuitively means that the proposed divergence constraint incorporates additional local information of surrounding normal vectors of the learned signed distance function. If we look at the circle example, we can see that the divergence is indeed low everywhere, except the circle center, which is a sinc point. Therefore, adding a term that will push the divergence to be low is beneficial. This leaves the question of how to properly initialize the network. The initialization proposed by Sitzman et al. Makes the input of each sign activation be Gauss normal distributed, and the output of each sign activation be arcsign distributed. However, for closed shapes and shape space learning, we witness that this sometimes results in ghost geometries, especially without normal vector supervision. Here we can see the SDF, iconal term, and divergence at every grid point at initialization. Atzmon et al. Showed that initializing to a sphere provides many benefits in the context of value and soft plus activation-based networks. Here, we propose geometric initialization for sirens by carefully choosing the weights and biases for the first and last layers. While there are benefits for this smooth initialization, for sign activations, we need high frequencies to capture the fine detail. Therefore, we propose the multi-frequency geometric initialization to insert the high frequencies back and impose a weight regularization to increase their entropy. For full detail, please refer to the paper. Here, we show how both the initialization and divergence loss influence the training process on the 2D L shape. We evaluate the performance of our approach on the task of surface reconstruction and show that without normal vectors for supervision, DIGS outperforms other methods that do not use normals for supervision. Shape-space learning without normal vectors poses a much more challenging problem. However, DIGS learns a human-like shape that resembles the ground truth shapes, but has ghost geometries where competing methods are not able to converge. When adding the normal vectors as supervision, DIGS is able to achieve a result with significantly less ghost geometries, however with somewhat oversmoothed details. This is even more evident when looking at full action sequences. Here, only pink frames are in the training set. DIGS is oversmoothed, but with much less ghost geometries and structural errors, whereas the competition shows more detail, but also many ghost geometries and disappearing hands. Thank you for watching. For further detail, please refer to the paper. Code will be available on GitHub.
We present SNARF, differentiable forward skinning for animating non-rigid neural implicit shapes. Neural implicit representations have emerged as a powerful tool to capture geometry at high fidelity with flexible topology. However, most approaches focus on static scenes only. In this work, we propose to learn a skinning model jointly with the implicit shape, enabling animation of neural implicit avatars. The input to our method is a set of posed 3D meshes in combination with the corresponding object poses. Given this input, we jointly learn a shape and skinning weight representation in canonical space. This allows our model to reconstruct continuous implicit surfaces for unseen poses, even in cases where the target pose is far from the poses observed during training. But how can we deform a continuous function in a differentiable way? Existing methods use backward skinning and learn a weight field conditioned on the deformed point and the object pose. In contrast, in this work, we propose a forward skinning model that learns a weight field conditioned on the corresponding point in canonical space. As illustrated here, backward skinning weights are pose-dependent, do not generalize well to novel poses. In contrast, forward skinning weights do not depend on object pose, and thus generalize more easily to unseen poses. While forward skinning defines the mapping from canonical to deformed space, we also require the inverse mapping for learning a shape model in canonical space. As this inverse relation is a one-to-many mapping, and as it is only implicitly defined, there exists no closed-form solution to it. We tackle this problem by deriving a differentiable forward skinning formulation. More concretely, we first find all canonical correspondences of a deformed point via iterative root finding. We then predict the occupancy of the deformed point by aggregating occupancy information from the set of all roots while conditioning on the object pose. We derive analytical gradients for this process via implicit differentiation to avoid backpropagation through the iterative root finding algorithm. This enables our model to learn both shape and forward skinning weights end-to-end from deformed observations. We now show results on minimally clothed 3D humans. We use 9 out of 10 sequences from the DFAUS dataset for training and evaluate on the remaining one. We first compare the results of our method to the results NASA on unseen poses from the trace distribution. Both methods are able to reconstruct overall shape well NASA skillset joins it doesn't learn skinning weights. In contrast, our method is able to construct the entire shape well. We now demonstrate results of both methods on poses outside the training distribution. In this setting, the baseline fails completely while the proposed forward skinning model generalizes well. Here is another example with a more extreme pose. We now show results of our method on clothed human subjects. We train our model on the CAPE dataset with meshes obtained from 4D scans. In this setting, we illustrate both the learned skinning weights in canonical space as well as the reconstruction for novel, challenging poses outside the training distribution. While in general, our model captures pose-dependent clothing deformation well, it degrades gracefully for more extreme, unseen poses. Finally, as a proof of concept, we also show that our model is able to learn from non-human subjects. To demonstrate this, we chose post-animal meshes from the small dataset for training. As can be observed, our model learns sensible skinning weights and 3D shapes also for animals, which allows for a realistic character control.
Hi everyone, I'm Han-Wen. I'm happy to introduce our work, Hand-Object Contact Consistency Reasoning for Human Grasp Generation. The motivation is to understand how to grasp 3D objects. As we all know, grasping objects is our primary way for physical interaction and is important for building embodied artificial intelligence. In the grasp generation task, the input will be the object point clouds. The output is a human grasp parameterized by the hand manual model. We intend to generate physically plausible and natural human grasps even on out-of-domain objects. However, due to the high degree of freedom nature of human hands, it is hard to generate perfect grasps by directly regressing the hand parameters. So our solution is reasoning the contact consistency between hand and object. What does the contact consistency mean? First, the hand should contact object surface without penetrating into it. Second, there are also possible contact regions on the object commonly grasped by humans. These regions should be touched. We reason the consistency from two aspects as the framework design and the loss function design. We propose two networks in the paper. The first is called Grasp CVE, which is a generative network aiming at generating grasps. In training, the network will learn to reconstruct the input hand conditioning on the input object point cloud. At test time, we sample random latent codes and then generate grasps using the decoder of Grasp CVE, also conditioning on the input object point clouds. The second network is the deterministic contact net, which is used for predicting the object contact map. The contact map are scores defined on each object point, illustrating the possibility to be touched by hand. The input of contact net is both the hand and object. In training, we train the two models separately on ground truth data. In testing, we propose a test time adaptation method for refining the initially generated grasps. We first generate an initial grasp by the Grasp CVE. Then we forward the initial grasp and the object into contact net to predict a target object contact map. If the grasp is good enough, the two outputs should be consistent, which means the hand should grasp on object regions with high contact scores. We use the consistency as a self-supervised loss. Then we learn from the loss for several iterations and optimize the parameters of Grasp CVE. In the end, we get the final grasp. Also, for training the Grasp CVE, we propose two novel loss functions. There are hand-centric loss, encouraging the hand touching object surface, and an object-centric loss, which ensures the object common contact regions of ground truth to be touched. In the experiment, we use three datasets We train a model on all-man training set. We not only test on all-man test set and also test extensively on out-of-domain HO3D and FBHA dataset, where the objects are different from all-man. First, we show examples on in-domain objects and also on out-of-domain objects. We also visualize the grasp before and after test-time adaptation. The grasp becomes more physically plausible and nature after TTA. For evaluation, we mainly use 4 metrics. They are the penetration between hand object, the grasp displacement in the simulation for measuring the stability, the perceptual score, and the contact measurements. Our method outperforms previous SOTA method grasping field for all metrics on in-domain objects, and better than ground truth in some of them. On the out-of-domain HO3D dataset, our method outperforms both grasping field and ground truth in all metrics. If you are interested in our paper, you can check the project website for more details. Thanks for listening.
Hello everyone, I'm Shuifeng. I'm excited to present our recent work, Implicit Scene Labeling and Understanding with Implicit Scene Representation. This is a joint work with Tristan, Stefan, and Andy from Dyson Robotics Lab at Imperial College London. Computer vision communities have long sought to explore the learned scene representations, or neural representations, to overcome several problems in the human-designed ones. Though geometric representation itself has long been a central research topic, we believe that representing geometry and semantics jointly is the right direction for scene models, which are both optimally efficient and the most useful for actional intelligence. In this work, we propose semantic nerve, a scene-specific implicit representation for scene labeling and understanding. Qualitative results of tasks such as label denoising and super resolution are shown below. Because semantics are human-defined properties are not possible with fully self-supervision, in semantic nerve, we explore if minimum in-place labeling is enough to train our system efficiently or not. This is important for practical applications, like when a robot encounters a new scene and only a small amount of in-situ supervision is feasible. Therefore, during experiments, in addition to a set of post-RGB images, we also supply some partial or noisy semantic labels for the images. Here, we show the network architecture of semantic nerve. By formulating semantics as a view-invariant mapping, we augment the original nerve by appending a segmentation renderer before injecting viewing directions. X-aligned positional encoding is used to leave network input to high-dimensional space. Like photorealistic volume rendering, 2D semantic labels can also be computed using weighted summation of semantic predictions across all samples along the race. We train the whole semantic nerve from scratch, jointly under photometric loss and semantic loss using MSE and cross-entropy, respectively. We demonstrate advantageous properties of semantic nerve in various interesting applications such as efficient scene labeling tools, semantic view synthesis, label denoising, super resolution, and so on. We first demonstrate semantic nerve for novel view semantic label synthesis. Since per-frame dense annotations are expensive to acquire, we show that with labels only coming from sparse keyframes, semantic nerve is still able to render accurate dense labels. The confidence of 2D rendering is generally high except object boundaries. Semantic denoising is another interesting and challenging task, given that only heavily crafted labels are available during training. Thanks to the multi-view consistency and smoothness baked in semantic nerve, labels with fine structures can be recovered. Another practical application is semantic label super resolution, because low-res labels are more efficient to annotate or predict. We generate low-res labels with two different strategies. The coarse labels provide dense but possible inaccurate supervision, while sparse labels provide sparse but geometrically accurate annotation. As an attempt to interactive scene labeling, we also validate semantic nerve with much sparser labels, like user-provided annotations. Although only small random seed regions of each class are selected for training, we still reach promise in semantic rendering. Up to now, we have mainly focused on user-provided labels. We also show that CNN predictions can benefit from our fusion process as well. Without using depth information to build dense correspondences, semantic nerve gets the best fusion performance across all metrics on the replica dataset. The last application we show is semantic 3D reconstruction using post images. We first extract the geometric mesh by querying the learned MLP on dense 3D grids. Semantic texture of each vertex is then added by applying volume rendering on its negative normal direction. Even in the unobserved or occluded regions, like the ones behind the sulfur, decent geometry and semantic labels can still be predicted. Thanks for listening. Please visit our project page for more qualitative results.
We propose a pipeline for holistic 3D scene understanding from a single image with implicit representation. From only a single image, we aim to jointly estimate room layout, object poses as oriented bounding boxes, and object meshes, thus achieving semantic understanding and reconstruction of the scene. Previous works like Total 3D Understanding propose to solve the problem following a box-in-the-box manner, which represents the scene as object meshes with oriented bounding boxes placed in a cuboid room layout, and decompose the task in a bottom-up way into layout estimation, camera pose estimation, 2D detection, object pose estimation, and object reconstruction. However, existing works still struggle on understanding and utilizing the scene context like humans to better arrange the placement of objects. For example, it's reasonable to infer from the context that the heavily occluded sofa here should be facing towards the table in the center of the room, instead of the wrong orientation estimated by Total 3D Understanding as shown on the right. Also, it is not well considered on how to avoid the intersection between objects in the final scene reconstruction. Last problem is that due to the use of the mesh representation by the latest single object reconstruction method, the output shape is often low quality and low poly. To tackle the first problem of context understanding, many other works have proposed to use GCN. However, by solely relying on GCN in the task of scene understanding, the problems of object intersection and shape quality remains unsolved, not to mention that even for a model as powerful as GCN, rich features are still required to provide shape priors and context information. To solve the above problems, we turn to implicit representation. Our motivation is that implicit representations like signed distance function can naturally represent whether a point is inside an object and provide a gradient to push it away from the object, which can be exploited to construct a physical violation loss to penalize intersection. Moreover, the latest local deep implicit functions, or LDIF, provides a compact while precise method to decode object shapes from a latent vector by incorporating implicit and structured representation, which can further improve the results of single object reconstruction, and to provide more structured shape priors for GCN. Therefore, we propose to incorporate GCN with implicit representation to solve the above problems. Our pipeline consists of two stages, that is, the initial estimation stage and the refinement stage. In the initial estimation stage, from a single image, we first predict the initial cuboid room layout, and the 2D object detection. Then from each image crop we estimate the initial pose, and embed an implicit shapecode for corresponding object. In the refinement stage, we model layout and objects as a graph to understand the scene context and refine the initial estimation with a graph convolutional network. Respectively, the above initial estimations, features, and shapecodes are concatenated and embedded into node representations, to be further updated with message passing. The updated representations are later decoded into residuals to refine the initial estimation. The refined poses are then incorporated with the object shapes decoded from shapecodes with LDIF to get the final reconstruction of the whole scene. During training, upon all the losses used in Total 3D Understanding including direct supervision on network outputs, we further propose a physical violation loss based on the insight that objects should not intersect, to penalize the points inside both adjacent objects. Here we show our results. In quantitative comparison, our single object reconstruction method produces the most accurate 3D shape compared to other methods, yielding the lowest mean chamfer distance. In 3D scene understanding, we compare to the state-of-the-art methods from aspects including 3D object detection, layout estimation, and camera pose prediction. The results show significant improvement especially on 3D object detection. Here we compare our results qualitatively with the state-of-the-art. For final scene reconstruction, our model has fewer flying objects, better object poses, less intersection, and finer meshes. For single object reconstruction, our method produces 3D shapes with correct topology, smooth surface, and fine-grained details, which clearly shows the advantage of the deep implicit representation. To verify the effectiveness of the proposed components, we carry out ablation study by disabling each of them and comparing on layout IOU and 3D object detection MAP. The study shows that each component contributes to the final improvement of both layout and 3D object detection, that is GCN, 2 features from LDIF for GCN, and physical violation loss. Also, further qualitative comparison shows that physical violation loss does reduce object intersection. In summary, we present a 2-stage single-image holistic 3D scene understanding system based on deep implicit representation. We also propose a local implicit shape embedding network based on LDIF, which extracts latent shape information from a single image and leads to superior geometry accuracy. Furthermore, we propose a novel GCN-based scene context network to refine the object arrangement which well exploits the latent and implicit features. Finally, we propose a physical violation loss with the implicit representation that effectively prevents the object intersection. Our code, data, pre-trained models are available online. Thank you.
Hello everyone, my name is Mustafa Hajij. Today I'm going to talk to you about persistent homology and graph representation learning.
We present LEAP, a neural network.
All right, welcome back, everyone. Seems like there was around 30 plus people in the poster session, lots of interesting conversations. I enjoyed talking to a subset of the presenters. And thank you for all the presenters again for making time to present in the workshop. So we now proceed to the next part of our workshop, which is a breakout session. So these are essentially mini panels within each breakout session, focusing on a certain theme that we've seen in the posters that were presented during the workshop. So I'm going to open the breakout rooms now, and you should be able to see the breakout rooms on Zoom. But don't yet go to the breakout rooms yet. I'm just going to provide some instructions before we do that. So the idea is that you should be able to join a breakout room using the instructions that you see on the shared slide here. So if you go to your name and then click on more, and you should be able to no, sorry, that was for the poster presenters who have been pre-assigned to one of these breakout rooms. Please add your poster ID to your name. And the way to do that is shown on the top of the slide, right? So you can just rename yourself and append the poster ID to your name. And for everybody else, you're welcome to kind of jump between different breakout sessions if you like. We have 3 breakout sessions, and so feel free to join one of them. and we are going to switch over to the breakout rooms in about 1 minute.
Okay, so I think as participants keep joining in, I can introduce myself. I'm Or Litani, and I'm a research scientist at NVIDIA. And together with Shubham Tulsiani, we'll be your hosts for the next 2 sessions. I think so far we had a pretty great first half. I really enjoyed the invited speakers. We had some amazing poster presenters. The poster session, I hope, gave some feeling of good old days when we could meet in person. One interesting feedback I got was from someone who said they got stuck. It was too crowded for them to see the poster, so they had to wait and go back, come back later. So that's exactly the feeling I remember from conferences. So I'm happy that went through. As Leo asked earlier, the posters will be live still on that link, so feel free to check them out later. Okay, so I think we can kickstart the next session. We have a great lineup of speakers for you, and we're going to start with our co-organizer, Professor Leo Guibas from Stanford. I can't think of a better person to kickstart a session on 3D representations, given all the work that Leo has done in that field and his knowledge. And I think we'll be hearing from him a little bit about the overview of 3D representations. And after Leo's talk, we'll invite our speakers of session 2. Just to remind everything, we then have a third session, so don't go away at the end of session 2, and we'll finish session 3 with a panel discussion moderated by Gordon. So Leo, over to you.
Or thank you very much for the introduction, and on my behalf, as well as a co-organizer, I'd like to thank all the invited speakers and the poster presenters for their participation in this great workshop. I want to make just a few high-level comments about 3D representations for geometry and appearance. I've decided to keep this high level. I will not use slides, I will just speak. The question is how to evaluate representations, and I'm going to borrow a term that first arose in the CAD community. You know, that's a community that for decades struggled with different representations. Shall we use parametric surfaces? Shall we use implicit surfaces? And so they came up with this notion of shape interrogation. What questions about the geometry does a shape representation support? And I think this notion of interrogation, so like what questions can we ask, is a central way to think about representations also. In our setting, typically we have the representation sitting between input and output, right? We have typically some sensor data, maybe an image, or a video, or a point cloud. And we go through some processing through an encoder that maps us into the representation space. And then we go out of that back into something meaningful to us, like a class, or maybe a per point or pixel classification, segmentation, or a reconstruction. This is, of course, a very simplistic view, because in fact, often we have connections that go from the specific layers of the encoder to specific layers of the decoder. So in fact, really, the whole pipeline is more like a set of representation changes. Really, every stage is its own representation, including the input and the output. And we are just changing the representations as we go along. Often, actually, we're interested in just the second half of this pipeline, where we go from a latent vector or a representation point to some meaningful output. That's a generative model. And we think about the representations in that sense, then in addition to asking how do we get data in, how do we get information out, we also have to ask how can we manipulate the representation itself in semantically meaningful ways. maybe the representation is that of a human face. Can we change the hair color? Can we add glasses? How can we do these semantic operations, but directly in the representation? So that's another thing we ask of representations to support manipulation. And clearly, the questions we ask affect the representation that we get. I mean, there's been a lot of work on nerves now. These are representations that are meant to be queried, mostly for creating views, right? I mean, we are shooting rays from a point in space towards the scene, and we want to know the RGB value of the radiance field that we get. This is great for making images, but maybe it's not the best for understanding, say, the surfaces on the scene, and working on them. And so other representations, maybe SDFs are better for that. So we also have to keep in mind the questions we are asking of the representation. Now, the traditional pipeline is you have some set of data, you have a task, and you build a representation that serves that set of data for this specific task. But as we go forward, I think it's interesting to ask about expanding this view of one representation for one task and talk about having one representation for many tasks, or maybe many representations for one task. This is something that in my group we call joint learning. So let me talk a little bit about how this might work. I mean, the reason that it makes sense to combine things is because many tasks are correlated. For example, if we go from an image of a scene to, I don't know, depth and to normals, clearly these are very correlated, and we would also expect that the representations of the depth and the representations of the normal should be strongly correlated. So there should be some simple mapping between them. So some years back in the astronomy work, we explored these kinds of maps between representations that allow us to go from a representation for task A to one for task B. And also in some follow-on work in CVPR last year, we explored the notion of benefiting from making these maps between different representations cycle consistent or path invariant. So for example, going from an image to normals should agree with going from an image to depth and then to normals. This somehow is self-supervision that improves all the representations jointly. But maybe it also makes sense to not have just kind of simple maps between these correlated representations, but maybe a single representation that serves multiple tasks. And one issue that arises here is how to parameterize a collection of tasks. What is a proper way to encode the task space? And if we think about a representation that can be universal for a set of tasks, and given some new task, how can we tell if this task fits into that space that this representation can handle? I don't have answers to these questions, but I think they're good questions to ask. How do we parameterize the task space? Yeah, in fact, I think as we ask more and more of the representations, I think we'll start to see certain things that kind of bring me back to an earlier life, because I started my career working in algorithms and data structures. And data structures is a bit the same. You're going to build something that supports many operations. I mean, the classic is a dictionary. You want to be able to insert, delete, and query. And what you find is something that's been described as the waterbed effect. Back in the 70s, these were popular to sleep on. It's like a mattress, only it's like a plastic thing filled with water. And because water is incompressible, if you press in one place, it pops up in another. So what you find with this data structure is that it's sort of the art of balancing, the art of negotiations, because if you try to make operation A too efficient, operation B becomes inefficient. If you push here, something else pops up. And I think we'll start to see the same effects here in the representations, that somehow if you make it too good for one thing, it will be less good for something else. And I think understanding these trade-offs can be interesting. It can also be interesting to study how multiple representations can be useful for the same task. You might say, so why should that be? And how do we use them together? Well, you can use them together by having some optimization at the very end. It's like, you ask a bunch of experts, they all tell you their opinion, and then you integrate the results. As an example, a few years ago, Ora and others had this work on VoltNet. This is just a way to detect bounding boxes of objects in a point cloud scene. And we had to generate object proposals about the bounding box and summarize the bounding box in a small number of parameters, say a few points. Well, the most obvious point to try to regress is the center point of the box. But, well, there's other options. You could try to regress the center points of the faces of the box. That would give you a different representation. Or regress the midpoints of the edges of the box. Or regress the vertices of the box. So in fact, one of my ex-students, Ying Huang at UT Austin, followed this idea and showed that if you regress all the representations jointly, separately each, and then combine the results in the end, you can do better. And you can do better because depending on the input that you have, one of them may have an easier time detecting the information that it has to support. For example, if you see a typical dining table, so regressing the center point of the bounding box may be difficult for the network because that point is far away from the table surface and sits in empty space. But regressing the midpoints of the edges, or maybe the center of the tabletop, yeah, that's much easier. So I think this notion of having essentially a team of representations that together figure something out can also be interesting to explore. Now, let me move on to the generative side of things, where I think the interest is to be able to manipulate the representation, and of course there we want to sort of disentangle things. For example, if you generate like a human body, there is the body shape and there's the body pose. So ideally, there will be some parameters that describe the pose and some that describe the shape. Only in many cases, this factorization is not fully possible. There are certain poses that dancers and yogis can take that most humans don't have an easy time taking, and some bodies might prevent them from doing that. So how to represent this weakly entangled attribute, I think that's also interesting to explore. And in fact, another aspect that relates to this is the fact that right now we represent things always as points in a Euclidean space, as a high-dimensional point in a Euclidean space. But Euclidean spaces are extremely homogeneous. And a lot of the semantic spaces that we're interested in are much less so. If I think of a space of chairs, okay, I have a chair with arms, a chair without arms. So the vector from one point to the other should mean, this is the semantics of adding arms to the chair. But in a Euclidean space, I can take a vector and translate it anywhere and apply it to any point. But what should it mean to add arms to a chair that already has arms? So the space is not so smooth and not so homogeneous. And how to deal with that? One way might be to enlarge the kinds of mathematical objects that we think as encodings of representations. For example, could graphs be latent spaces that we learn? Another option can be vector spaces. That is, it's not that the latent space is a vector space, but the encoding of a piece of data is a vector space. This is not a new idea. In algebraic topology, it's been practiced for a long, long time, where we encode topological spaces into algebraic objects, like groups and vector spaces, and actually so that the structure of the original space, the topological space, is reflected in the structure of the algebraic object that encodes it. And I think the same thing can be here. If we select a representation space that has some structure in its members, then we can try to make it so that the semantic structure of the data we have is reflected in the algebraic structure of the particular object that we select to represent that physical entity. So anyway, I think these are just some high-level thoughts that I wanted to throw out because I think this is an extremely interesting and central topic for all that we do. And with that, I'll pass the floor back to Or.
Thank you, Leo. This is very thought-provoking, as expected. Thank you for that. I think Shubham, you'll introduce our first speaker.
Yeah. Again, before that, thanks again, Leo, for the reminders about generalization to tasks, and that we must be careful about the structure we impose on representations. And yeah, I think I'm very excited to introduce the next speaker, Dima. Dima is here around. If we can just try sharing your screen, just so we know things are up and running.
Yep.
Yeah, I think this works perfectly well. So yeah, let me just introduce and then we can get started. So yeah, it's a great pleasure to welcome Dima for the first talk in the second session. Dima is a final year PhD student in the Geometric Data Processing Group at MIT, where he's advised by Professor Justin Solomon. He's also an NSF graduate fellow and has done internships at Adobe and Pixar during his PhD. I think his research really very innovatively combines techniques from computer graphics, geometry, and deep learning. And in particular, I think he has done some amazing projects on processing and generating geometric representations like triangle meshes and parametric shapes that aren't really very easily compatible with typical learning pipelines. And yeah, I'm very looking forward to hearing more about these things. Maybe just one logistical thing before you get started is we want maybe the talk to be 30 minutes with 5 minutes for questions. So I'll interrupt you at 25 minutes just to give you a reminder that you have 5 minutes left.
Okay. Cool. All right. Thanks, Shubham, for the intro, and thanks for having me. So like Shubham mentioned, I'm currently in my final year of my PhD working with Justin Solomon at MIT in the Geometric Data Processing Group. And over the course of my PhD, I've really been interested in the intersection of deep learning and computer graphics from the perspective of shape representations that are kind of usable, useful, and necessary. So there are many ways to represent shapes. I think maybe the first one that comes to mind in a deep learning and graphics context is the image, the raster image. And it's no surprise, kind of the convolutional operator, which forms the basis from many, but not all, recent learning architectures, kind of relies on the uniform and regular structure of the pixel grid pretty fundamentally. But images are not the only representations that are out there and the ones that we care about. So you can imagine representing a shape as a collection of some sort of parametric primitives like these Bezier curves that are sparse but expressive and editable. Or as we move into 3D, there's even more options. So you might have point clouds, you might have voxel grids, triangle meshes, or graphs that may be represent the connectivity of the triangle mesh. And all of these representations have their own pros and cons, but I think, unfortunately, some of the ones that are most obviously and intuitively compatible with standard deep learning techniques are oftentimes the ones that we actually care about less, and the ones that are less useful for many of the downstream tasks that are necessary in computer graphics. So while inputting this image or even this voxel grid is a pretty standard thing into a convolutional network, and more recently, we can do a lot of good learning on point clouds and graphs as well. Oftentimes, the representations that we really care about and that we want to either process or produce look more like the things here in the middle. So we might want to have kind of a small set of editable, interpretable parametric objects, or we might have a triangle mesh that we want to learn on. So the question of operating on these types of representations with a deep network is interesting, both kind of from an input and an output perspective. On one hand, we don't want to have to convert our input into some other representation because that involves oftentimes losing information. On the other hand, we don't want to convert our output into our target representation because that can incur a costly and complicated post-processing procedure. So the question that I've been interested in is, how do we design deep learning systems kind of from the shape representation up? how do we design systems of input or output common, useful, and intuitive geometry representations that don't necessarily fit into the typical convolutional architecture. So over the course of the past 4.5 years, I've done a few projects that deal with this broad question. I've looked at triangle meshes, I've looked at sort of parametric shapes, kind of vectorized graphics and sprites. In this talk, I'll focus on the works that kind of have more to do with 3D given the workshop. And I'll also show some very recent results that we just got the other week. It's still in progress, but I think it's pretty exciting stuff on kind of a hybrid implicit-explicit method. So the first thing that I'll talk about is HodgeNet. It's learning spectral geometry on triangle meshes. So this deals with the input side of things. So the task at hand is, how do we take a triangle mesh, input it into a deep network, and learn features? The features that we learn might be a single feature for the entire mesh, say for a classification problem, or it might be a feature per face for a segmentation problem. Now, of course, like I mentioned, we could just sample points from this mesh or convert it into a voxel grid or a graph, but that loses a lot of information. We typically lose topological information, connectivity, and it can make our representation not invariant resolution. So for instance, if we sample, then it might turn out that a dense sampling produces very different features than a sparse sampling, even though the underlying geometry is actually the same. So you want a perspective that allows us to input triangle meshes directly and reason about their underlying surface. And for this, we turn to the field of operator-based geometry processing. The basic question here is, what can we learn about shape from its vibration frequencies and oscillation patterns? In other words, if we gently tap the shape and listen to the sound that it makes, what can we actually tell about the shape? And the answer to this question often lies in the Laplacian operator and its eigenstructure. So what a lot of approaches here do is they compute the Laplacian on the mesh and compute its eigenvalues and eigenfunctions. And looking at the eigenfunctions corresponding to the smallest eigenvalues, these are the ones that, of course, that convey the low frequency information. We see that a lot of kind of interesting structure comes out. In particular for this HodgeNet work, we take inspiration from this paper by Lipman and Wetzstein from 2014, where they define a class of shape descriptors based on Laplacian eigenstructure. In particular, they define a shape descriptor at every point of a mesh by summing over the lower order eigenpairs, taking some function of the eigenvalue and multiplying it by the eigenvalue. Eigenvector. It turns out that depending on the choice of f, we can recover common descriptors from geometry processing, like the heat kernel signature or the wave kernel signature. And in this paper, they propose to learn f using a neural network based on the task and the data. In HodgeNet, we decided to go kind of a step further. And in addition to learning the f, we also want to learn the operator. We want to learn a Laplacian that is custom suited for the task at hand. Now, in order to learn an operator using a neural network, we need some way to parameterize it. For this, we turn to Hodge theory and the Hodge Laplacian. And basically what this says is that we can write down the Laplacian as this product of these Hodge star and differential D operators that operate on differential forms. And the gist here is that the D are combinatorial, so they only care about mesh topology and structure. So they're kind of fixed for a mesh independent of the geometry. And the star only depend on local geometry of the mesh. But then computing the Laplacian and computing its eigenfunctions, we can get something global about the mesh structure, which is exactly what we want. So how do we learn Hodge Laplacian? Well, we can learn the star 0 matrix as features per vertex. We can learn star 1 as features per edge, and the D is just computed directly from the mesh topology. So as an overview of our system, we start with some sort of triangle mesh. We learn these per vertex star 0 features just from input vertex positions and normals. We similarly learn per edge features based on positions of incident faces. We get this sparse combinatorial D matrix out, and we use them to write down an operator. So now we kind of have an operator that's parameterized by learned features. Now that we have this operator, we can compute its eigen decomposition. And following the recipe from Lipman and Bronstein, we can take a function of its eigenvalues and eigenvectors to get out features, which we can do more learning on depending on the task at hand. Now this forward procedure is relatively simple, but in order to train this, with gradient descent as a neural network, we need to go backwards and backpropagate. And this is a little bit tricky, in particular in this step here, in the part of backpropagating through the eigen decomposition. And the reason for this is because if we do this using sort of standard GPU-based deep learning libraries, this will require us to compute the eigen decomposition of a large dense matrix, because our operator, the size of the operator comes from the number of vertices in our mesh, which for any reasonable mesh is quite large for a GPU. So this becomes a bottleneck. But note that this matrix actually isn't dense. It's a sparse matrix whose sparsity pattern has to do with the combinatorics of the graph. And we don't care about the full spectrum. We only want the lower order eigenvalues, because those are the ones with interesting, that communicate interesting features. So our question becomes, how do we differentiate a map from sparse matrix entries to low order eigenstructure without having to compute the full spectrum, which is prohibitively expensive? It turns out that we can do this, and we can implement this in practice using sort of standard sparse linear algebra solvers. Now, unfortunately, sparse linear algebra solvers are in their very early stages in the GPU and are mostly implemented on CPU. And so because of this, we actually take our entire learning pipeline onto CPU, which may sound kind of blasphemous in the day of modern deep learning when we have many, many GPUs. But it turns out that although, of course, each iteration is considerably slower than a typical deep learning iteration, the overall wall clock time to convergence is comparable to state-of-the-art methods because of the information flow. So it's kind of interesting how using insight from typical geometry processing pipelines allows us to make a very atypical choice, but still have decent performance. So first, to show that we learned something interesting with this operator, we do kind of a toy example stress test, which is dihedral angle prediction. We have a data set just of rectangles with a crease down the center, and our goal is to learn from the mesh the dihedral angle. And the point here is that if we were to use a standard Laplacian, this would be impossible, because the Laplacian is only aware of intrinsic features, whereas the dihedral angle is an extrinsic feature. But with our network, we're able to learn this almost perfectly, which kind of shows that something sensible is happening with the operator that we're learning. We evaluate on the standard mesh segmentation data sets. So here we have our chairs, aliens, and basis. And we evaluate on the decimated human body data set, which is typical in these deep learning mesh segmentation works. But kind of interestingly, it turns out that our method is able to scale to the full resolution human body data set, which is an order of magnitude more dense than the standard decimated one. And this is actually due to two things, I think. This is due to the fact that because we do things on CPU with these sparse solvers, although they're slower, they scale better to large meshes. And because our spectral decomposition is aware of kind of a global structure that's independent of mesh combinatorics, we're able to take advantage of some pre-training and use these invariant features. So here we showed how kind of thinking carefully about the shape representation and taking inspiration from geometry processing can make for better learning on meshes. Now I'll focus on some of my other works where the goal is to output interesting, useful, but non-standard geometry representations using deep learning. So the first work is this deep parametric shape predictions using distance fields. And the overall task here is kind of is abstraction using parametric shapes. So the input is some sort of simple representation like a raster image, and the output is an approximation of the input using kind of a sparse set of parametrized primitives. So in 2D, these might be Bezier curves parametrized by control points. In 3D, these might be things like cuboids or other simple volumetric primitives. Now note this is a self-supervised task. We don't have strict supervision, so we don't know which curves correspond to the boundary or which cuboids correspond to the volume. All we have is the geometry, and we want to fit the target primitives in an unsupervised way. So kind of a standard approach to do this is by optimizing chamfer distance. Chamfer distance is pretty simple. All that it means is you sample points from one shape and the other, and then you compute the smallest distance from one point cloud to the other, vice versa, and then you optimize this distance. If the distance is 0, that means the point clouds are the same, and probably your original geometry is also similar. It turns out that there are some issues with chamfer distance that arise from this sampling procedure. In particular, in our case, where we want to predict Bezier curves, it's actually not very easy, and especially in differentiable kind of learning setup, to sample uniformly from our curves. If we sample in uniform space, we end up oversampling around areas of high curvature, undersampling around areas of low curvature, which gives us an undesired bias in the chamfer distance. Another issue is that chamfer distance on its own has no notion of alignment. So if we have these two sets of lines that are almost orthogonal, we sample from them, and according to chamfer distance, the geometry is very similar, which is not what we want. So in order to solve these issues, we propose to think about chamfer distance kind of in a variational sense and cast it as an expectation, which allows us to define a variational notion of chamfer distance. And it motivates a framework of loss functions based on the distance fields. So now, instead of dealing with the geometry directly and sampling from it, we can compute a distance field to the geometry and evaluate our loss functions on this distance field. We write down several loss functions using this framework. So we write down surface loss, which is kind of an analog to chamfer distance. And whereas before we had the sampling issue, we now are able to evaluate it in terms of a grid, which is uniform and regular, and we no longer have the sampling issue. And I want to point out that the grid resolution is not a bottleneck for representation here, because note that each grid cell contains the distance to our geometry, and therefore it can compute kind of sub-voxel level distances. So it's just a way of computing quadrature, but not a bottleneck of not a discretization of the representation. And then similarly, we have this alignment loss, which, whereas before we had this issue, now we're able to kind of propagate normals to every point in the ambient space, which makes things align well. So this is kind of what our pipeline looks like. Like I said, the input is something simple like an image or distance field. We encode it using a standard ResNet, and we get out explicit parameters for each either Bezier curve in 2D or 3D primitive. Now that we have these primitives, we can compute a distance field to them in closed form analytically differentiably as part of our end-to-end pipeline. And now we can evaluate these distance field-based losses on this intermediate representation. So here are some results in 2D. The goal is to predict the boundary of fonts. And when the fonts are simple, we recover a pretty good vectorization. But I think more interestingly, when the fonts are kind of decorative and high frequency, we're able to distill the overall geometry of the boundary without kind of ignoring the filigree and letting us compare the coarse geometry. And because these primitives are consistent across different inputs, this motivates sort of fun applications, like we can do nearest neighbor retrieval in curve space, which lets us find similar fonts based on kind of coarse geometric quality. It lets us interpolate between font glyphs or do this kind of style structure deformation mixing. Now in 3D, we're able to also approximate shapes using these cuboids and these random cuboids. And you can see here, compared to this prior work from Shubham and others, which uses kind of vanilla chamfer distance, we're able to get a bit more details out because of kind of these distance fields as an intermediate representation. And then the last thing that this enables kind of nicely is CSG operations. A lot of CSG operations translate very nicely to distance fields. Like we can easily do union and intersection just by operating in the distance fields. So we kind of show how this might be used to learn CSG decompositions in an unsupervised way. So the next work that I'll talk about is learning manifold patch-based representations of man-made shapes. And this aims to address actually a pretty similar problem. We also want to learn 3D parametric models, but the primitives we use here are more expressive than just simple cuboids. So the representation we want here is a parametric patch-based representation of manifold 3D geometry that is piecewise smooth, that is sparse, interpretable, editable, and amenable to deep learning. So the reason we might want this kind of is inspired by CAD workflows and representations. So kind of a sample workflow that is facilitated by our system is, say we take this input sketch of a car, we can input it into our network and get out this 3D model that is that is a realization of this car in 3D made out of these patches. And then because of this patch-based representation, we can import it into standard CAD software and kind of make edits intuitively, which would be a lot harder with something like a voxel grid or even a mesh. So our primitive here is this parametric Coons patch. It's kind of like a tensor product patch. The idea is that it's parametrized by the boundary curves, so 4 Bezier curves that meet at the corner points, and it's interpolated bilinearly in the interior. And then we represent shapes as deformations of a template of these kinds of patches. So you see here, so the template provides kind of hard topological constraints. It tells us where the patches attach to one another, and it provides a very rough initialization of the geometry. Now, the way we obtain these templates is automatically. We look at a collection of shapes. We sort of take an intermediate model. We fit cuboids to it. We subdivide it to form a quad mesh, and then we simplify to get a template. But the point here is that it's not very sensitive to how the template looks like, as long as it kind of has some general geometry similar to the shape category. So these are the templates for each shape category that we have. You can see that it doesn't convey a whole lot of detail, but poses a nice initialization. We also show results on generic sphere templates that have no knowledge of the geometry. So the main question here is similar to the one with the previous work, which is how do we optimize the distance from these patches to our target geometry? And once again, applying shame per distance in a naive way doesn't work. If we sample uniformly in the parameter domain, we again get non-uniform sampling on the patch. And whereas before we dealt with this by computing distance fields to our primitives, in terms of these patches, this is quite difficult to do. It's not clear how to differentiably and efficiently compute a nearest distance to this Coons patch. So we need kind of a different solution. And what we do is we again formulate shame per distance as a surface integral in a continuous setting. And now we just do a change of variables. We basically pull back the integral and do it over the parameter domain, which is a square, instead of over the surface. This introduces this Jacobian term to account for the distortion, but because our patches are analytically defined, we can actually compute the Jacobian in closed form and just evaluate it as we're evaluating our loss function. So this kind of solves the sampling issue in a different way than computing a distance field. So here's what our pipeline looks like. It's not too different from the previous one. We ingest an image using a simple encoder. We output directly parameters for the control points of our patches. And then we have a number of losses and regularizers, most of which rely on this idea of pulling back the integral, the surface integral, to the parameter domain, and therefore not having to worry about non-uniform sampling. We generate our training data automatically. We take 3D models, we render their contours, kind of do some data augmentation and make them look like pencil sketches to make it compatible with human drawn sketches. And this is what some of our results look like. So for each input here, we show 2 models. The top one is using that sphere template that has no notion of geometry as in the initialization. And the bottom one is using a category specific template. And you can see that kind of both of them are manifold meshes composed of a small number of patches that have a good amount of detail, but of course the bottom ones have slightly nicer patch placement due to initialization. Here's some more results. And so you can think of this actually as kind of an automatic conversion of an input mesh or geometry into NURBS patches. And this is actually a pretty open problem in CAD. If you plug it into a standard CAD software like Rhino, it's not able to decompose the surface into sensible NURBS patches. It creates tens of thousands of very tiny elements. Whereas ours is, of course, not as faithful to the initial geometry, but is able to predict a very sparse decomposition that's more usable in something like a standard CAD pipeline. And moreover, our representations are consistent. So kind of the same patch that gets mapped to the nose of an airplane does so in all the different examples. And as before, we can kind of interpolate both in patch parameter space. So we can interpolate directly on control points, or we can interpolate in a latent space. And these two are actually not that different, which kind of shows that our representation is a reasonable way to represent this geometry, because the learned latent space follows the same structure as this final representation that we get. So finally, I'll talk about this very recent work that we just started a couple of months ago, and literally last week started to see interesting results. But the idea here is...
Just a heads up that about 5 minutes are left. Thanks.
Perfect. So the idea is we want to learn implicit shape representations with boundaries. So this is kind of a new hybrid representation that we thought of. So shape representations kind of typically fall into one of two categories. So the Lagrangian representation is explicit, like a triangle mesh. And it's limited in topology, but not in resolution. Whereas an Eulerian representation, you can think of as, for instance, a voxel grid or an implicit function discretized on a grid. It's limited in resolution, but it can afford any topology. More recently, as I'm sure many know, neural implicit representations have become very popular. And the idea here is to represent geometry as a level set of a neural network. And the nice thing here is the neural network can focus more on high frequency regions near the surface without wasting resolution, but at the same time, there's no fixed topology. Now, these neural implicit representations have come a long way in the past couple of years. And for instance, representing a shape like this human body at this point is no problem for a neural shape representation. But notably, almost all existing neural implicit representations represent closed surfaces due to the fact that they're taking level sets of some field, which is convenient, but oftentimes we actually want surfaces with boundary. Even in this case, if we think about the segmentation of the human, it might make sense to model each segment individually. And now you have all these boundaries that current methods can't really handle. So we want to think of a method we want to create a neural implicit representation that is able to obey some sort of boundary. And for this, we take a look at geometric measure theory. And geometric measure theory, one of the questions it aims to answer is the minimal surface problem, which is how do we compute a surface of minimal area that obeys some boundary? And to do this, without going into too much details, the geometric measure theory proposes using currents. And currents can be kind of thought as delta measures over one forms. So kind of like a delta measure is a limit of a function. Currents are delta one forms over surfaces. And basically the idea is that the minimal surface problem can translate entirely into a minimal mass problem, where instead of computing the area, we can compute this mass norm over a surface. And instead of, and the boundary constraint turns into this constraint here, which just means that we can represent our current as the gradient field of some function plus some alpha, which is a BO sub R field. The takeaway here is that this is a hybrid representation. The alpha is what makes our surface obey the boundary, and it's computed explicitly from an explicit boundary representation. But the interior of our surface is dictated by this learned F. So let me show you what this means. So in practice, our network goes from some point in R3, projected onto random Fourier features, and goes through a standard kind of floating architecture to get out a single scalar value. And then we minimize this mass norm over the gradient field of our learned function plus alpha, which is defined by the boundary that we want. So in 2D, say we want this boundary, we compute this alpha using just the equation to the Biot-Savart field. And then after optimizing our network, we get something that looks like this, and the magnitude looks like this. So we are able to recover the minimal surface, which is just a line segment. In 3D, we can start with just a ring, a circle. And after doing the same optimization problem, we learn this flat disk that respects the boundary and is the minimal surface. If we do kind of these two intersecting rings, we get this interesting kind of soap film surface that's also the minimal surface. So now we kind of have a way of learning minimal surfaces with networks that obey a boundary, but how do we use this to reconstruct from data? So say we want to reconstruct this head with this boundary. If we plug this into our kind of, into the system that I just described, it learns this thing. So it basically learns a disk, which is the minimal surface. So how do we actually get the head out of it? Well, without going into detail, if we change the metric from the Euclidean metric to a metric determined by the data, we can actually make it produce the head, because in this new metric, the head turns out to be the minimal surface. And so we can do this with any of the segments shown before to get these kinds of reconstructions. So notably, all of these surfaces are by construction forced to respect the explicit boundaries, but the interiors can be learned from data. And we can think of this as kind of maybe a generalization of the patches that I showed before, where the boundary is determined explicitly, but then the details can be filled in with a learned network. So kind of to wrap things up, sorry, my computer froze. To wrap things up, there are many common shape representations that are popular, common, and necessary for downstream tasks, but are not really obviously compatible with the deep learning approaches. But by putting the geometry first and making deep learning work for geometry rather than the other way around, we can actually craft learning algorithms that are tailored to the specifics of the geometric data that we care about. And there's a variety of next steps that we can consider here. I think a big open problem is topological challenges. It's unclear how to communicate sort of discrete topological changes in this context. There's other 3D modalities like sculpting CAD. We can think about higher dimensional spaces like volumetric representations. And then of course, we can look at other geometry processing tasks like surface flows, parametrization, and so on. So that's it. I guess I'm short on time, but I'm happy to take any questions, and feel free to reach out if you want to chat about anything.
Yeah, thanks, Dima, for a great talk. And particularly the results and visuals are amazing to see. I think we have time for maybe a couple of quick questions. I'll start with one that Or had about the first work that you talked about. And the question is, can you train the operator to be less sensitive to the partiality? So I assume he's talking of settings where you don't have the full mesh, or there's maybe some aspects missing. And could your operator maybe handle that setting?
Yeah, that's a good question. I think so. I guess so. One possible caveat that actually is okay is that we do handle shapes with boundaries, so we kind of have a way to allow the operator to work separately in the boundaries. So that part is fine. So I think as long as kind of the task at hand and the loss function it elicits that sort of bias, I think that's a reasonable thing to try. Yeah.
And actually, the other question is maybe something I sometimes wonder about, which is in the middle two projects, there were these parametric decompositions. And I'm curious on your thoughts on what makes for a good parametric decomposition versus a bad parametric decomposition.
Right, that's definitely a good question, and it's what makes kind of quantitative evaluations and these things pretty tricky. I think I like what Leo said in his introduction, that I think we should look towards kind of CAD literature and expertise for this sort of thing. It seems like we want something that affords us a lot of expressivity, but also is easy to work with and edit and sparse. So I guess I don't have a strict quantitative answer, but I think the goal is to make things that are actually usable for people who want to build such representations.
Okay, yeah, thanks. That's a good perspective. So yeah, we should thank the speaker again, and I think Or will introduce the next speaker, Shuran.
Thanks, Shubham, and thanks Dima again for a great talk. Really enjoyed it. And by the way, for the participants, please feel free to keep posting questions for speakers. If they still hang around, they can answer them in the chat. It's my pleasure to introduce our next speaker, Shuran Song. So just on a personal note, I remember attending, I think it was ICCV 2014, and seeing Shuran's talk. Maybe while I talk, Shuran, can you please just share your screen with the slides so we can see that it works? Okay, we can see your screen and your slides. Perfect, looks great. So I think it was ICCV 2014, correct me if I'm wrong, where you presented the sliding shapes. This was truly inspiring because we were just the emergence of incorporating 3D deep learning or deep learning into 3D scene understanding. And I think this kind of opened up so much cool research. And I also feel like you're almost like the perfect speaker for this workshop, because you've crossed the boundary from just doing 3D scene understanding into actually using it for robotics applications. So I think this is we'll be hearing about that. But you're not just in either camp, but you actually crossed between them. So that's great. So to more formal bio, Shuran is an assistant professor in the computer science department at Columbia University. And that's where she directs the Columbia Artificial Intelligence and Robotics Lab. Her research focuses on computer vision and robotics, and in particular, developing algorithms that enable intelligent systems to learn from their interactions with the physical world and autonomously acquire the perception and manipulation skills necessary to execute complex tasks and assist people. And without further ado, Shuran, to you.
Thank you.
In 25-minute mark, I'll kind of give you a short notice, and then you'll have 5 minutes more, and then 5 minutes for questions.
Okay, sounds good. Thank you so much for the introduction and also such a nice workshop. I just dropped in like half an hour ago, and I feel that the talk before me is actually very inspiring, and I think it's going to be really helpful and useful for like my research as well, because like very soon you'll see that we're going to represent geometries with boundaries because we are dealing with class and deformable objects. So yeah, so today I'm going to talk about how we can learn 3D visual representation for deformable objects. And in particular, we will focus on one specific subset of deformable objects, which is cloths and garments. Okay, so as we know, garments and cloths is probably like one of the most common type of objects in our daily life, but they have like a set of very unique properties that makes them incredibly hard for machines to really perceive and interact. And today I will probably start my talk by first describing those properties and why they make deformable like cloths perception particularly hard. So first is their high degree of freedoms. So unlike rigid objects where their pose or configuration can be easily specified with just a few numbers, right? For rigid objects, just 6 numbers. A piece of garment can easily has a near infinite degree of freedoms. And how to efficiently represent and infer their full configuration is the first challenge we need to deal with when we're considering handling garments. And the second is about their 3D geometries. So for objects like cloth and garments, they often consist of very thin 3D structures that are not watertight. In another word, it has holes or it has boundaries. And as we just see in the earlier talk, this kind of unique geometric property makes them ill-suited for typical 3D shape representations designed for solid rigid objects like occupancy grid or sign distance functions. Therefore, that really requires us to think about new shape representations to represent objects like cloth. And finally, because cloths are so thin and they can deform in so many different ways, they often also experience the most extreme case of self-occlusion. right? So for example, the ratios between the observed and the observed surface compared to the full surface of a piece of garment can be as little as 10%, especially when they are crumpled together or like folded up, which makes the perception task extremely difficult if we want to handle those cases when they are heavily self-occluded. So due to all these challenges, prior works on garment or cloth perception often build on top of several simplifying assumptions, right? So for example, they will assume high visibility of the cloth by only considering the scenarios where the cloth is already worn by a person. So the self-occlusion is pretty much minimized. And or they can rely on very strong prior knowledge about objects, such as very known accurate instance level 3D mesh, or like a full state information in the first frame, and therefore the post-estimation task is reduced to a simple tracking task in the following frames. So in today's talk or in this project that I am going to talk about, what we want to do is to try to relax some of those assumptions and then try to answer the question of how to estimate the pose of a piece of garment from a highly incomplete partial visual observation. And the work in particular I'm going to talk about is called Garment Net, which is done by my student Cheng Chi, and this paper is just presented in this ICCV conference. Okay, so the goal for this project is to do pose estimation for garments, right? So, but the first question that we should ask before we even start this project is how we should even define the pose given a piece of garment. So for rigid objects, the definition is very clear. Given object instances, the pose is fully described by 3 degree of freedoms, which is 3 degree of freedom of translation and another 3 describing the rotation. And then in order to extend this definition for a collection of object instances that belongs to the same category, we can define a shared category level canonical pose. So for example, here is an example of cameras. We can use the direction of the lens in order to align different object instances in order to get a canonical definition of their pose. And then the task of category level pose estimation is defined by inferring the correspondence transformation between the observed objects to this canonical pose. And many of you probably are very familiar with this representation. It's called NOX, which stands for Normalized Object Coordinate Space. And a similar idea can also be extended for articulate objects, just with a few additional degree of freedoms describing the object's joint parameters. But how about for deformable objects like t-shirts, right? How are we gonna define their pose? Are we going to kind of specify the position of every single vertex on the cloth? Well, the short answer is actually yes. And since the garment has such a high degree of freedom, in order to fully specify its configuration or pose, we kind of need to specify every point location on the t-shirt surface. And even more, we need to also specify the position for both observed and unobserved surfaces as well. Since we no longer have the rigid body constraints, we can not directly solve the pose for those unobserved points using algorithms like RANSAC. So obviously, it is a lot for the network to infer. However, since all the degree of freedoms are not completely independent, there are very strong constraints or priors the algorithm could leverage in order to simplify the problem. So the key question we need to answer here is then how we could impose those constraints or prior knowledge during this inference. And again, we borrow the similar idea that we can define a category level canonical space for different garment categories. So this time, this canonical space is defined across different garment instances under a similar configuration. So here the configuration is defined by the garment geometry worn by a person in a T-pose. And as a result, this shared canonical space will allow the algorithm to learn a strong priors within each garment category that is independent from their configurations or their own geometry. And the one way to understand this canonical space is that given a coordinate in this canonical space, it will map to a similar surface location on different garment instances, which means that they are very likely to share similar local geometry or semantic meanings. So for example, here, all the 3D points on the shoulder should have a similar coordinate label in this canonical space. And in the later slides, you'll frequently see visualizations like this, where the RGB color on the mesh will corresponding to its XYZ location in the canonical space. Okay, so in total in this project, we consider 6 garment categories provided by the class 3D dataset. And with this post definition, now we can finally define the task. So given a partial observation of an unseen garment, the goal of the algorithm is to map all the observed points into a category level canonical space. But how about for the unobserved surface? Remember, since that we no longer have the rigid body constraints, we no longer can directly solve those positions by using RANSAC. So instead, what we do is to ask the network to complete the garment's full 3D geometry in this canonical space, and therefore provides the post estimation for those unobserved surfaces as well. So finally, we'll need to map the completed shape back to the original observed space so that the output can directly describe the garment's input configuration. So to summarize, the key idea for this project is to really formulate the deformable object post estimation task as a shape completion task in the canonical space. And by mapping the observed points into the canonical space, we can estimate the pose for all the observed points. And then by completing the shape in this canonical space, we can estimate the pose for all the unobserved surface as well. And since the shape completion happens in this category level canonical space, the algorithm can leverage a much stronger shape prior that is invariant to object configuration. So that is the high-level idea for this project. And in the next few slides, I will just go over a few most important design decisions for this algorithm. So first is how we can get the input observation. So in this project, we are less interested about the task of unbodied class perception, where the class is already worn by a person. So instead, we are kind of more interested in the garment post estimation under arbitrary configurations. However, the problem is that if we do not post any constraints on the garment's configuration, the task can quickly become way too hard and in some cases, even impossible to solve. So instead, what we'll do is we will use a simple robot action or like interaction to transform the class from any arbitrary configuration into a configuration that is more trackable for the perception system. So what we do is to ask the robot to randomly pick up the garment from any location it can. So by using this very simple pickup action, the system is able to reveal more surface area on the garment by leveraging the gravity force. Basically, put on the garment, therefore you can observe more surfaces on the garment geometry. And at the same time, this kind of pickup action itself is very simple, and it does not rely on any prior knowledge about the class or its pose. Therefore, it has a very high success rate, which basically means that we can always assume that it's going to be successful. And then after that, the algorithm will label all the visible surface with their canonical coordinates using a typical pointer++ network architecture. And also in this step, we can propagate the grasping point to the canonical space by using the predicted Knox label. Right? So because we're predicting the Knox label for all the points, and we also know where the robot actually grasps this garment, therefore we can directly map this grasping point in the canonical space as well. Okay, and then after we kind of map the observation, all the observed points into this kind of canonical space, the next step is to complete the shape in this canonical space in order to provide the Knox labels for all the unobserved surface as well. So the task of shape completion, especially for rigid objects, is a very well studied problem with many existing algorithms. However, for garments or cloth, because of their thin 3D structure, it is actually a little bit tricky to select the right 3D shape representations so that for the network to do the job effectively. So for example, occupancy grid is obviously not a good choice for representing thin surfaces since its accuracy will directly limited by the voxel resolution. On the other hand, using sun distance function, we are able to represent much more accurate thin structure by using the zero crossing surface. However, sun distance function can only kind of describe the watertight surface with no holes or no boundaries, which means that if we directly extract out the zero crossing surface, we'll get additional surface around those garment openings, such as their necks or waist. So to address this issue, we use a different, slightly not standard shape representation called generalized bending number field that allows to represent thin surfaces with openings. So what is a bending number field? So bending number field at any given point is actually, and also a given 3D mesh or 3D surface is defined by the signed length of the projection of a curve onto the unit circle. So the final value is normalized by 2 pi. Therefore, the end value is ranged from 0 to 1. So intuitively, if you try to understand it, for a point that is inside a closed surface, the bending number field is always equal to 1. And for a point that outside the curve, the projected bending number field is always equal to 0. And if we compute the bending number for all the locations in the space, we'll get a bending number field. And we can also extend this definition to 3D by replacing the 2D angle with solid angle in 3D. So the next question is why we use bending number field, right? So what are the special properties make it desirable for our application? So actually, if our surface is watertight, then the value is constant 0 inside the surface and 0 outside, which is basically the same as occupancy gauge, which is not that exciting. However, when the surface has openings, the things will become more interesting. So for those surfaces, we can observe a smooth transition from the inside positive value to the outside negative value on the opening area. And in fact, this function is smooth everywhere except the discontinuity on the surface. So therefore, by detecting the gradient on the bending number field, we can find the surface. And by using the magnitude on the gradient, we can distinguish the difference between the surface area and the opening area. So here is an example of the bending number field and its corresponding gradient magnitude. Okay, yes, it's clean. And we can see that the gradient is much stronger around the surface and in comparison to the openings. And by thresholding on this magnitude, we are able to separate the surface from the openings. Okay, so here are some example results for the shape completion steps. So on the left is the canonical coordinate prediction on the top left, and the ground truth surface on the bottom left. And on the right, we shows all the shape completion results by using different shape representations. And what we can see here is that with bending number field, the algorithm is able to predict very thin surfaces with the correct openings. Okay, so in the last step, what we need to do is to map the completed shape from the canonical space back to the observation space, so that eventually the output representation is able to describe the full configuration of the garment in the original task space. And in this final output, it will describe the configuration for both observed surface and also occluded surfaces. Okay, so for this last step, there's actually two possible approaches for this step. So let's see. So the first approach is to use physics simulation, where we can use the predicted grasping points from the first step and the completed 3D mesh in the second step, and then we can simulate how this class will fall under gravity force, and then therefore map it from the original canonical space to the task space. So the advantage for this approach is that it will always predict a result that looks physically plausible because it's basically running a physics simulation on a complete mesh. However, the downside of this approach is that it is also very sensitive to any errors that can happen in the earlier steps, such as incorrect grasping point prediction or invalid mesh reconstruction. So if any of those period steps make any mistake, this physics simulation will just simulate on those wrong predictions. And another approach is to try to directly predict the transformation or the warp fields as another implicit function. So basically for each of the points on the 3D mesh, will predict the warp field mapping from the canonical space to the original task observation space. So although this kind of predicted warp fields may not always guarantee to be physically plausible, the network gains some additional robustness against the prediction errors happened in the early step. So in our paper, we actually implement and compared both approach and also shows their pros and cons. So here are some example results. So in both examples, actually the Knox prediction for the grasping points, as you can see, is actually mirrored. So for example, in the first row, the ground truth grasping point is supposed to be on the right sleeve, but it's predicted on the left sleeve. So in this case, the simulation-based approach will infer a wrong pose based on the mirrored grasping point prediction. However, the warp field prediction is able to self-correct this kind of error and predict the correct pose. So now we can put everything together to form this kind of end-to-end framework for garment nets, which consists of 3 major steps. So first is map the input point cloud to a canonical space. And then we complete the 3D shape in this canonical space. And the third step, the final step, is to warp back the complete shape back to the input observation space. So the output representation will describe the garment's full configuration using completed 3D mesh with per vertex coordinate label, where the label is basically where it should be in the canonical space. So now I'm going to quickly show you some of the results from garment nets. So here is the results of a dress. On the top row we show the predictions for each step, and in the bottom row we show the ground truth 3D geometries. And here is the result for skirt. And top. So in this case, you can see that the algorithm still have some issues or struggles when predicting the straps on the shoulder because it's just very thin structure that the algorithm still has issues predicting, or maybe we didn't select the best threshold. Okay, so we also test our algorithm with some real-world RGBD data. So in this case, we test with a real-world cloth captured with an RGBD camera, and the cloth is grasped by a robot. And here are more results testing on real-world RGBD data. In the bottom, you can find the project webpage link that's we provide additional results and visualizations on our project webpage. And before we wrap up, I also want to mention that there's one very obvious and biggest limitations for the current system is its very strong reliance on simulated data for training. Since the algorithm needs this kind of dense correspondence of Knox labels as supervision, it's going to be really hard to directly train such a network with real-world data, which is what really prevented from achieving better real-world performance. And I think one of the promising direction to really address this issue is to use robust active interaction in order to help us to automatically collect training data or like kind of ground truth labels. Right. So in this project, we actually kind of already use some similar ideas. Basically, we use a very simple robot actions like pick up the class in the step 0 in order to increase the class visibility and reduce the difficulty for the perception task. And if we want to take this idea one step further, in another parallel project, we also show that it is actually not that hard to learn an effective interaction policy for the robot to actually fully unfold a piece of garment using dynamic actions like fling. So through interaction like this, what the system can achieve is that it can always reset the class state into a canonical state that is fully unfold. And then from this state, if the robot chooses to pick up the class again, then we can automatically compute the Knox labels for that pick point location, which we can use that as a weak supervision signal to fine-tune the model in real world. So I think this is a very promising next steps to improve the system's performance in real world. And then to quickly summarize the project, I will go back to the three challenges that for class procession that I talked about in the beginning of my talk. And I will try to summarize how GovernmentNet is able to designed to address each of them. So first, in order to handle government's near infinite degree of freedom, we introduced a normalized canonical space and use it to define the canonical pose for different categories of garments, where this representation allows the algorithm to learn meaningful correspondence between garment instances that where they have may have different styles, shapes, or configuration. Therefore, also enables category level generalization. And then in order to handle garments' severe self-occlusion, the algorithm explicitly performed shape completion under garment's canonical configuration, which allows the algorithm to fully specify the garment's pose and the geometry for both observed and unobserved surfaces. And finally, to accurately represent garments' thin 3D geometry, we propose to use bending number fields as a shape representation, which we show that achieves much better performance compared to standard representations such as sand distance fields or occupancy grids. And I think this representation can also be potentially very useful for other objects or applications that requires to represent thin 3D geometries. And that's the end of my talk. And I think I have time to take questions. Thank you.
Yes, we certainly have to. Thank you for a wonderful talk, Shuran. This was really, really great. And as I set the expectations, indeed, you showed how 3D representations that we all work on can actually be used in real life and robotics. So this is really wonderful. So everyone, please post your questions to Shuran on the chat. And while you're doing that, there's already one question from Srinath. So Srinath is asking the following, saying texture on clothing could repeat or generally be less salient than object. Is it harder to learn this mapping to knocks for clothing compared to objects?
Yes, definitely. I think the first step for mapping the observed points into the Knox prediction was a canonical space is actually the hardest part of the whole pipeline and also has the highest error. And apart from like the class is textureless and also it has symmetries, right? So it has all these issues that makes the first step really hard. But what we found out is that the algorithm is actually relatively robust to certain errors in the first step because of the shape completion step. And as you can imagine, for garments, because they're designed to like cover like our body, so that they actually has very typical shapes for different categories. So the shape completion step really like save a lot of mistakes from the first step and actually produce like reasonable result in the end. So yes, the short answer is that yes, that's really hard, but it kind of gets solved by the second step of shape completion.
Interesting. So the completion is not following the predicted. So the predicted points are not remaining intact while the others are completed, but instead you also correct for those predicted points as well as complete for the others.
Yeah, exactly. So basically we predict the Knox coordinate and we will propagate the information to this kind of grid representation, like also like using the features and also the whatever information that's carried in the original observation to this canonical space. And the shape completion can choose to trust it or correct it in the second step.
Got it. Maybe a quick question. So you introduced like this really interesting WNF, the winding number field. I'm curious about that because that in itself could be disentangled from the entire work, right, as its own kind of contribution. And I wonder, are there any downsides to using that? I mean, you showed great examples where how it's great for representing open surfaces. But when compared to watertight meshes, am I going to lose anything by using that representation?
Yeah, so first of all, I want to say that we didn't invent this wonderful representation. It's actually already used in graphics community for a very long time, and also even physics and other fields. And we just found that it's actually particularly suited to represent thin structures with openings or like with boundaries. I think that's a better way to say it. Yeah, so your question is there any downsides? So if we are really trying to represent, for example, a rigid object. As I said, it's not, if you just directly apply winding number fields, it's not too much different compared to occupancy grid. So you won't gain any benefits by using winding number fields. It's only when you have like a 3D geometry with boundaries, then you see the benefit of using this representation. Yeah.
That's great. We have a question from Shubham, who's asking one question: how much variation across shapes can the canonical space handle? For example, can blazers and t-shirts be handled together?
Yeah, I have exactly the answer for that. Yes, it is, and you can see some of the results. So if you have like shirt sets with openings, like long sleeve, short sleeve, it's all handled with one category called like tops, I think. Yeah, but as I said, I feel like for garments, although there are variations, but because they are trying to like cover our bodies, the variation is actually not that severe compared to rigid objects, right? So for example, for chairs, you can easily find chairs with like 1 leg, 3 leg, 4 leg, but you almost never see t-shirts with like 1 sleeve or 2 sleeve, like it's always 2 sleeve. So I would say that we also like benefit from those kind of strong parts in terms of category level. Yeah,
that's really great. I wonder also about the definition of a canonical pose, because I really like that you took your definition of a canonical pose was how would that garment look on a T-posed person, but still I can imagine some clothing, still this is not sufficient to define them in a one-to-one sense, right? So like if I wear a hoodie, right, this thing can go either, can still have many variations, right?
Yeah, exactly. I think for like we didn't really think like too deep, like how we should define this canonical pose. I think we cannot choose this because the data come with this canonical pose, and it is defined in this way. And I think indeed for some very special garments, maybe it won't fit into this canonical space, or maybe we need to have like additional degree of freedom to describe them, like the hoodies. Yeah, so I think if we want to consider more categories, then we need to like maybe revisit this definition.
Okay, so maybe one last question. I'm curious. You very nicely presented the two approaches to kind of go back, do the warping back to the original pose from the canonical pose. But I wonder, can one help the other in closing cycle consistency? Because if you take your prediction and plug that into a physical simulator, and you could actually match that to your original pose and ask, did my network do a good job predicting the warping field?
Yeah, exactly. I think that's a very good idea for so if we are thinking about automatic labeling data, this is one thing that we are thinking, like if we can kind of know where you grasp and you know the 3D geometry of the t-shirt, then you can do the physics simulation to kind of propagate this kind of dense coordinate label in order to get like labels. Or you, as you said, you can be like a self-consistent training process. You predict and then you check with your observation and see whether your prediction is correct or not. I think that's like very interesting. We didn't do that, but I think that's definitely a very interesting direction. Yeah.
Awesome. Thank you again, Shuran. This is great. Thanks for joining us. Feel free to stay. And if anyone wants to post more questions and you're still around, feel free to answer them on the chat. And I'll pass the mic over to Shubham to introduce our next speaker.
Bye.
Thanks, Shuran, again for a great talk. Yeah, so we have Jitendra as our next speaker. And before I introduce Jitendra, if it's possible for you to share your screen just so we're sure things are working, that would be great. Yes, so we see the slide. We see the slides. Perfect, thanks. So yeah, it's a great pleasure to introduce Jitendra, who of course is a person who really needs no introduction. He is a professor of computer science at UC Berkeley and also a director of research at Facebook AI. He is a member of almost all prestigious academies you could think of, like the National Academy of Engineering and Sciences, and has won numerous awards in computer vision over the years. In fact, I think the set of conferences where he has not won an awards might be smaller than the set of conferences where he has won awards. And I had the pleasure to be mentored by Jitendra over the course of my PhD. And one of the most remarkable things about him was the ability to sort of drive and predict the directions in which the field should be going back to, let's say, embracing empirical evaluation and data sets in the 90s, to then focusing on recognition and the interplay with the other two R's, the reconstruction and reorganization, and sort of more recently, the focus on perception in embodied settings. And I think one of the best predictors for figuring out what the field will be focusing on in the next few years is to look at what Jitendra is doing right now. And I think with that, we are very excited to hear what he has to say. I think if maybe you're muted.
Can you hear me now?
Yes, now we can hear you.
Okay.
And maybe just a logistic thing. So we are hoping to leave 5 minutes for questions at the end. So 30-minute talk, and I'll bug you at 25 minutes just to give you a 5-minute heads up.
Perfect. Thank you. So thank you, Shubham, for this very generous introduction. And this talk will have a technical component, which is an approach we call differentiable stereopsis. But before I get to that, I want to state a little bit of philosophy. And this is really my philosophy for all of AI and not just computer vision. And this is that I believe that Turing's proposal from his 1950 paper, which was the following, which is that instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. So I really do believe that this is our way towards artificial intelligence, that we start with some inbuilt stuff, but then after that, we try to copy various aspects of how children grow and develop their mental capabilities. So in the early stages, children are very multimodal creatures. They're interacting with the world. They're playing, this child is playing in the crib. She touches an object. She hears some sound. She sees it. She moves around. Then there's this phrase from Alison Gopnik, which is that the child is like a scientist in the crib, interacting with the world, doing experiments from which she acquires knowledge about, for example, Newton's laws and so on. So then this child, after 1 or 2 years of this, then when you take this child, the mother takes this child to the zoo and then gives one example of a zebra. Okay, that's enough for the child to know the concept of zebra. Compare this to what our systems need to now do. We train them on ImageNet and they need like 1,000 examples of zebras, and they can't even, those examples will not be enough to get a 3-dimensional notion of a zebra. So that's my philosophy. So given that philosophy, let's get to the subject of this particular workshop, which is about 3D. So what do we know from child development about 3D? So I picked one paper. There's a fair amount of research that has been done, but this is quite concise in terms of what it says. So it's talking about the development of sensitivity of kinetic, binocular, and pictorial depth information. So kinetic means structure from motion, from like the moving camera or the moving object. Binocular, of course, means 2 eyes. And then pictorial depth information means that we can see depth in a single image. And those are pictorial cues. And there is a very definitive order to this. Sensitivity to kinetic information may be present at birth or soon after. Sensitivity to binocular information appears between 3 and 5 months, and sensitivity to static monocular information appears between 5 and 7 months. So I'm not going to insist that we have to slavishly follow the development in computer vision of the development of these capabilities and in human vision, but this gives you an existence proof of a certain approach that could work, which is that you start out from using multiple views as a signal. So you can call it structure from motion, or you can call it binocular stereopsis. And with that, we build some kind of 3D models of objects. I mean, the term model I'm using in a very broad way. And then subsequently, we have the ability that even from a single image, even when it's just a picture, we are able to see it in 3D. So that's the program of research that I believe we as a community should be pursuing. So, so what would be the grand goal? My grand goal is that, so now I'm going to put it in computer vision terms, the research goal is to develop the ability to 3Dify any scene. So any image that I see, this image is just 2D collection of pixels, but what I want to see in it are these 3D objects, which are indicated here. And so I can actually have a notion of what would it look like if I move around and so forth. So that's what I call 3Dification. And it should be possible to do it from a single image. But before that, there is a stage of acquiring the 3D models. And those 3D models are acquired from multiple views. That's natural supervision. So CAD models and so forth, or the way we have done things in the last 5 years with ShapeNet, I mean, this was useful for the current stage. It got us started in this era of sort of learning to reconstruct. But I believe the right way is to reconstruct from multiple views. That's the natural kind of supervision. And I think this will be, the data for this is getting there, right? Because the whole field of computer vision benefited from the fact that cameras became ubiquitous. Every cell phone has a camera, and people were taking pictures and uploading them. Well, I think we are going to have be in the situation where now many of these images will be 3D, right? I mean, the new phones have this kind of capability. And as these are uploaded, we will have the kind of data on which we will be able to build the representations that I'm talking about here. So, okay. So now we go into further down the technical path. So basically, what we need is to develop the practice of building 3D from multiple views. And this is something that we have been doing in my group for several years. In fact, one of the earliest papers was from Shubham and Abhishek in the 2015 kind of era. And here is one of the recent papers from that paradigm, which is we are trying to reconstruct these 3D models of birds. And the starting point are many views of many birds, but these are distant views and just single views. So I just have single pictures of many different birds, but they of course share a family resemblance. And from this, we are able to build a 3D model. So, and then we worked on this, a couple of papers with actually Shubham Tulsiani and Anju, and then here's the latest paper, which shows how we can get pretty good results in this setting. But today I'm here to talk about setup of recovering shape from multiple views, which is a little bit more classical in nature, which is when you have multiple views of exactly the same object. In this bird example, we had multiple views, but they were of different instances. They all shared the category, but they were not the same instance. So we're going to call this approach differentiable stereopsis. And this is a very simple idea. It's actually something which, after I'm done with this talk, you will not need to read the paper. It's as simple as that. And it's the kind of stuff you can teach in an undergraduate computer vision class in like 15 minutes. So it's interesting that it somehow has taken longer to discover it than more complicated and more sophisticated schemes. So, and this is, of course, to acknowledge my co-authors, Shubham Goel and Georgia Gyoksari. Okay, so what's the problem we are dealing with? So the problem is it's the classic SFM or stereopsis kind of problem. So you have a bunch of images. Okay, let's call them RGB images of some object. Maybe we also have the masks, and we also have cameras. And these could be noisy because if you assume exact cameras, it makes the life much easier. But we're assuming very noisy cameras, maybe 10, 20, 30 degrees off. So that's the setup. Okay, and then what's the output? The output is shape and texture. So you recover the 3D shape. Okay, in our case, that means 3D shape in the form of a mesh, as well as a texture map. And with this texture map, you can render from any viewpoint. So, so this is a complete representation, complete shape as a mesh and a texture representation, and very classical. I mean, this is what graphics people would be comfortable with from 40 years ago. Okay, how do we do it? Okay, first of all, I should convince you that it actually works, and here are some results. So here are 8 views of an object, and we have some initial guesses of cameras, and then but they are quite noisy. They have like 20-degree noise with respect to ground truth, and then these are the reconstructions. Here's an example from, say, Amazon catalog. You have some 4 photographs of this one guitar. And what we can do is, so then the question is, how do you get the cameras? Well, one answer is we can use structure from motion techniques. So use CallMap. I mean, that's like the standard open source software out in use. Now that is a way that will basically that will find a few corresponding points, and with that it'll estimate cameras. It can't really estimate dense shape because it'll only estimate it for the few points that you can correspond. So flat areas don't really count because you don't have any features there that you can correspond. And then here is another classical kind of data set from the multi-view stereo community. So this is called Tanks and Temples, and here's the statue of a horse, and we have these 15 views. You estimate the cameras using CallMap, and after that you can do this reconstruction. So note that CallMap helped us initialize in terms of getting cameras, but CallMap could never give us these dense 3D reconstructions. Okay. So that's what. So that was meant to be a preview of what the approach can do, and then just to relate it to classical work. So there's a lot of classical work on sort of stereo and structure from motion in the era pre-deep learning. I mean, people have been working on. In fact, if you consider the field of photogrammetry, it has existed for close to 150 years, and in computer vision for like 50 years, we have had approaches based on trying to make use of multiple views. Okay, and then in the current era, in the last 5 years, a lot of the models for 3D have been based on, you start with ground truth 3D and then you try to learn how to predict that ground truth 3D, because supervised learning is the paradigm, right? So you want to, you convert the problem of 3D to a supervised learning problem. You have one image, you have the ground truth 3D model, ShapeNet is canonical. I think this was useful, but I don't particularly like this going forward because this begs the question of how you get the ground truth 3D model in the first place. I mean, we do eventually need something like this where, because we need to have the ability to 3Dify from just a picture. And then of course, there's this example of work from Berkeley on this, this bird kind of reconstruction. And of course, there's, we are in 2021, so we are all aware of the nerve revolution, which basically is how one can make use of multiple views. And there's a lot of excitement around that. And this is work from colleagues at Berkeley and Google. Okay, now where do we come in? The framework is we're starting from images and masks and noisy camera poses, and the goal is to get to shape and texture. Okay, so so let's first recap what like a traditional. What if you took a class in 2005? What would Steve Seitz tell you in a lecture on stereopsis, right? So what we know is, okay, we have multiple images. We need to find corresponding points. And once we have corresponding points, then you do triangulation. You have a point you see in two views. So you have the two cameras, you extend the rays where they intersect. That's where the point is in 3D. Okay. And, a photosynth, right? These are examples of sort of systems developed from that era. And now, if you notice some of the great works from that era, like Snavely, Seitz, and Zelinsky, and so forth, they relied on, there's some picture of the Colosseum or whatever, which has like thousands of tourists taking photographs. So as a result, you get a fairly dense coverage. If you have very few views, then we are in trouble. So this is what's called the problem of wide baseline stereo. Suppose I have only 4 views. Then these views are very far apart, and finding correspondence becomes hard. And you may not even, you only see some points in multiple views, most of the points are there may be points which are only in one view, in which case you can't really use them in the standard SFM style. But the big challenge is getting dense correspondence. There might be a few points which are characteristic enough that you can correspond them, but not a lot. So your shape recovery will be very sparse, be a very sparse point cloud. Okay, so what do? So we here in this work, we draw a very old idea, and this is what we call model-based stereopsis, and this is from a paper 25 years ago. Okay, Paul Debevec, C.J. Taylor, and myself, and this is work presented in like the SIGGRAPH in 1996. So this is the so-called facade system, which was very influential at that time because it was kind of the entry of computer vision techniques to help computer graphics in terms of building models of real world scenes. And this is actually somewhere buried in that paper and not the most prominent aspect of that paper. But the idea there was something like this, that if I'm trying to match these two views, these are difficult, they look very different. But suppose I have a rough estimate of the shape and the camera, then what I can do is I can kind of warp this to a new view based on this current estimate of the shape and the camera, and then I do the comparison. So basically, model-based stereopsis is like trying to reduce it to a residual matching problem. You get the bulk of the job done on your current guess, and then you try to do the rest. Okay, this is of course an idea which shows up repeatedly and is a very good idea, right? I mean, iterative solution procedures have been used in optimization for years. In computer vision setting, we had a paper on iterative error feedback with Joao Carreira, and you can think about ResNets as having an aspect of this main path and then a residual, and which once the residual becomes small and sort of easier to deal with. So it's that intuition, okay. And but of course, this was that was 1996, and this is 2021. So what do we know in 2021? We know that we want to use deep learning, and deep learning is really about computing gradients, right? So if you have, once you can compute gradients, you can do gradient descent. So differentiable rendering is the tool, and you have packages like PyTorch 3D which make that possible. And of course, there was preceding work like the software rasterizer from Howley's group and Neural and so on and so forth. So we're going to basically meld these two ideas together. Okay, this is again a picture from that 1996 paper from 25 years ago. We are trying to match the key image to the offset image. And what we do is we warp the offset image into the camera of the key image based on our current estimate of the shape. I mean, in this case, it's just a plane. And now when I'm trying to solve my stereo correspondence problem, I'm doing it between these two, which look fairly similar. So you have a much easier problem. And you can see how, by the way, this idea is so simpatico with what we would do with differentiable rendering, right? Because it's like a small error, which you will then try to correct by tweaking the shape and tweaking the cameras. So this is it. This is our algorithm. There's no more to it. You don't need to read the paper. Okay, we need to have a guess of the shape. So we start with a sphere, and there's some little trickery to deal with the fact that the topology of the object we are dealing with may not be that of a sphere. So what we're going to do is periodically do some remeshing, but I'll come to that. But the main is there's a shape S, there's a camera pi 1, 2, which corresponds to the projection from 1 to 2. And we compute some kind of a gradient. We adjust both the shape and the cameras, and you just keep going until you're like happy with the result, and then you output. Okay, more details. So suppose we have view 1, view 2, view 3, and we have a current guess of the shape. Okay. Now what we do is we will take the shape and we will texture it, and we need to choose which view to texture it, because you can see that the views are from a certain camera angle. So therefore, like one side of this object, the texture for that may be available only in view 1, and for the other side, it may be available in view 2. So there's a little bit of work to basically find which view to extract the texture from, but we're going to extract it with quote the optimal view based on some heuristics. So basically the one where you see it most fronto-parallel is the best view to use. Okay, so now we have textured this shape. Okay, and then we have a target view. Okay, and so what we can do is, this is based on our current guess of shape and current guess of cameras, and then the textures we have exactly because we have the views. And we render the view from the camera for view 3. And if our shape was correct and if our cameras were correct, these two should be identical. Okay, they won't be, right? So that's where we measure some loss. So there's some discrepancy there, and that's this loss. So like the L2 loss in the image, or you can throw in other perceptual loss, some regularization of shape. And now we measure this loss, and then what do? We use that to compute some, now that's where the differentiable rendering machinery comes in. We're going to try to make some corrections. So we're going to make some corrections to the cameras, pi3, pi1, so forth, and then some corrections to the shape. And hopefully that makes this loss smaller. That's it. That's all the idea. So there is a forward process shown by blue arrows, and then there is this the gradients which are flowing backwards, which is in this with this other direction of arrows, and that gives us these results. So here are 8 views from which we can do these reconstructions, and more objects, okay, and more objects, and basically this machinery just works. It just turns the crank. And note that it's working in settings where it's a bit shady, the basic assumption. So the assumption we have made here is that of classic stereopsis, right? So classic stereopsis essentially assumes that a point looks the same in different views, which means that you are assuming that the object is Lambert-shaped. Okay, so when you have shiny objects, classic stereopsis actually will have some trouble. So some of these products are shiny, right? So at that point, we should be doing different things. I mean, we should obviously be building in the some kind of parameterized BRDF and doing appropriate stuff for that. That is possible. I mean, this framework can easily be extended to that, but we didn't do that. This is version 0, so we need to keep it like super simple. And now I want to do some qualitative and quantitative comparisons. And obviously, since this is 2021, we have to compare it to NUF. So of course, if this was 2005, you would say compare it to classic SFM. So the comparison with classic SFM is easy. Classic SFM can probably find you decent cameras, but it's not going to give you dense shape. It's going to give you a very sparse point cloud. But of course, we can use NUF. Now, what's the difference between NUF and this? Roughly speaking, NUF is volumetric and this is surface-based, right? I think that's the difference. Now, and then in both settings, you have to get into differentiable rendering in some way, right? Now, when you have enough views, which is the setting in which NUF was developed, then that paradigm works perfectly fine, right? I am trying to deal with the case that when we are doing stereo reconstruction, if you think about it classically, we usually have relatively few views, and we need the approach to work in relatively few views. So that is where we hope to see some superiority to NUF. Otherwise, there is no value added by this technique. You can just do it in that way. So, okay, so first of all, what does CallMap do? CallMap will do a credible job on finding cameras, but not in finding dense depth. I mean, you'll get some point clouds, but the point clouds will be quite sparse. Okay, so the serious comparison is with NUF, and let me show that here. So we have these two metrics on chamfer distance and F1, where chamfer you want, the chamfer loss between the reconstructed shape and the ground truth shape. And what we have here on the x-axis are how many cameras do you have? 4 views, 6 views, 8 views. 12 views. So the 4-view case is pretty difficult because there's not going to be that much in common among the different views. And then this is, of course, what the loss is. And then we have these other curves. These other curves correspond to how much noise there is in the camera. So, I mean, we can't assume that Colmap will give us perfect cameras, right? So we should test what it does with when the cameras are off. So we have here these 3 curves. The solid lines are DS, differentiable stereopsis, our approach, and then the dashed lines are with NERV. And again, we have the so this is like noise variance of 10 degrees, 20 degrees, 30 degrees, that kind of thing. So what do we expect? So first of all, we should expect that R10 should do better than R20, should do better than R30. So you should see that in the curves, right? So the green curve, versus the orange versus the blue, right? Okay. Then, but note the other thing, which is the solid, which is our approach, differentiable stereopsis, and the dashed one of the same color is the NERV approach. And what you see is that the dashed curves are always higher, which means that they are giving you a bigger error. And this gap is more noticeable when you have few views and more noise in the cameras. When you drive to the point of like you have 12 views, right? Then you see that the errors are all very small, and then basically both approaches do perfectly. I think our selling point is really the robustness for few views and noisy cameras. And this conclusion holds up in multiple settings. It holds up in the setting of measuring chamfer distance, this F1 loss. This is comparing the shape recovery by comparing surface normals. Okay, so they are consistent, meaning the angles are 0, then that's the best. So like the dot product should be like 1. So it's a consistent result. Here are some, and then here are some.
Just a reminder that about 5 minutes
Yeah,
are left.
that's good.
Thanks.
Thank you. So here's some ablations. It makes use of the masks. So you might think, oh, is this just save space carving in some? No, it's not, because if you didn't have the textures, you would not get the right interior of the shape. And if you don't, this shows that. And then here are a variety of results. I think I've shown some of them before. It's to show that the cameras can be estimated from SFM. Lots of product shots. I mean, if the paper is now on archive, and you can look at zillions of results to convince yourself that this is robust. Like this is a really bad case because the surface is very shiny, and it still does a reasonable job of recovering the approximate shape. Obviously, we can add fancier priors and so forth, but our approach here is to be as vanilla as possible in this first work. Okay, so this is the tanks and temples, classic stereo data set. Some more results. Okay, here the cameras are obtained from Colmap. More results. More results. Okay, and I'll conclude here. So it's a very simple story. It's a very simple paper. Okay, SFM techniques like Colmap do, and I want you to think of it in the context of the last 40 years of work on stereo and structure for motion, where wide baseline stereo was regarded as like a grand problem that we needed to solve, which we didn't have good solutions for. And I think now we do. Okay, so we can start with something like Colmap for finding cameras, but it won't give us dense point clouds. Our technique as well as NERV can get dense shape. The difference is one is surface-based, one is volume-based. Both are making use of the information of how the object looks like from multiple views. So in that sense, they are solving a similar problem with different techniques. One is volumetric, one is surface-based. For the case of many views, both do well, but for few views and noisy camera estimates, DS is more robust. It solves the classical problem. And the paper is on archive, you can read it. Maybe I'll make one remark because this is probably a popular question, like why do you, when you use meshes, that you're compelled to use some topology, and we started with spheres. So, but obviously the objects we're reconstructing are not just spheres. So our basic trick is you start from that sphere topology, you start proceeding towards doing the reconstruction of the shape. And then at periodically, what you do is you, from the mesh, you go to a point cloud, and then you remesh. And that remeshing will change the topology. And then you just continue. And this simple approach of at various points in between, you just convert to point cloud, remesh, that's been good enough for us. And with that, I'm done. Thank you very much.
Great. Thanks, Jitendra, for a great talk and sort of some revisiting of the past. So we have one question from Orr to begin with. So I think he's alluding to the pipeline where you showed that there are certain source views from which you can transfer texture and then synthesize a novel view for training. And the question is that he assumes the solution would really depend on what views are selected as the source and target ones. And one may get different results based on which views are selected for what. And do you have any thoughts on this? Or
Okay, first let me stop share. So basically we use all views, right? So basically everything is being used as a source and everything is being used as a target. You can only use, but there with some caveats. The caveat is that, first of all, that texture should be visible, okay? And then the best one to use is what's the most frontal parallel texture. So that's the one which is least distorted. And this is an old idea, again, in that paper from 1996 with Paul and CJ. We had something called view-dependent texture mapping. And the idea was the best texture to use is the one which was seen most fronto-parallelly. Because when the texture is seen at an edge, it's going to be very distorted, right? Whereas when you see it frontally, it's going to be the best. And that's basically that cosine of the slant term. So you want to have the cosine of the slant be as close to 1 as possible. That's it, nothing fancier than that. I think so everything is being used. I think the places for improvement, if you want to know, are probably in better BRDF models. It's just assuming Lambertian. Shubham Tulsiani's recent work has examples of using fancier BRDFs, and this is again classical. We had a paper in 1998 which was in this like building off on that 1996 work, 99 maybe, where we used fancier BRDFs and they help. And then maybe we need better priors, right? So the surfaces are not like absolutely flat, right? Because at some point the loss function is not hurt enough by that. And but in the kind of world we live in, there are lots of very planar surfaces. So there should be some way of incorporating that kind of a constraint. But I strongly believe that in the first paper you write with a technique, you don't put in all these bells and whistles. Keep it simple.
So actually one other question I had, going with the title of the workshop on representations, is, so in your conclusion, there were these two representations. One is this mesh-like representation, which you're using. One is NERF, which is very volumetric. I think over the last few years, you've also seen some maybe hybrid ones, which use volumetric SDFs, which tend to have some surface-like properties while still being volumetric. So I was curious on your thoughts on how these might fit into the differential stereopsis framework.
Yeah. So I don't have any any non-trivial thoughts on this. I feel that I think the benefit of the volumetric representation is in terms of the optimization. I think that's where it really shines. Otherwise, I think surface representations are more natural. I think that because we have to do something to make these processes, like rasterizing is not differentiable. You need to do some tricks to make it differentiable. And people have worked those out in those earlier works like the neural renderer and soft RAS and so on. And then, but the volumetric setting just, I think, makes it much nicer and easier. And I mean, you had a version of it with the differentiable rate consistency, but it somehow seems that volumetric is very nice for the optimization. But otherwise, I think surfaces are the more natural representation because objects are typically opaque. So volume rendering is overkill, right? I mean, in graphics, how many people do surface rendering and how many people do volume rendering, right? So, so I think that that's what the tension here is. And let it play out. Yeah.
Okay, thanks. Also, I think those are very excellent remarks to keep in mind for our panel discussion later. But yeah, I think thanks again, Jitendra, for the talk. So we have a short break for 10 minutes now, I think. So if you want to go grab a cup of coffee, please feel free to do that. And we'll meet again in about 10 minutes.
Okay, thank you very much. Bye.
Thanks.
All right, so welcome back to our third and final session of the day. I hope you all enjoyed the last session. I think it was very exciting. This session also has a surprise at the end. So we'll hear a talk from Noah, then from Katerina, and then we'll have a panel discussion. We'll have all the speakers back, or most of our speakers back, for a panel hosted by Gordon. So that should be also exciting, with some thought-provoking questions from. I know Gordon has prepared for you guys. So it's my great pleasure to introduce Professor Noah Goodman. Noah is an associate professor of psychology, linguistics, and computer science at Stanford University. He studies the computational basis of human thought, merging behavioral experiment with formal methods from statistics and logic. Specific projects vary from concept learning and language understanding to inference algorithms for probabilistic programming languages. Noah received his PhD in mathematics from the University of Texas at Austin in 2003. He then entered cognitive sciences, working as a postdoc and research scientist at MIT. In 2010, he moved to Stanford, where he runs the computation and cognition lab. I'm really glad to have you with us, because this workshop is about bringing people working in 3D representations from multiple fields. And I think we've yet to hear from a speaker with your background. So I'm really curious to see what you have to say about all you've heard so far, and what representations you're using for your research. So without further ado, I'll just remind you that I'll give you a 25-minute kind of note. Take it away.
Awesome, thank you, and thanks to all the organizers for having me. So I don't primarily work on computer graphics or 3D representation. I dabble sometimes with that, but what I mostly work on is kind of human conceptual representation and language. And so I'm hoping that what I'll do today is kind of take you on a little bit of a fun detour through a different world, ending up back where we can talk again about sort of visual representations. Now, okay, I want to start with this really high-level question that I think a lot of people are interested in this group, which is simply, how do humans structure our representations of the world? And in particular here, we should think about the visual world. So what's the structure that we use to represent the visual world? Now, you can try to figure this out by looking at the visual world itself, by looking at what you might call purely visual behavior in humans, like eye movements and stuff. Or you can say, hey, wait a minute. Language is this amazing window into human mental representations. Language, because it's relatively high level and compositional, it really tells us a lot about the pieces that we need to explicitly or implicitly represent in our representations of the world. So for instance, that chair is a bunch of pixels, maybe a 3D mesh. It's also a chair with 4 legs, a slatted back, and thin arms. And you can imagine, okay, great. If I had that language, I could figure out the appropriate part decomposition of the chair, sort of very, well, maybe not immediately, but very, very much more easily than if I had no idea how humans thought about it. There's a catch, of course. So what if we just use language to learn representations? And what I have in mind is, like, we might end up with something like these beautiful pictures, in this case from the PartNet, project, where we have objects together with all of their different decompositions. But the fact that they have many different decompositions starts to point to the catch. And the catch is that the way humans use language depends very, very heavily on the context that they're using the language in. So for instance, if I ask a human what that is, they'll probably just say chair. They won't give all of that really nice compositional kind of structure. If I ask them to describe the chair on the left out of this context, then they might say it's a chair with 4 legs. And if I expand the context some more, maybe I can get them to finally produce this more detailed utterance: chair with 4 legs, a slatted back, and thin arms. So the basic point here is that before we're going to be able to use language in order to understand visual representation, we're going to have to do some work to understand how context affects description in language. Now, I'm going to do that by taking a step away from 3D and really any rich visual representation. But I will hopefully get back to it. And my goal, the promise here, is that eventually we're going to be able to say something about not only how to use language, taking into account the context and how context affects language, but that there will be some payoff. That by taking into account the pragmatics, this context sensitivity, as well as the semantic composition properties of natural language, we're going to hopefully get a payoff in the form of reduced data complexity for the learning problems. And maybe this will be a topic we can all think about together at the end. So, okay, let me dive in. And by the way, I can't see the chat at all. So if there's any pressing questions, feel free to just unmute and raise them. I'm happy to discuss.
I'm following the chat closely. If there's anything, I'll interrupt. Okay,
perfect. Yeah, awesome. Okay, so how do we think about context sensitivity for language in a kind of visual reference setting? Well, the canonical way of thinking about this goes back to the 70s, where a bunch of natural language philosophers were thinking, what is reference? And David Lewis in particular wrote about this idea of reference games. So in a reference game, you have a set of objects or a set of situations, and there's 2 players, a speaker and a listener. You can imagine that you're playing the game and you have this set of objects in front of you. And if you're the speaker, you maybe are asked to refer to the middle object, and you have to think, would you rather say blue or circle? Now, probably most people would rather say circle because there's only one circle, there's 2 blue things. This then sets up the other side, the listener side. As the listener, you might imagine somebody uses the word blue and you have to figure out which object it is. Now, it doesn't uniquely pick out one of those objects, but if they said blue, they probably weren't referring to the blue circle because there's a better way to refer to that. And so this is a really elementary, awesome demonstration of how the basic meanings of language get strengthened in context. So here, blue might mean the blue square, even though in general it could mean any blue object. So how are we going to capture that kind of reasoning? I think this because you could have done that because I think that. Well, together with some colleagues over the years, we've done this using a pretty straightforward Bayesian modeling setup. We start out by just assuming that there are some literal meanings that connect the utterances to the objects. So in this case, blue picks out the blue objects. And then a literal listener simply renormalizes over the possible reference. There's a target object, an utterance, a context set, and critically, this meaning function that says yes or no to each of the objects. From there, then we can say, oh, well, what if there's a speaker who is choosing an action approximately optimally in order to convey the reference to the listener? So then the utility of the speaker is simply the information conveyed. And this is pretty interesting because you can get the effect that, when referring to the middle object, the speaker would rather use circle rather than square. But when referring to the left, the blue square, the speaker kind of doesn't have a good way to uniquely refer to that object. Then we can keep going. We can say, oh, what if we have a listener who's aware of the way that speakers behave? Then in that case, this listener can do a Bayesian inference, but now where the likelihood is the speaker model, the probability the speaker would say a particular utterance to refer to one of the objects in context. And now what happens very nicely from this is that this pragmatic listener, the listener marked as L1, will exhibit exactly this kind of strengthened meaning inference. They'll say, oh, the speaker wouldn't have used blue to talk about the middle object, so they must mean the blue square on the left. Okay, so some whole bunch of years ago, 10 years ago, Mike Frank and I said, hey, let's test this simple Bayesian model in these reference games. Details don't matter much, but we ran a bunch of these simple reference games with speakers, with listeners, and running another condition to measure the priors that we needed, just explicitly measure them. And what we found is that this simple Bayesian reasoning model of social inference, I think that you think that I think, is really good at explaining both how people choose to describe objects and how people interpret descriptions of objects in this simple setting. So this is really cool because it gives you at a high level a way of starting to take into account all of the context sensitivity of how people use language, so that hopefully then ultimately you can back out sort of what words mean and how they connect to the visual world. We've used this for all sorts of stuff in language, and I'm not going to talk about most of that, although there's some review papers you can look at. What I want to talk about instead is to say, sort of, how do you go from this very simple picture to somewhere that we can start to learn the meanings more directly from richer kinds of stimuli, although still in reference games. So the first observation is that if I actually asked you to talk about, let's say, the object on the left, you would probably say something like green square. Now, this is sometimes referred to as redundant or over-informative, because of course you don't need to say square, you could just say green. And the model I showed you a moment ago, which I don't think I mentioned, is usually called the rational speech acts model, says that that shouldn't happen, that people won't be over-informative because there's no additional utility provided from that. And so if this is actually how people behave, if people actually will say green square, it seems like a definite problem for the modeling. It turns out people do this. In somewhat more recent work, we've gone from using this kind of artificial, limit the words that people can use kind of paradigm to using these two-player interactive language games on the internet. It's really nice because we don't restrict the language and we get sort of much more rich linguistic data, how people actually talk about different objects. And sure enough, in a context like this, people will say small blue pin, even though small would be enough. Okay, so how do we explain that? That seems like a problem. Well, the basic observation here is really simple, and it goes like this. If you weren't totally confident that somebody would understand what you mean by small, then it might be rationally redundant to add the extra information, say something like small blue. So in order to capture that idea in this social reasoning model, all we have to do is assume that there's a little bit of wiggle room in the basic meanings. We could do that by adding stochasticity, but it turns out to be equivalent, and I think a little bit nicer, to simply relax the meanings to be a real number between 0 and 1 instead of being Boolean, either 0 or 1. And so the basic idea is that when you apply small to that particular small blue pin, the number, the fit might be 0.9 instead of 1. And that's enough wiggle room that it might be reasonable to add the extra term small blue. Now, what we're going to do here is we're going to assume that the different modifiers, the different nouns and adjectives, compose together by multiplication. For the moment, just think of that as like a very simple, easy assumption to get us going. But I'm going to come back to this idea of how exactly do we want to model composition amongst the words in a little while. I can't actually see anybody's face at all, so I'm just assuming that you're all happy and following. Oh, there's Or. Okay, great. So good, yeah. Okay, so what we do here is we relax the basic words, and for simplicity of modeling, what we actually assume in this case is that each kind of adjective, size, color, and so on actually just has what we call a fidelity, sort of the epsilon away from 0 or 1 for that kind of adjective. And so this lets us potentially model the idea that maybe size is a little bit, has a little bit more slack, a little bit more noise than color and so on. Okay, so if we do that, and we did that, we ran a reasonably big experiment. I'm not going to tell you the total details here, but the experiment was designed to kind of systematically vary how many distractors share different properties with the target object, because the model said that should be important. And so we give it a whole bunch of data. And the basic result here is that the model is now able to predict the data quite well in this pretty complex set of different conditions. And critically, the model now predicts the over-informativity or the redundancy for exactly the reason I mentioned before, that real valued meanings all of a sudden make it reasonable to provide extra modifiers if you're not sure that you're going to be sort of accurately understood. Okay, so on the one hand, all I did here was kind of tell you about how to model the context sensitivity of language in a slightly nicer way. But I also snuck in a key property here that everybody in the room is sort of a deep learning person. And so you're going to be happy that now the basic semantics is a real valued thing, right? Now, that's good because, hey, real values, but it's also good because that means that things are differentiable. And so now we can go and we can say, hey, what if we wanted to learn the meanings from the data instead of just kind of stipulating what the meanings are going to be? To do this, I'm going to look at another little reference game corpus. This one is in some sense even simpler, although it's kind of nice because it's kind of a more uniform space. We take all of these color patches and we ask people to play a reference game referring to these color patches. Now, what's interesting about colors is that if you are just given one color, you'll use a very simple basic level term like green. But because we can manipulate the context here, we can get people to produce these actually pretty complicated color descriptions, like, the light orange one, or sometimes they're a little bit more metaphorical, like, the baby puke green one or something like this. I think that was a description of this particular color. Okay, so we have this big corpus of now color reference. And the question is, can we learn the meanings of these expressions, these color expressions, from the data itself? It's about 50,000 utterances in the corpus, grounded utterances in the corpus, various conditions that I won't go into, but they basically vary how similar the distractor colors are from the target color. Now, when we think about learning, we're going to be able to learn. Let me just go back one step. Well, I guess it wasn't on this slide. Okay, we're going to be able to learn as long as we have a differentiable meaning function, because, well, gradient-based learning, deep learning, all that. We could use whatever we want here, and I highly recommend, if people are doing this again today, to use something more modern, use transformers and all of that. But it doesn't matter a great deal. So the underlying semantic model just needs to be something that can take a referent, in this case a color, but more generally any visual referent, and a sequence of words, the utterance, and spit out a real number. So here we use an LSTM, glove embeddings, CLab color space, all of this kind of stuff. And oh yeah, I have a little aside here just because it's fun. It turns out that actually the L0 model, if you think about it as simply an embedding model, is in fact equivalent to the info NCE lower bound on mutual information. So if we decide we're just going to train the literal listener model, we're actually doing modern representation learning sort of magically all by itself. And it's a pretty straightforward proof, but a kind of interesting observation. But that's not actually what we want to do. What we want to do here is we want to say, hey, wait a minute, Noah, you just said that it's really important to the actual language behavior to take into account the context, so the pragmatic behavior. And that you can describe this by these like L1 and S1 models, the pragmatic listener and pragmatic speaker. Now, on the face of it, that seems like kind of an obstacle to learning the underlying semantics. However, the RSA model is really very simple and it's fully differentiable as a function of the underlying semantics. So if you look at the equations here, the only obstacle is the proportionality where we have a normalization. If we were able to explicitly normalize, then we can just use autograd to take the derivative all the way through to the thetas in the semantics. And so we do need to do a little bit of approximation. We have to sample in order to approximate the normalization. But fixing those samples, then the whole thing is differentiable. And that's cool because it means that we can ask, what happens when you take the pragmatics into account in trying to learn the semantics, the mapping between meaning and between objects and utterances, and how much does it matter that you take the pragmatics into account when you're training the model as opposed to only when you're using the model after the fact? Okay, so here's what I just said. Interestingly, most previous models before we had done this, either there's no pragmatics at all, so you can think of that as an L0, a literal listener at training, a literal listener at test, or they would train without any pragmatics, a literal listener at training, and then they'd stick pragmatics on the top of that to see if it helps at all at test. And the finding was like, yeah, it seems to often help a little bit. So there's, for instance, some old papers, nice old papers by Jacob Andreas and some by us at Stanford, kind of doing that. Nobody had looked yet at the question of, well, if you're going to use it pragmatically at test time, shouldn't you train it pragmatically also at learning time? So we decided to try it. And the basic result here is, yeah, actually, taking into account the pragmatics at training and test time is useful. Now, the table that I'm showing you here is relatively small differences. They're reliable. They're actually highly reliable differences, but they're relatively small. And what we see is that there's a little boost going from no pragmatics at all to pragmatics at test but not training time. And there's a bigger boost going to pragmatics at both training and test time. And it's worth saying that the fully pragmatic model also beats the previous baseline from the Monroe paper. Now, we had the intuition that, oh, and there's just these kind of pretty eye candy pictures on the right, which are showing you how the model decides to ground various color terms into CLAB color space. And just stare at it, it's kind of cool to look at the kind of regions that the model chooses. But more importantly, what we wanted to know was basically, does the pragmatics help to reduce the data complexity of the model by essentially telling you how the other objects are supposed to interact with the target object when you're interpreting the language. And so we just did a little study where we subsetted the data pretty radically. And sure enough, the pragmatic boost is there more at the much smaller data set sizes, but it's not very big kind of ever. And so we then kind of hypothesized that the issue here is that the domain is not complex enough. And as soon as we start to have a more complex visual domain, the value of pragmatics is gonna show up even more strongly. So we made these still not very complicated, but slightly more complicated stimuli that we call color grids. So 3x3 grids of color patches. Did the same kind of data set creation reference games, verified that we get longer utterances because people are just describing more about each of these images than in the color case. And then did the same kind of modeling study. And here, if you look at the plot on the bottom, what you see is that sure enough, the boost due to pragmatics during training is bigger overall, and it sticks around as the size of the data set gets bigger, which indicates that basically there is this data complexity boost, and it's bigger the more complicated the domain is. Okay. So what about more interesting shapes? Now, this is where we get to start thinking a little bit about 3D and the kinds of shapes that you all are much more interested in. So together with Leo Guibas's lab and led by Panos Akliopoulos, who is a grad student there, we did the same basic idea. Let's do reference games, but now let's use 3D objects. And so we went to ShapeNet and we pulled out, first of all the chairs, because there's a lot of them. And then Panos did this kind of very nice thing where we used existing embeddings, PointNet embeddings, in order to construct both hard contexts of chairs where we thought the geometry would be pretty similar, and easy ones where we thought the geometry would be pretty different. And then again, we had people play this reference game and collected, in this case, about 80,000 utterances. So we can look at both modeling the listener behavior. If you hear an utterance, which chair should you pick? And then at looking at the speaker, how do you generate utterances? I guess at a high level, what we found here was that surprisingly, like we could do this task reasonably well. There were some simple sort of standard things like attention matters in the language model. For this group, I want to point out an experiment that Panos did where we thought that our hypothesis going into this was that 3D representations, if we used those to represent the chairs, we were going to do a lot better at grounding human language, because that's what human language is about. It didn't turn out that way. So we used a point cloud representation using the PointNet embedding, or we used just the image with a CNN embedding, or we used both. And now you could, the glass half full version of this is, oh, using both was better. The glass half empty version, though, was that the point clouds were by far the worst, and they didn't help that much on top of the image itself. Now, here's why I'm pointing this out. In some sense, this is a failure case, but my challenge to you guys is I still think it's the case that with good 3D representation, the 3D representation should be a better feature space to ground the language into. And so you can almost turn this data set around, and it's open, it's available to everybody. You can turn the data set around and say, well, let's use it as a test of whether our 3D features are good high-level features for reflecting how people want to talk about these shapes. And what I've seen today makes me kind of optimistic that there exists some high-level features today that would work much better than the PointNet representations did. Okay, we can talk about this more maybe in the discussion period. So it worked pretty well to do the listener, and we did it across two splits of the data, one where it's basically new utterances with previously seen objects, and the other split where it's new objects that you hadn't seen before, and it works decently well for both. Oops, that slide isn't there. Something that I thought was super, super cool when Panos showed it to me was that this listener model transfers with no additional training to new categories that are out of distribution. So you can then take, furniture, beds, lamps, and you can say, okay, how well can this model trained on chairs work for, say, distinguishing beds? And it doesn't work as well as chairs. That's not a big surprise. But usually these sort of deep learning models just completely fall apart if you get that far out of distribution. And so I was really impressed to see that you don't totally fall apart. You're way above chance, even with zero shot, even with no additional training. Now, one of the details here that I think is really interesting is that if you split the utterances according to whether they mention a part or don't mention a part, for chairs, the utterances that don't mention a part, that might say something like lazy boy lounger, are better. That's in the training domain. But for the transfer domains, the ones that do mention a part are actually much better. So the ones that say something like, tapered legs. And so what this is showing you is that the transfer, I think what this is showing is that the transfer really depends on the fact that the language is compositional in terms of the parts. And so as long as the transfer category has some of the same parts, you can get decent transfer by essentially talking about the parts that are shared.
No, just a 5-minute mark.
Cool. Okay, great. Okay. It also works for speakers. Maybe I won't go into this too much, but you can set the task of producing an utterance, and you can ask, how much pragmatics do you need in that production model? It turns out that pragmatics is super useful. And what's really satisfying is that this works for human partners as well. You can take the utterances produced by the model and give them to humans, and humans can, reasonably well pick out which chair you're talking about. Not quite as well as human to human, but still quite well. Okay, so the last thing I want to talk about it brings us back to something that I kind of alluded to at the beginning, which is that part of what we think is awesome about natural language as a source of information about visual representations is that natural language is compositional. And so the compositional structure of language will hopefully help us learn something about the compositional structure of objects and images and scenes. Now, in order to do that, it would make a lot of sense if our semantics model, instead of being like a completely undifferentiated LSTM, were something that explicitly took composition into account. And so we tried this. We first tried building on the neural module networks that Jacob Andreas and company had first introduced, and a lot of papers have followed up using. And these are models that basically, they route the information through a network, which is basically a network of function composition. So it's a lot like the kind of semantics that Montague introduced in formal semantics, a sequence of function applications. Now, unfortunately, this didn't work very well. We tried various versions, and none of them worked much better than what I'm calling the shape glot attention architecture, which is just the LSTM with attention. So that was kind of disappointing. So Shamil Book picked this up, and we decided to try a really different form of composition. Now, remember way back, 15 minutes ago, I showed you this case of redundant modifiers, and I said, let's just assume that they compose by multiplication because it's simple. So it turns out that composing by multiplication is equivalent to, in classical logic, composing by conjunction. It's blue and it's small and it's a pin. And on the face of it, that doesn't seem like a rich enough composition rule to cover natural language. But there's this thread of reasoning in philosophy and linguistics where people have tried to work out how far you can go with just conjunction and realize that you can get really, really far with conjunction. This is called a conjunctivist event semantics. And so in particular, as long as you have different events, or think of them as regions for the moment, in the input, and you route them differently to the different words. So each word is going to be basically just a predicate, and then you're going to compose them by conjunction. But the events that get routed into the predicates are going to be different. So for instance, red and circle both get the red circle, green and square both end up getting the green square, and above gets the red circle and the green square. Then if you just verify that each of those predicates is true, then you'll have a good semantics for this sentence. Okay, so if we want to do this in a modern way, one, we have to relax everything to make it differentiable. And two, we have to do that in a way where we can say something about how to route the events to the appropriate word meanings. But the payoff is every word is just a classifier, right? And we compose them just by multiplication. So we just generalize this idea. Okay, I know I'm running short on time, but the bottom line here is it actually works really well. So the neural event semantics, which is this relaxed version of conjunctivist semantics, actually gives us, by a pretty significant margin, a state of the art for this chairs data set. So we're now at 85%, which is above the 81 or 82% that we got before with the LSTM. Turns out also going to ResNet instead of BGG is good, but that's just model capacity. And so for both the chairs reference task and the zero-shot transfer task, doing this conjunctivist event semantics actually gives you better performance and significantly better generalization. Okay, I don't really have a ton of time to talk about this. You can kind of introspect about what the words mean, and you can look at sort of the systematicity of the behavior here. But maybe the takeaway here is that by making stronger assumptions about the semantics and how it composes, you get better generalization. And that hopefully, and I don't have evidence for this, kind of is something that you can then use to constrain the visual representations further to map onto that kind of compositional structure. Okay, thank you all very much. That is all.
Thank you, Noah. This was beautiful, really inspiring and thought-provoking. I think you mentioned a couple of super relevant things to this workshop, right? Among others, I think this concept of using these tests as a measure of how useful the 3D representations we have is for tasks, and language can be kind of a way to ground that or answer that question. And something that kind of came up to mind as you were talking about this and was that recently there's a very powerful model that ties together like images and text, right? The clip, you've probably seen it, used. And any thoughts on that? Because here's something that I recently saw in a talk, right, in ICCV. I saw that people were using clip to generate they're pushing clip representations to a generative model and generated shapes. And then when you fit in things like children drawings, you might get drawings that look like they were drawn by children, but they might also a lot of times be drawings of children. And this kind of ambiguity, can easily come up in this compositionality framework. Any thoughts on that?
Yeah, absolutely. I mean, first a comment about, kind of clip and how it fits into what I described. Part of the reason I threw in that like very side note about mutual information lower bounds is that clip is exactly optimizing the info NCE loss between, basically captions, descriptions and images. And so really you can think of clip as exactly the semantics that I was talking about, trained exactly the, L0 only kind of way, where the other objects, if you sample the other objects uniformly from the data set, right? So the distractors are sampled uniformly, those are the negatives. And so I think there is a very nice parallel here. So, one point is clip probably needs to think more carefully about why the utterances are generated. So in fact, those utterances come from just like taking random text on the internet that occurs near images. And so it's a very weak kind of purpose in some sense. And so I think, you could do a lot better if you took into account in some sense the topic that the text was talking about for the image. The other point is more about kind of, I think, the 3D, well, there's two other points. The ambiguity, I think, just you're right. And taking into account a little bit more what the utterance is for will help disambiguate some of those things, right? A drawing by a child and a drawing of a child and a child drawing are going to be, appropriate reference for child drawing in quite different contexts, right? So that's one thing. But for this group, I would say like, okay, probably, actually, I'm 100% sure people are thinking about this already, but what happens when you start thinking about things like clip for 3D shape as opposed to just, flat images? I think it gets really interesting, particularly since, as we showed, there's a lot of nuance that only shows up in the right contexts. And so the 3D version of clip, I think, can't be done fully out of context. It needs to be done in some more nuanced context where you'll have some reason to talk about the details of the structure. So that's maybe my most important takeaway there.
Yeah, that's really interesting. We got a couple of questions for you. One is, but maybe one, if I can steal the stage for one more question, I'd ask, what about, when when you introduce concepts that are becoming more and more vague, right? And then this listener part of, if I talk about chairs or familiar structures, or, that blue pin, right, is something that I could say, well, everyone knows what blue is, everyone knows what's a pin, so I can just kind of enrich my description with those things. But if I just would try to describe, things I've never seen before, and I know the listener is completely unfamiliar with, I guess some medical imaging can come to mind in that context. Would that still behave in a similar way?
Yeah, so it turns out that it does behave in a largely similar way. So there's a whole line of psycholinguistics work going back decades. Herb Clark did a lot of this. A bunch of people did a lot of this, where essentially you start with shapes that are hard to talk about. So Herb Clark did this using these crazy tangrams that were sort of vaguely humanoid-like, but not really. And then you look at how do people refer to these and how do the conventions form over repeated interactions? And what turns out to happen is basically people have a lot of linguistic resources at their disposal to talk, in a kind of like imperfect way about the same thing. And so they'll start out with very long descriptions that I think you can think of metaphorically as just exactly like a whole bunch of tries, to provide a lot of redundancy in case you're not quite getting it across. If you then are interacting with the same partner with respect to the same domain multiple times, you'll start to shorten those descriptions as you kind of like, zero in on the effective ones, and you'll form these ad hoc conventions. And so my take is that it is actually very, very similar, with the caveat that the starting point is, the meanings are much less precise. And as long as you're dealing with real valued meanings, that's okay. They're just like farther from 0 and 1.
That's really great. I have another question for you, and so from Srinath, who's asking, which representation do you think would be better for grounding language instead of point cloud? What would be the properties of such a representation?
That's such a good question. In some sense, we should maybe mostly save this for the panel discussion, because I want to hear what other people have to say. I think what's interesting to me is that it's clear you need to have the ability to refer to parts, at least somewhat, but that's not enough. You also need kind of like geometric modifiers. When we do this with textured things, of course, people talk about color and texture, thinness and bumpiness. And so, I've always really liked the kind of heat kernel based, the Laplacian based representations in terms of functions. And I sort of thought that they were a no-go, although the talk this morning kind of made me think again and think, oh, maybe the right version of this will actually have a nice, kind of basically Taylor expansion that has the right features. Yeah, I don't know. I would love to hear what everybody else thinks.
That's interesting. Maybe on that, like, do you have a sense of why point clouds were particularly bad as a representation?
This is a really good question, and I don't know. I'm not sure if Leo is still here, but my take on it was basically just, this was a number of years ago now, and they were kind of noisy and kind of imprecise, so they didn't actually capture the fine-grained geometric details that we were able to elicit from the language. Just because, like there was a trade-off back, I mean, there still is, but back then there was a big trade-off between how many points you use, so what's the, the spatial frequency that you can get, and the ability to actually do anything. And so they were trained at a fixed, number of random points. And I think that just didn't fully capture like the details that needed to be there for this language to ground out. Now, whether there was some version where we just like radically upsample the points or more strategically sample the points, or whether point clouds as a representation were just not good, I don't know. Again, we should all talk about this, because I think you guys know the answer to this probably.
We'll ask our experts over the panel. So thanks a lot, Noah. This was fantastic, and we'll meet you again shortly.
Very good. My pleasure.
I'll pass on the mic to Shubham to introduce our next and last speaker before the panel.
Yeah, thanks again, Noah, for a great talk. Yeah, so our next speaker is Katerina. Katerina, if you could just share your screen so we can make sure things are working before we introduce you. Also, I think you're muted, so if you could also unmute and just say something. So.
Yes, hi everyone.
Hi. Yes, so we see the slide and okay, yeah, perfect. Now we see the presentation as well. So yeah, it's a great pleasure to have Katerina for our last talk of the day. Katerina is an assistant professor in the machine learning department at CMU. And before this, she was a postdoc at UC Berkeley and also at Google Research. So I remember as a grad student, Katerina did a lot of amazing work on tracking and detection in videos. And then while at Berkeley, she wrote some of the foundational papers on learning-based prediction models for sort of motion and videos. And I think over the last few years, her group at CMU has really taken a lead on how 3D representations can help in context of these prediction problems and sort of even be useful for interaction down the line. On a personal note, I think I've had the pleasure of talking to Katerina often enough, and what really stands out is this unique mix of insights about what's ecologically plausible ways of learning and really deep technical insights on how to operationalize this for important problems. So yeah, I'm really excited about hearing what she has to say today. And just a logistic reminder, I'll maybe prompt you in 25 minutes saying that you have 5 more minutes.
Yes, I'll try to keep it short. I know the panel starts at 5. Yeah, thank you, Shaban, for your sweet introduction. What great questions we heard from the previous talks about what is the right 3D representations. I just want to jump directly on the, of course, the nerve resolution and the implicit function resolution, and what the great results we get with test time optimization. Even from a single video, we can learn a nice 3D model for the object, right? I don't have the recent like NeurIPS 21 papers on this, but I mean, you can imagine forward. Now, what is the right 3D representation? I mean, one thing that I'm going to hint at the end of the talk is maybe it is not that important if it's an implicit function or it's a voxel or something, as long as there's modularity and compositionality in the representation. Maybe this is more important than the details of how the rendering is done and so on. Now, starting from those representations, I just want to point out that these works go through 3D for the sake of graphics, essentially. We want to render beautiful images. We want to have very accurate 3D occupancies, which of course is very task relevant for augmented reality and cleaning a house and so on. It's very important to get the 3D representation of the house. But some questions we're going to ask is, how can 3D help on language grounding that Noah mentioned in the previous talk? And language grounding essentially is also object detection, because you ground a single noun, or you ground a particular, okay, look at this particular person with a black shirt. So how can we use 3D as a bottleneck for us to do better and easier visual parsing of the scene? Essentially, this is what we're going to discuss. Yeah, so here is Rod. This is a controversial statement that says that internal models, which are complete representations of the external environment, besides being impossible to obtain, are not at all necessary for agents to act in a competent manner. So Rod here is trying to go against complete internal models. Well, it may just be that, yes, of course, the agent is going to pay attention on different things, and different parts of the scene will be different from different tasks. But what I see the trend is that we do model more and more, right? And we do try to be generative whenever we can. And NERF is and all these nice recent lines of work do hint on was that direction. Now, one earlier work we had was on do not commit on a shape and color and just try to live in 3D with features. And just try to map images to 3D feature maps as opposed to 3D occupancies or, texture maps and so on. And then just have these features there and then train them end-to-end for your end task. And the end task can be 3D object detection or tracking or language grounding, or you want to render the features and predict something, that's fine too. And predict images, and backpropagate. So the feature maps have 4 dimensions, 3 spatial and 1 is the features. Height by width by depth by number of channels. And these networks essentially, this fish tank, my student who introduced those in CVPR 2019, these networks essentially operate as if they do SLAM in the heart of the network. They take a bunch of images as input that can be RGB or RGBD, and they aggregate them into a 3D feature map. As I said, they have a 3-dimensional latent state, 3 spatial dimensions and 1 feature dimension, and there is explicitly GoMotion estimation for aggregation, which is, of course, what we do now with jointly optimize camera poses and assemble the 3D shape, right? And these representations were trained, they are not a particular for a specific scene. You train them across scenes, right? The condition on the visual features of the scene. You can train them for view prediction. You have a query viewpoint for a target camera viewpoint, and then you ask your network to predict what it's going to see, and then the network uses the mental camera and puts the mental camera in the right place and renders the 3D feature map from this particular viewpoint, right? And then you can just optimize with just predicting views, just trying to guess how things are going to look from different viewpoints. Now, once you finish training, then from a single image, you can run it forward in the network and map it to a 3D feature map of the scene. And by 3D feature map, we don't mean the depth map of the visible pixels, we mean all features that are there, even in the dark side of the objects, the sides that we don't actually see. And there is a clear benefit coming from representing the 3D feature, essentially the space in 3D in the bottleneck of the network, and that clear benefit shows in the generalizations of this network. So here we're showing if we train only on those scenes, only on scenes that have 2 objects, and you test on scenes with multiple objects. So this is just 3 different frames that I'm showing. And we'll compare now, this is GRNN with a network that also is trained for view prediction, but doesn't have a 3D bottleneck. And as you see, then it doesn't have the combinatorial generalization that we humans have. It doesn't see multiple objects, it still sees 2 objects, right? But the inductive bias, these architectural inductive biases, through this sum projection and 3D convolutions of our network, is able to allow, to generalize across number of objects during view prediction. Now, to handle photorealistic scenes, instead of predicting image pixels, you can predict feature maps and then maximize the point-wise or pixel-wise contrastive loss in 2D or in 3D. And what happens is that we have now here 2 networks. One is this geometry-aware recurrent network that I discussed that takes images, lifts them in 3D and aggregates them. And the other is the 2D short network that operates on the target view and featureizes it. And they are both trained concurrently to maximize this contrastive loss. And here is the same thing in 3D. If you want to do voxel-wise contrastive matching, then you need to lift the query view into the 3D again using the same encoder. So how is this different than point contrast? Point contrast essentially takes 2 views that with a known camera pose and try to, using triangulation, tries to figure out which pixels of the 2 views are corresponding, and says the features of those pixels should be similar and non-matching pixel features should be far away in the embedding space. So here we directly operate on a 3D feature space, not 2D. But the most, so basically that's why you see these 3D dimensional cubes. But the most important thing is that you can query about things that are actually not co-visible in both views. You can query about 3D content that may be visible only in one view and imagined in the other view, or even about 3D content that is not visible in any of the 2 views, but that the network has learned to essentially paint. So that's the difference. So now that you have built this 3D feature map, okay, that tries to mimic the 3D world, and it's essentially a 3D grid where every grid location has a feature vector that represents the appearance and geometry of that part of the scene. You can put a camera wherever you like and render it to see what it has as content. And here I just showed a video where we put the camera in the overhead and just see here, things emerge that you haven't, annotated, like the lines of the sidewalks, right, as a special feature, or the curve of the road and so on. And the hope is that through this pre-training scheme of view prediction, you will learn features. This is going to be the self-supervised, let's say, task that will pre-train the features so that labels, you will need very few labels to do well on your downstream task. Now, 3D, those 3D feature grids are, every grid location is very fat because otherwise they don't fit in the GPU memory, even in the latest GPUs. And of course, the better spatial resolution you have, the better you do. So one thing we did recently is to, instead of using this 3D feature grid, we use implicit functions in the following way. We had multiple functions, or basically there was one function that was conditioned on that feature vector of the 3D grid, and would take also an offset, a continuous offset, and would learn some parameters to map that continuous location into the corresponding occupancy 0, 1 value and the corresponding feature vector, okay, because we care about the features as well as the occupancy. And again, this is trained end-to-end through rendering and backpropagation. And this solves, like the results are much, much better with, having resolved this, the problem of discretization. All the training is exactly the same. It's just the only difference is that you sample now locations in the scene, you find their feature vectors and their occupancies using the implicit functions in the cart on the network, and the rest stays the same. So as you can see, using those coconuts, essentially contrastive continuous scene representations, you do better than the 3D point contrast, learning 3D representations with contrastive loss, as well as our previous work that uses only fat voxel features. And again, using them as pre-training for a 3D object detector, you see you do dramatically better than not pre-training your features. Okay. So here we use the VoteNet as our 3D detector. And of course, so far we've applying these networks into whole scenes. Of course, you can apply them also in objects and get these nice, you know, reconstructions as well as color renderings, just like NERF out. This is the same pretty much machinery. Now disentangling object shape and style, the same way as in the 2D, we can do also in 3D. Essentially, the disentangling here is, I mean, the texture map and the depth map. So why such disentanglement is important? Because if your downstream track is object recognition or object classification, then you don't need to see a particular object category in all possible colors. You just need to see it in once and ground its label on the shape as opposed to the texture. So, so this is in ICLR 2021, where we take our 3D feature maps and essentially we use adaptive distance normalization as an architectural bias to separate them into 1D style vector and 4D content vector. And then in a completely unsupervised way, this is just an autoencoder with those adaptive distance normalization layers. And and then you can quantize the content into your dictionary. You create your shape dictionary. You can quantize the style into another dictionary, and you know, use those representations for grounding of specific language terms. So we have the style is 1D, and the content is the 4-dimensional XYZ and the number of channels. So because I read on the workshop that is also about, you know, you find these 3D representations for shape and for texture, and you do care to find them, to make them relevant for the downstream task. So here is one downstream track we have used them on, is about visual question answering. And you do see that by using this self-supervision, by looking around in the scene to build those 3D feature maps, and by quantizing them into objects with very few object labels, and creating this style and shape dictionaries by essentially doing exactly what I said with this autoencoder with adaptive distance normalization layers to separate, disentangle 3D features into shape and style, then you can solve VQA with very, very few labels compared to not doing that or operating on a 2D representation, okay? So what is the benefit here? The benefit is because you have these very simple scenes. So I'm going to show you clever scenes and cater scenes where the only thing you need is you take the image, you get the 3D feature map of the scene, you can apply your detector, and the detector will work under occlusions because it's in 3D and it's assisted very much by this pre-training, this view predictive pre-training. Essentially, your visual parsing gives you this ideal super disentangled representation in terms of objects. There are 3D locations, there are shapes and styles, okay? And by the way, even the poses can be read from this representation because we just take the shape of each one, because our shape prototypes, which I didn't mention, are 4-dimensional. So by matching them in a rotation-aware manner to the instances, you can even read off the pose of the object, right? So this is like ideal. This is exactly what we would like, let's say, visual systems to provide. Unfortunately, not in these toy clever scenes, but in very entangled and complex, arbitrary complex scenes, right? But here I'm showing about this level of visual complexity. So once your visual representation is so disentangled and modular and compositional, the only thing you need to do to potentially ground language is you map it into a program, right, of what modules I need to apply to my visual representation. And these modules operate on specific features. For example, the relate operates only on the locations. So you can learn left and right, in front and behind with very few training examples. And the shape, find shape will only operate on the shape descriptor and will not worry at all about the style. And query style will only worry about the style descriptor, not about the shape. So exploiting this feature disentanglement, you can essentially save a lot on labels, all right? So here, first we need to say, find the broccoli, find shape broccoli, and you take your objects in the scene and you compare them using this rotation aware manner to the broccoli essentially entry in your dictionary. And then once you find it, you need to find which one is to the right of the broccoli by looking only at the 3D locations, okay? And then you need to find, okay, what is the color of that object that I found, which is very hard to do using, end-to-end attention models between image and the question that are, kind of black box and so on. They are not going to learn to disentangle automatically, okay? You will require a lot of training data to do well in that case. And here is you query the style and you figure out that it's red. And this is not the only thing you can do. I mean, you can ask questions, complex questions. You can detect objects with novel combinations of color and shape, like this blue broccoli and so on, novel poses, novel arrangements, exactly because your encoder is so strong and spits out this nice disentangled configuration, and the encoder generalizes under object rearrangements. Now, okay, so here's some results. We have added some, extra objects in look like food in Clever, and just showing here some quantitative results that show that our full model can do very well, particularly in very, very few training examples, 10, 25, 50, and 100, compared to previous models, or one previous model that we helped by adding our disentanglement in there, all right? So you take the 2D features and you try to disentangle them into style and shape using adaptive instance normalization. And you do also very well in one-shot test set, because it always depends how well a method does is how well you have split the train and test sets. We never talk about this explicitly, but how similar is the test to the train, and what type of factors you change to make the test set similar or dissimilar to your training set matters. So the more disentangled your representation that comes out of your encoder, the better you will do on novel combinations and things that you haven't seen before, let's say. Now the question is, what happens beyond those scenes? So here, okay, we have a scene. We can go to 3D with this end-to-end differentiable network. We can detect the objects, compare them to dictionaries, and parse them into, okay, here's the object with this particular pose. Another thing, since we're talking about 3D shape representations, is that instead of detecting a concept, you can also generate a concept. Like, for example, now to you, I can talk to you about a blue broccoli, and you don't see one, but you can imagine it. So this is exactly also what we did. You can consider an embodied agent that looks around the scene and that has strong supervision. It has access to the parse tree of a particular utterance. The scenes are tagged with descriptions, and it can learn to map language, like green rubber cylinder, to the 3D feature map of this particular object. And the same thing can do to the blue ball, or any noun phrase. Now it can be mapped to the corresponding 3D feature map of the object. And the left to or right of and so on can be mapped to the 3D offset. And because you have now these generative models of nouns and special representations, I can talk to you about things, and you can generate and could try to imagine what I'm talking to you about in 3D, not in 2D. And we showed you can do much better to detect when the person is saying things that doesn't make sense. For example, when the person talks about the ball inside the cell phone, or when the person says A to the left of B, B to the left of C, and C to the left of A, and some configuration that essentially is not realizable. A 2D model will be able to come up with some explanation, but in 3D, because you exploit the constraints of the 3D space, you actually can detect those implausible sentences. Now, and this is the last part of the talk because it's 4:50. So here you see again the benefits of operating in the 3D space for language grounding. You can give me super complicated sentences, and I will sample from my generative model, trying to make the scene that you're talking to me about. And if I don't manage, if I sample, but I don't manage to find the configuration then I'll tell to you that, oh, I think this is implausible. I don't think this configuration you're describing actually can be realized, which a 2D model, actually we have comparison results in the paper, has a big gap in performance in doing that because it cannot model occlusions easily. Now the big problem is the following. A lot of the results I showed was in worlds like to the left, which is a clever worlds where you have objects. The objects can be complicated, but they're far away from one another, right? So as long as things are far away from one another, then just by going to 3D immediately, even if you see the point clouds, even if you just see the point cloud from one image, you can easily detect the objects. They're far away from one another, and there's a clear plane, which is actually the table where the objects sit. Now, the truth is that this is not how the world looks like. The world looks like more to the right, where objects are on top of one another. They are not super easy to disentangle, right? And although to the left, of course, you can just write a paper by saying, look, I'm going to go to 3D and look at depth, and just, of course, segmentation of the object becomes so much easier, okay? Which this is not what I discussed, by the way. I discussed about view prediction and completion. To the right, you cannot actually have that benefit, right? Let's alone that everything is really flat. So the question is, how can we use our 3D inductive biases in examples like to the right as opposed to the left? So these are very preliminary, and I just need 2 minutes to describe this. Some efforts that we have tried recently is using generative networks, curriculum in generative networks in the following way. First, we don't try to parse the full plate at once. We just try to parse extremely simple shapes like surfaces or identical legs and so on. And we learn sets of encoders and decoders that can capture those primitives, okay? And then at test time, you'll show me something that is extremely out of distribution. Very, very complicated table here compared to what I was trained on. And I should be able to parse it into the parse just by gradient descent using my part bottleneck. So basically, I mean, here, his work, this is, here is a first year CMU PhD student. What I learned from his work is that the importance of the bottleneck is not on being 3D, but is rather on being modular, essentially. So what he shows here, well, he trains on those super simple, shapes that are surfaces or pairs of cylinders or either quadruplets, okay? And then you can show to the network something very complex. And in the 2 first cases are complete point clouds. They're as if you've seen it from all the viewpoints. The last case is incomplete from only one viewpoint. And you try to parse, you feed those to the network. And of course, the network, encoder, decoder, you just run it. There's no training here. You just run it and you see that the result is not great. It is segmented, but actually doesn't respect the initial shape. You see here that the holes have been completed, has been filled up and so on. But if you do gradient descent on the encoder and you say, think how you can use the parts, try to sample, search over how you can combine the primitives you've learned to make up the shapes, then very good segmentations come up. Then as the network is thinking and through gradient descent thinking, different decompositions will show up. And here I just have some, so this is something that looks very, very different than what was given at training time. A very incomplete point cloud that has nothing to do with how the complete parts were looking at training time. And still the network is trying to piece it up out of parts that it has seen before. So this is some, let's say, direction that we're exploring right now of how we can add in the bottleneck, not just 3D, like not just go from image to 3D in that convolutional, fully convolutional manner, but rather through, entity-centric, essentially, bottlenecks. And I'm going to close now. So what did we discuss? I discussed about 3D scene representations learned by view prediction. And we showed how the features we learned, the representations are useful for detection, but also for language grounding. And last, maybe we give a small hint on the importance of modularity for the representation to be able to explain things that it has not seen before. Thank you very much again for your invitation, and let me know if you have any questions. here are the students that actually are behind the work that I present.
Yeah, thanks, Katerina, for a great talk. I think, members, if you have any questions, please feel free to post in the chat. And meanwhile, I had one question. Well, you started with a quote from Rod Brooks against trying to build full representations, but then a lot of the work was actually using reconstruction and pixel generation as the learning signal, which of course is sort of pursuing full representations. But when we try to do reconstruction, for instance, the handle of the door has very few pixels, or sort of the button on a TV remote has very few pixels. And do you feel these kind of objectives on their own would miss out on all these details and not be very useful for any interaction tasks downstream? Or
yeah, great question. Well, we don't need to weight our loss based on a number of pixels or a number of points on the 3D scene. We can value it on the number of entities. So every entity gets one value. So whether you are a fat wall, like very, very big wall, you're a big wall, and you're a tiny little door handle, or you're an even tiny key on the keyboard, you're going to get equal weight. So we can change our loss like this, right? So we can reweight it based on the surface. And actually, this hints, though, in another very important question, which is when I'm an embodied agent and I train my generation and I want to understand the world by generating it, I choose where to pay attention and I choose where I'm going to be trained and what I'm going to ignore. And right now, we're not putting this in the question whatsoever. And it might be as an important of a research problem as all these nice techniques or differential rendering that we're discussing and the attentions in the architecture and so on. Yes, so I'm pretty sure it's an insanely crucial point that we haven't touched. These representations ideally should be trained end-to-end for your end task, as opposed to by having this agent decide where to train and where not to train.
Okay, thanks. Actually, one more question on the work in the middle, which was talking about language-guided VQA. So you had the distinction between the clever world in terms of the visual part, the clever world versus the real world. And I also feel the same analogy can be drawn with respect to the language, that it was a very clever-like language with explicit composition and passing known, versus the real world language, which is much more messy. And just your thoughts on how can we use these kind of representations in context of more natural utterances, and will we need to rethink some machinery?
Great, yeah, so this is a great point. Now, somehow I feel that this is a much easier problem than a visual problem because first of all, the NLP community has come up with some amazing ideas like paraphrasing. So I tell you, I generate programmatically things like pick up the blue cup, and then you go and you crowdsource it. You say, give me different ways you would say it, and you say, look at the cup, it's blue, pick it up, or look at the blue cup, pick it up. Can you see the blue cup, pick it up, and so on. So you can create insane amount of training data through paraphrasing. Now, I think another very, very important point you're making is I don't think the program can be predicted from the utterance without looking at the scene, because the co-references of it, or look at that, or look at this big mess and so on can be very fast resolved by looking at the scene. But yes, these people have done that. They do predict programs by looking at the scene as well. But I do like, I must say, between end-to-end attention and programmatic through programs and more modular, mapping from language to vision, I do like the modular approach much better. Yeah.
Okay, great. Yeah, thanks again, Katerina, for a very nice talk. I think we're almost at the time for the panel session, so I'll hand it over to Gordon, who will be moderating the panel session. Yeah, so Gordon, feel free to take over.
Well, thank you. Thanks, first of all, to the organizers for doing a fantastic job with the second workshop this year. I think it was a great success, and we've heard lots of fantastic invited talks, and the poster session was a lot of fun. I also wanted to thank all the speakers for giving us different perspectives on this exciting topic. And we have most of them here for the panel today. I prepared a few questions. but I'd like this to be fairly interactive. It's a fairly small round, so we're going to start with some introductions again, because some of you may have not been here the whole day. So what I'd love to do first is go around for the speakers and the panelists and just give us a 1-minute pitch on, what do you think is the grand challenge in this area of scene representations, and what is the most exciting idea that you've heard of in this general area over the last, I don't know, year or so. Okay, so let's maybe keep it to 1 minute. Tell us a little bit about your background again, and just tell us what you think is the biggest challenge moving forward, and what's the coolest idea you've heard recently. Who wants to start? Okay, then maybe I'll go ahead and start. I have a biased opinion, but I would say the coolest idea, I've heard recently, it is really this idea that you can train 3D multi-view consistent representations from 2D data. This doesn't seem intuitive because most of 3D computer vision, we reconstruct 3D scenes from multi-view input images, but the idea of using unstructured 2D image data sets like CellUp-A, FFHQ, using 3D GANs, for example, and adversarial training to train a multi-view consistent 3D representation, that was something that just blew me away about last year or so when I kind of understood how that works better. But I think that one of the most challenging things moving forward is, there are so many different challenges. I think everybody of us can name something different. I think some of the biggest challenges are related to figuring out how to set up neural network architectures that have a very high capacity in representing high fidelity signals that are also computationally efficient and that can span multiple different areas, including graphics, the inverse process and vision, but also maybe all the way over to language and other domains to enable us to learn truly multimodal representations. So that's just my personal opinion, and I'll hand it over to the next speaker. Who would like to say something? Maybe Katerina, you just went last. Do you have any opinions?
Yes, I do have an opinion. So what is the cool idea? Well, I've heard so many cool ideas. Deva was talking about his SARM and Visser papers just in the other workshop. In general, cool ideas, yes, learning 3D from 2D, that sounds great. Let me start from what I think is the one big few challenges going forward. Okay. One challenge that I see is that I don't think we know what are the right architectures to take a scene and do binding inside. Like you detect the parts, and the parts assemble the objects, and the objects assemble the scene. And then there's also feedback loop. And as we go up, then there's also feedback. And as the big concepts light up, for example, the dining table, then you go up and you update your representation and so on. So we're very good at model building, going around, building the nerf and so on. But the truth is that this is great, but at test time, we also need to get it from a single image. How can this single image processing access all these previous models and that we've learned before, right? I think this architecture is still to be, discovered. There is the GLOM paper from Jeff Hinton, but it's just a paper. There's no implementation, right? So I don't think we have a way to do analysis by synthesis, coming on the image, finding the 3D modular structure through some iterative thinking and so on. I don't think this architecture exists. So I think this is one problem.
Okay, that's great.
Now, how do we found this, hierarchy of concepts? What is the right curriculum? What is the right supervision? How can we make it task relevant, as Shaban mentioned? That's another open problem. But yeah, cool ideas. I have a lot of papers that I read that I'm like super blown away, which I have difficulty now remembering titles to mention, so I'm afraid to mention.
That's fine. Don't worry about it. So, but just to paraphrase it, I think you actually phrased two two big challenges in one. One is, how do we understand the structure of the scene that we're learning and not just some, kind of a meaningless model, let's say, that we can use for novel view synthesis. But the other that you hinted at is actually also how do we generalize across those learned priors that we can then use for example, single scene reconstruction, right? And we'll talk about this more a little bit later. So for now, maybe let's hand it over to the next panelist. Dima, you're next on my list. I'm just going to write down my list here now.
Sure. Yeah, thanks. So as far as greatest challenge is sort of in the area that I've been working on the past few years, I think we've done a lot of work on geometry, on learning and predicting and ingesting geometry in neural networks, but sort of another thing that people care about is topology, right? And I think that is very much an underexplored area across most of the methods that are coming out now in this general area. I think just even something as simple as predicting some sort of geometric primitives and varying the number of primitives, I think that already is kind of an open problem, and there's no really clear way to do that. And I think this is kind of one of the fundamental issues of being able to truly predict sort of discrete structures and things like that. And I think it's a very challenging problem, right? Because fundamentally, topology deals with discrete changes in discrete things, which and it's not entirely clear how to make that compatible with the smooth things like gradient descent and that kind of optimization. So I think that's one of the biggest challenges in my opinion. One of the things I'm most excited about is there's been a lot of recent work kind of in these hybrid representations that try to take these neural type, implicit type models and endow them with some sort of more tangible explicit controls. I think that's one of the things that I've been looking at recently, and I think there's a lot of exciting work there because I think it's very impressive what all these neural implicit things can do, and the next step is making them actually useful for the downstream applications that we know and love. And I think it'll take a while until kind of conventional graphics CAD modeling tools are able to entirely deal with these neural representations. So making the representations more editable, given the tools we have now, is an exciting direction.
Fantastic, thank you. So editability is also like that was one of the big challenges we actually discussed last year, to be a big challenge, and it still is a big challenge. So it's good to know. Okay, great, thank you. Andrea, I think you're next on my list here.
Okay. Right. I mean, it's difficult to pinpoint one single or one major contribution or great things that has happened recently. There are so many to choose from, but maybe what I thought is particularly interesting is the idea that 3D understanding is coming back, but it's coming back not to replace the work on semantics, but rather to work together with it. And in particular, I think 3D understanding gives us an opportunity of explaining images and videos in much more detail. And now that might seem counterintuitive, but I believe that's the key to be able to make self-supervision or unsupervised learning work, and therefore eventually also learning high-level semantics. So, when computer vision has moved to machine learning and learning semantics, we took basically gigantic shortcuts. We didn't try to explain the images in detail anymore. We forgot about their 3D structure. We almost forgot about the 2D-dimensional structure, but that was possible because we had this sort of external signal that was the supervision that could allow us to take these shortcuts, and it would still make sense for the machine to try to learn that big jump, if you like. But when you remove that, then it's necessary for the machine to make much more use of the actual raw data that it sees. And I think geometry is absolutely essential to be able to do that. So I think that's great that now geometry is coming back in the area of deep learning, where we also have the semantics. And eventually, by combining these two things together, maybe you're going to get machines that are able to learn from raw data much better than before. So that's one thing. In terms of challenges, I mean, there are so many to pick from, but there are some that are very practical, I think, but are a very big bottleneck at the moment. One is speed. So a lot of the stuff we discussed today, for example, NERF, they take for freaking ever to learn anything. So it might take you days even sometimes to process a single video. And if you want to learn semantics, of course, we learn to process thousands of those videos, maybe millions of those videos. So we need to work on that. So we need not just to make the rendering faster, but we need to make the learning of this representation much faster. So they're great, but they're just probably too slow to scale really at the moment, I think. And there are many things that we really didn't discuss too much in the workshop, I guess. And another one, which is important, not just covering shape and color and appearance, but also dynamics. So we have deformable objects, we have people, animals, things that move, they change in complex ways over time. And we need also to be able to understand that much better. So of course, there are versions of NERF that can do that to some extent, but not at the level of learning a dynamic object category, for example, like what is a human, what is an animal, how are they related, how they can move, what is the space of possible changes that they can be subject to, et cetera, et cetera. And yeah, and connected to that, there is also physics, of course, which we didn't touch almost at all, right? So not just things can have a volume, and a shape, and an appearance, and a set of possible motions, but they actually have a mass and physical interactions. And that is also something that should get into these models of 3D understanding we're building on the world. So it's not just a bunch of empty shells. It's shells with stuff inside, and we need to understand that as well.
Fantastic. Let's get back to that maybe a little bit later in the panel also. I think this is a fantastic point. Okay, who's next? Noah, what do you think?
Sure, let's see, I guess. Starting from the things that feel more like about 3D representation, and I think people have mentioned most of these, but the coolest thing that I feel like has happened in the last little bit that I got to learn updates on today is basically taking the old idea that like functions are a good representation of the visual world and saying, oh, and neural nets can be functions. And I'm pretty impressed all the different ways people have done that in the last couple of years, and that it's actually worked. That's pretty amazing. I feel like the things that other people have already pointed to, that the problems that poses basically have to do with the fact that like a neural net as a specific representation is difficult because it's not decomposable into pieces. It's kind of like the weights are all intermixed in like completeness, which makes it very hard to do a lot of high level tasks, a lot of editing or recombining. I was going to bring up physics actually, like it's very hard to see how you get a good forward model that doesn't diverge from that. I guess I would say in some sense at a high level, the problem goes all the way back to like, if you look at the PDP books, they were worrying about this problem of, how do you treat the weights, not the activations, as the thing that you learn? And there are these ideas about, weight shipping, which are now what we call hypernetworks. And, in principle, like something like that could be the answer, hypernetworks as a prior over those functions, but they haven't worked super well. And so whether you have to then switch to a fairly different representation, or maybe, get those representations to work at the higher level, the hierarchical level, I'll be interested to see what you all figure out, basically. It's important to me, though, I would say, because I think whatever language points to in these representations, it is probably relatively high level features, which are the kind of, they're the joints along which you would want to be able to remix, like some of the stuff that Katerina was just talking about, actually. And, like, so what's the connection between the implicit representations of scenes and things as functions, and then the representations we need to hook words and sentences and ideas into? That seems like the outstanding challenge to me.
Fantastic. We'll get back to that also in a little bit. Shuran.
Yeah, so I think I'm probably quite biased, and also I think I want to echo what Andrea just said. In terms of future works, I really hope to see more works that's actually trying to learn 3D representation that go beyond just rigid objects. I think there are like so many objects in this world that is not rigid, right? There's deformables, there's articulate objects, and we have seen so many successful stories on like how to learn a good 3D representation for rigid objects. And I'm really curious to see how much of those successful lessons can be borrowed to non-rigid objects, and how much of those things need to be redesigned. And another related thing that I really hope to see in the future, like at least see more, is more self-supervision, and hopefully go beyond just multi-view self-supervision, right? So I think that for example, how we can use like active interactions to provide different ways to as supervision signals. And I think that's particularly important if we start to think about those non-rigid objects. Like for example, you can not really reconstruct a drawer without opening it, right? So there's like, if we think about those objects, we need to think about different ways to get more observations and more supervisions. Yeah, so that's like the two directions I'm thinking about.
Okay, that's great. So I think did I forget anybody? I don't think so, but other co-hosts, feel free to chime in as well. So two topics that were mentioned quite a few times in these ideas is, one is like, how do we learn priors efficiently over function spaces? Let's say we heard about hypernetworks. There's also meta learning. We've seen a lot of conditioning by concatenation or other ways of like trying to learn priors over distributions of functions. Yeah, what's the right way of doing this? You know, what is the right way? I don't know. This is also one of the grand challenges that we discussed last year, but anybody among the panelists, you know, do you have strong opinions on how we should learn priors, or is this something that, you know, we should just explore everything there is? Maybe Andrea, I think you may have some thoughts on this, perhaps.
And my thought is that we don't really know how to do that well, to be honest.
Right.
We have been trying, yeah, as I said, we have been trying different stuff, different things, different approaches in the community, but I didn't see anything that definitely the answer yet. Yeah, it's interesting. So, I mean, of course, I think what you mean by priors here is, you mean we want to learn something about, say, for example, an object category, and then be able to take.
Let's say, you know, we represent an object or a scene by a function that is represented by a neural network. Now we have, you know, many different of these objects that we can learn a function for each. So we want to learn some kind of a prior over the distribution of functions so that we can do things like single view 3D reconstruction, for example, by filling in the missing parts with a prior. We want to do semantic segmentation, or maybe we want to do things where we have very little training data. We want to solve tasks like that from, you know, representations that we learn in other contexts, perhaps like some kind of a transfer learning approach or semi-supervised learning approach. Like, I think being able to generalize across these distributions seems important, and frankly, to me, is one of the biggest promises of this whole, you know, neural network parameterized scene representation area, because now you can tap into those types of tools from the machine learning computer community. But, well, how do we do that efficiently, you know?
I think
again, hard to say, but one thing that we are exploring for sure. So we're trying to be inspired by NLP as effectively and how they model their distributions. They do that quite well, obviously. Of course, in their case, they have a discrete space to work on, which is a space of words and sentences. So, for example, they have these autoregressive models that work very well for modeling distributions, condition distribution, or distribution as such without conditioning. And some of those can be ported to the image space, to this space. Then, I mean, I don't know, you can pick BQ-VAEs or BQ GANs or stuff like that. And so, you know, some of those ideas probably can actually be ported to 3D. It wouldn't be too difficult to port them to 3D. So that's something that is worth exploring. But that's just one possible starting point, I guess. One thing that it seems that for those models to be able to model ambiguity or distributions well, they need to work on a quantized space. So they cannot do that, or usually they don't do that directly on a continuous space. Well, in NLP, you don't need to do it, of course. In Vision, you might have, but it turns out that in Vision, so far at least, we have been having more. I think we have been more successful at doing that by quantizing image or image patches if the goal is to model distribution. So I wonder whether that's something that we need to live with, or if it's just an accident of how things are done currently, and we don't actually require this quantization. So yeah, that's I guess.
Thank you. So Noah raised his hand a little while ago. Leo, I'll get back to you in a second as well. Noah, do you have any opinions on this?
Leo is probably more on topic, but when we start talking about priors on functions, I guess, you know, my background as a Bayesian kicks in, and I start to ask myself, well, what about even the simpler function before you get to full priors, which is, can you capture uncertainty? And I think like a key Achilles heel of a lot of deep learning models is that they are terrible at capturing extrapolative uncertainty, right? You know, any kind of uncertainty, just a little bit outside of their training regime. And so maybe like, I don't know how to do priors over such complicated spaces of, neurally represented functions, but even just starting by figuring out how to have really well calibrated uncertainty might be an interesting first step.
Absolutely. That's a great thought. Leo, sorry, we cut you off.
No problem. Yeah, I had a comment that relates to what Noah said earlier and also to what Andrea just said. I think part of the issue we face is that the knowledge in a deep net is encoded in a very opaque way into these weights. And these weights are not canonical. Essentially the same entity, the same object, the same learning can be represented in many, many, many different ways. And this makes it very hard to share this knowledge, to transfer it. I think our deep nets operate in splendid isolation and don't communicate with other deep nets, which would force a common and a shareable representation. And maybe that's something else we can learn from NLP, not just the techniques, but the notion of tokenizing for the sake of communication, so that somehow these priors that I learn from something can be shared to others. I mean, I don't know if there's any studies about how much of children's learning of the visual world depends on communication with parents and others. I mean, maybe no one knows more about this, but I feel somehow having to communicate and to share forces a tokenization. I think also that's a view that Geoff Hinton has espoused. Somehow tokenizing something continuous forces you to make a choice, and then that choice can be communicated to others.
Certainly not an expert on early child education, but having a 2-year-old at home, I have observed that they try by error a lot, falling over, bumping into things. But once they do understand some amount of language, you can actually communicate ideas fairly efficiently, and it seems like a semi-supervised approach where they already have a reasonably good representation of what happens where, and if you tell them something that they will actually mostly remember it.
Also, the fact that you can read them a story and they can imagine what that world is like in their head does mean that language is like, probably not below 1, but somewhere between like, 1.5 and 3 is a very efficient means of getting some high level prior about the scene.
Actually, I have an argument partially against using language. So if you take an animal like, I don't know, a cat or a dog, they can see perfectly well, but they probably don't communicate, in a very sophisticated manner. So I think that shows that you don't actually need language to learn, convincingly good visual systems.
With Andrea. Oh yes, Shuran, go ahead. Sorry.
No problem. I just want to add a little bit about like what kind of to the question of what kind of prior we want to learn. I kind of feel like this is like really depend on the task or the application, the downstream things that you want to do with this representation, and therefore it defines like what kind of prior you want to capture, right? But I think go back to what Leo said. Maybe if we consider like all the downstream tasks, we probably want like a prior that's able to share that can be used for multiple tasks. So maybe that's one way to think about what is like the fundamental prior we want to enforce or let the network learn.
Great. Just to follow up on this, I agree with Andrea. Sharing doesn't mean that we need language to share. We can build modular visual representations simply because of the modularity of the visual world. Like, for example, here you see the tip of the pen, now you don't see it. So, you don't need language to capture that. So modularity and sharing can be there, and the tokenization that you mentioned that we need to tokenize. We don't need one monolithic net. We can just have 1 million different things that attach on different things in the visual scene and communicate and share, and so on and so forth. This I wanted to mention.
And maybe I would like also to clarify, I'm not against tokenization. So I think that may be something which is needed statistically internally for the model. I'm just saying that, that is a little bit orthogonal to the issue of language as a mean of communicating between different beings. That's also tokenized, obviously, but, these two things can exist. I suppose the internal tokenization can exist even without an external tokenization, perhaps.
Okay, Great. One other topic that came up quite a bit is this idea of an inductive bias on the network. So, early scene representation networks typically try to use, 3D agnostic CNNs or other architectures with moderate success on multi-view consistency. We've seen then things that bring inductive biases into these networks, like NERF-like models that have some kind of a density representation perhaps, or some other intermediate representation that creates an inductive bias towards having a 3D structure. So how much inductive bias do we need? Do we want more or do we want less? More seems to over-constrain sometimes the scene, although we have seen actually a couple of examples. For example, one of the earlier talks today, for example, from Yaron, used inductive biases on the density, and he's not here right now, which is unfortunate, but to kind of, create better intermediate representations that are not only more interpretable, but that are probably making it easier for the network to just learn the important parts that it needs to learn. On the other hand, we've seen fairly bias agnostic models in other domains with transformers or maybe in natural language processing that actually do learn the structure of the data almost automatically. So, how much bias do we need or do we want? Also keeping this generalization in mind. Any thoughts on this?
Okay, as a visual scientist, I would say as much as possible, because that's where I can actually use my brain in the design of these biases. Otherwise, I just leave everything to the network and then I'm out of the job in a way. But more seriously, I think they're great if used in moderation. As you said, you don't want to over-constrain the problem. Having said that, especially when it comes to 3D geometry, a lot of it is very low level. So, and we have a very good model of low level 3D geometry, Euclidean geometry, for example. And there is no reason why we shouldn't be using them. I guess some of those things are basically settled. We know how to model geometry mathematically. Why giving that up and not helping the network by somehow injecting some of that already? Now, I know that it's not necessary to have an Euclidean model of the 3D world in your head to actually be able to see and navigate and all that. But it seems like a reasonable starting point at the very least.
Okay, would anybody think that less inductive bias is better?
Well, maybe we can have our cake and eat it too, which is like the evolution of scientific theories. There's a theory, it is useful while it lasts, eventually it gets superseded by something better. So as long as we have a way to overthrow the government once in a while, it's okay, right? So we can use the biases while they're serving our needs and then throw them out when they stop. It seems to me, it seems just impossible to decide this in advance.
Yeah, I think in a perfect world with infinite data with big enough model, like we probably don't need to use this kind of inductive bias, but that we are not in that world, right? So I think having inductive bias will really help in reduce sample efficiencies, make network learns faster and better. And I think that's in particular important for applications like in robotics, right? We don't have that many data that we cannot have like infinite training data. So I think for a very long time, having this kind of prior knowledge like injected into our network will be an important part of making things work.
I could also add, sorry.
Sorry, Andrea, do go ahead.
I was just saying inductive biases are everywhere. In the design of CNN, there's plenty of inductive biases. But what it would be interesting to know is what kind of biases we have, right? We have genetics, we have a couple of, thousands of years, hundreds of thousands of years of evolution, right? That have determined how our visual system actually works, possibly more than that. And when we are born with all these inductive biases in the way we are structured. And it would be nice, it would be very interesting to know which ones are these biases, actually.
Yeah, so exactly following up on that, it would be great if we can add inductive bias that are actually useful as opposed to what we are comfortable with and modeling, for example, right? So we are all very comfortable with 3D, like we really like 3D metric, 3D of scenes and so on, that while we know that, humans operate over glimpses and they don't build a full metric 3D of a scene, despite the fact that we're comfortable with. And at the same time, there are things that potentially humans do well, like modularity and compositionality. Like, for example, look at, you can see every line here of my chair as an isolated entity. And we don't know how to build networks that will see and recognize the self-similarity between those patterns, right? So yeah, so overall, we should try to build inductive biases that match, as Andrea said, what we know humans are good at. To answer to Gordon's point on, the more inductive bias we put, is the less constrained it is. So, for example, with a park bottleneck, we see two things. We see objects that you know well. You don't need inductive bias. When you're in domain, you can be fast and reactive and build extremely, networks with not a lot of conditionality to do the job that you know. But when you are out of distribution, you really want to plan. You really need to think and search of how to explain the new thing that you see in terms of things that you've seen before. So you need both the model building ability and being reactive and expert and excellent on things that are in distribution you're comfortable with.
I want to just be devil's advocate for a second. I kind of spiritually agree with what everybody's saying, but like it can be super hard to build inductive biases into the model for big neural nets in a way that works the way you expect it to. Like, over in NLP, people have time and time again tried to build in some kind of compositionality bias or syntactical bias, and they just eventually give up because it's like, it doesn't work as well as just making the model, bigger and the data bigger. The only thing that sort of like, if works effectively is building in a bias by data augmentation, which is sort of the secret sauce to a lot of like in NLP, but also in like, contrastive representation learning in vision. And so I guess like, do we really think that we're going to be able to figure out how to build in those cool, awesome biases in the model, or should everybody focus on like, just think about the data augmentations, and that's where the biases can come.
I also think Andreas sort of alluded to this, but I think in addition to thinking about building inductive biases, it's important to kind of realize and think about what inductive biases already exist in models that we use kind of regularly, because CNNs have an inductive bias, and I think we don't always remember or think about that so explicitly when designing models. So kind of taking the tools that we're so used to using and thinking carefully about what inductive biases exist there and how can we kind of swap them out for the task at hand is not very important way to think about it.
Yeah, I mean, in the design of NERF, there is a bias that you put your compute UMLP on top of a 3D point, which is registered against the word reference frame. That's a very simple bias. It's a design choice almost, right? You could call that a design choice, but that's very important. Otherwise, then nothing works. Okay, so I mean, there are some biases which are very, very low level in a way, so they don't even look like. I mean, as Dima was just saying, you don't even think about them as biases maybe sometimes, but they are.
Okay, so let me get back to one of the other points that I think you mentioned earlier, which was we haven't really found a good way to incorporate dynamics. Maybe people have modeled dynamics using partial differential equations or other methods for, well, centuries perhaps, but we haven't, or maybe I'm not aware of this, but I haven't seen any really elegant methods of combining these with some of these visual representation networks. I mean, we have seen a ton of work on using graph CNNs, for example, for these kinds of purposes, or graph networks in general. But I haven't seen anything really combining, these types of inductive biases with visual inductive biases. And then the question is then, what's the one representation that could even handle all of this at once, like that we could use to model dynamics in a physically meaningful way, that we can use to induce 3D biases that help us to view synthesis tasks better, and maybe even connect it to a language. Like, is there one model that rules them all? And if yes, what is it?
I mean, there's been works where you have a latent space where an ODE, a neural ODE, describes the dynamics of the system, and then from the latent state, you can sort of generate a 3D representation of the scene. that can be actually at a different resolution than the one that you started from, and also sample unobserved times. But I'm not sure exactly how you would put physics inductive bias into this latent representation.
I think there's a fair amount of work actually trying to learn like this kind of predictive model in 3D. I think that can be considered as like the initial steps in learning dynamics, and with also this kind of 3D shape representation and also this kind of bias. I think I remember Katerina has like this kind of 3D dynamic scene representation work along that line. I think, although I guess probably like to directly answer your question, there is no like existing work that's able to do all these things together, but I think people definitely are looking at that direction. Yeah. And another work coming to my mind is like, for example, the ICCV is kind of like encoding this kind of bias of rigidities in rigid objects, and then try to learn a dynamic model on top of that. I think there is a line of work that's doing those kind of stuff.
Yeah.
So if we took, oh, sorry.
This is actually, yeah, this is the holy grail. That's what people are working on. I've seen some models like this on toy scenes, where the dynamics come as, in the latest, you take the video, you want to find different slots that correspond to different objects. You want to predict the next object, what's going to happen next. Potentially, you can put a graph there to model the interaction between the other objects. So people are thinking about this. But yeah, we haven't seen something that will have empirical excellent success, right, on benchmarks.
So to me, when it comes to intuitive physics or modeling physics in a scene, a very difficult thing is that, I mean, so sometimes the physics can be very simple. It could be some Newtonian physics, but when you have a piece of data like a video and deciding how that simple physics should apply to explaining that video, and that's actually very hard. So you need to take the data and figure out how to approximate it essentially, and to a level in which you can apply simple physical laws to explain how what you're looking at is evolving. And so that this process of abstraction, if you like, or simplification of the data is actually very hard to achieve, I guess. But there's another aspect of this that to me is actually quite interesting, which is to say, so we're learning object categories, or maybe even meta categories like all animals. And we do that in terms of their shapes and how the different shapes can be related to one another in terms of proportions or number of parts and correspondences, etc. But another thing would be also to understand how the different motions of these objects relate to one another, right? So what are the categories of motions? So, the way a cat and a dog, they move, they're different, but they're not completely different either. And I think building an understanding of categories of motions, if you like, that would also be very, very interesting and would help us maybe getting some abstraction of dynamics and physics that would generalize better.
Yeah, there's also the challenge that many physical parameters of importance to dynamics are not directly observable visually. They have to be inferred indirectly. And it's not the same as seeing shape and appearance, seeing the weight of the object or the inertia or the rigidity.
Which is where these trials will become even more important, right?
Yeah. Related to both of those, the thing I brought up earlier about uncertainty, I think actually is part of the reason that the physics is so hard. So if you don't have properly calibrated uncertainty in your interpretation of the visual input, then it's basically hopeless to have a forward model that doesn't accumulate so much error that it's useless, right? One of the reasons that model-based RL hasn't worked well is that the learned forward models that, they're good for one step, but they accumulate error catastrophically after a few steps. And so that what you need from the latent understanding, as Leo was saying, is like much stricter and requires much better calibrated uncertainty to be useful for forward prediction. I don't think anybody quite knows how to do that.
So I want to sort of make a comment here, which is that actually we don't need to have very long range prediction of the dynamics of objects, because you will think of how you use that kind of knowledge, right? You typically use it as part of some kind of feedback system. So I don't need to predict how that ball is going to move for the next 100 seconds, because I'm going to be interacting with it and I'm going to measure and I'm going to act. So I feel that long-range dynamics for physical objects, even though it has all these problems that physicists have told us about, chaos and all the rest of it. I think that may actually not be a real problem. I feel that predicting the dynamics of agents is, to me, the more interesting problem. And that is not just a problem of physics, but also a problem of goals. And but this is the one that I think we should focus on, because we also have tons of data, because we have lots and lots of videos of people performing actions. So for me, this is like a big chunk of the problem, which we sort of have to learn from data. That like if I'm running, how do I make predictions about the future? If I'm jumping, how do I make predictions about the future? So these are problems where there's a combination of physics and intentionality. And I think that, with Katerina, we worked on these things a long time ago, but I think of this problem as sort of a continuing problem where much, much more needs to be done.
Do you think that the prediction horizon is longer for people, or just they're more complicated to predict in the short window?
People are more complicated, yeah, and so it's a more complex problem. See, I mean, the Newtonian physics is actually simple, right? I mean, the challenge is because of certain parameters that we don't know. So we don't know about friction, we don't know about deformation, and so forth. But otherwise, the physicists would think of it as a solved problem. I mean, the same is true as mechanics and optics. I mean, in the case of vision, we worry about optics. Again, optics is a solved problem for physicists, right? The uncertainty is because certain parameters we don't know. Otherwise, the laws are all there from the 19th century or earlier.
Katerina.
Having said that,
so just to follow up on that point, I want to mention the following. Physics is not only about predicting the future. Look at my background. You can understand the shelf and all these objects support it, and you know that somebody is supporting this so it doesn't fall down, right? So, and this, by the way, I'm not sure you realize, but it's hanging. I'm pretty sure you realize it's hanging from that hook. Does our network do this interpretation right now? No, they just spit out some feature maps. We barely can segment some objects. We don't understand that there's a shelf and there are objects on top of it standing. So I think we interpret what physics is more convenient for us, because we don't know how to predict the scene in this type of modules with these type of relationships. We say, okay, let's predict the future instead, and so on and so forth, and condense the scene into one feature vector or maybe a few feature vectors. But physics, the real physics should be able to be there to interpret in the visual parsing, even of that static scene even, right? Because it's about the pairwise interactions of the visual entities. So this is what I wanted to add on the topic of physics.
I think it goes back to that comment about abstraction, like not just learning some parameters, but actually abstract information away from, something that is generalizable and of others that is not really generalizable.
Right,
Andrea,
right.
You wanted to say something also.
Right.
excuse me, sorry.
Did you want to say something? Sorry.
Oh, I think this is a very good point. So we also want to understand physics in a sort of static situation, just as an explainer of what's going on, I guess. The other thing was about, it's true that we cannot make very accurate physical predictions because there are just too many things we cannot observe with sufficient accuracy. And that goes without saying, I guess, but that's similar to many tasks we have in vision, for example, I don't know, colorization or in painting, or, I mean, there's a huge amount of uncertainty because we don't observe a large chunk of information, we observe only the context, and then we have to guess what's missing. And the answer to that is, of course, that we can predict the distribution of possible solutions, right? So likewise in physics, if the goal is to predict what would be the trajectory of a human moving in a scene, for example, we cannot do that exactly, but we can generate or predict a motion which is plausible. Now, this may not be necessary for semantics or understanding at that level, but may be very important for certain applications, for example, computer graphics. If I want to extrapolate motion of people in a crowd, or not even in a crowd, in just short videos of my family, because I want to have a 3D reconstruction of it, how am I going to do that if I cannot generate plausible motions of the people in the scene, right? So there are many applications where these capabilities would be useful, even if they are not necessarily representative of the fundamental task of vision, which is analysis. I mean, the synthesis problem is also important.
Yeah, I want to add a little bit about the uncertainty part. I feel, yes, I feel if we want to predict futures, there is natural uncertainty, and it's going to be helpful to avoid uncertainty. But also, I think if we consider like active agents, and if we consider actions, then we can actually perform actions to reduce those uncertainty. That's why like we are so good at like, not so good, but like we're kind of better on predicting the future. It's because we actually actively seeking information that can help us to reduce uncertainty, especially for the things that we care about, right? So I think if we're just thinking about this like a passively observing a video and we're trying to predict the future, then of course like there's a huge amount of uncertainty. But if it's an agent that's actually in this environment and they can actively acquire information about the physics or anything that's useful, they can actually reduce those uncertainties.
I think a lot of the prediction game has been misguided. I mean, because a lot of it has been focused on sort of doing prediction at the pixel level, and it's hard and basically useless, I think. I think that people focus on it because it's very easy to formulate, but it's basically, to me, a slightly silly exercise. I think that I think it is better to put in some more inductive bias that the world contains objects and so on and so forth, and then focus it from the perspective of what do you need the prediction for. So if I am a robot and I need to move and I need to avoid colliding with other objects, okay, I need to have some prediction of how other people are walking. If I'm a robot, I need to catch a ball. I need to have a prediction of this ball for how to catch it. Once you set it up in those settings, these problems are not so hard. I think we are trying to do it in the sense of evolution of the pixel space over many seconds, and this is hard, but it is an artificial problem. I really think it's only justified because machine learning people want to set up a problem where they're not putting in some kinds of bias like the world contains objects. I'm a vision person or a robotics person, and I believe that the world contains objects.
Okay, great. Any other follow-up comments on this?
If you are a graphics person, you may care about the pixel values.
I care about the pixels, but as consequences of the objects, right? But I want to use the latent variable of the objects for the pixels. Yeah.
Yeah, it all depends on how you want to interrogate the future.
Okay, so I want to leave some space for questions from the audience, perhaps too, and or already started. He was wondering what people think, what roles simulators will play in, well, helping us learn priors. So, and maybe let me generalize this question. You know, we have actually quite a bit of data. We have good models, but somehow there doesn't seem to be enough data or not enough inductive bias to really learn sufficient priors. Do we need better simulators to generate more data where we know the ground truth? Do we need to have models that can work better with data that we capture in the wild, or do we just need better data that works with better models that work with less data? What do we need, or do we need some kind of a mix of all of these? So that's maybe generalizing Orth's question.
I mean, I can take it if you like.
Sure.
I think simulator, I've worked on a couple of simulators. I think simulator technology is getting better all the time. Okay, so I feel that you know, as t goes to infinity, our problems will become much better. Because 10 years ago I would have said, oh, simulators, you can't do real vision with simulators, okay, because you'll get some garbage and it'll probably misguide you. And this is not true now. I think simulators gives us the ability to solve problems where there's control laws and feedback and active perception and so forth, which we could never do in in a static data set. I think we just have to know what we can simulate well and what we can't. So the sim to real transition for problems such as in navigation has been quite easy. I mean, this is something where we worked on, and we could develop the strategy in simulation in Gibson. We put it on a robot in Berkeley and it just worked. Okay, I think manipulation will not be so easy because the fidelity that you need for modeling contact and deformation. I mean, some of the cool works that people have done on learning grasping have to do with the fact that the packet of potato chips deforms when you hold it. Okay, good luck getting that in your simulator at a reasonable pace, right? I mean, you can do it, but your speed of your simulator will be so low that it won't be useful for training an agent. So I think the physics of contact is tricky. Physics of moving in free space is much easier. And so we just have to know where to use to use the simulation in a judicious way. But I think it's very much part of the picture, and it is going to keep increasing.
Okay, great. Srinath, you had a question and a comment that you wanted to add.
Oh, thanks, Gordon. Yeah, I just wanted to follow up on Noah's thoughts earlier on what is a good 3D representation for grounding language. He started giving us some clues towards that. I'm curious to hear more of that. And also generally thoughts from the other panelists on this topic.
I guess from my point of view, I can start in, but really just to amplify that as a good question for everybody else. Like, I think if you look at language, the language we use to describe physical scenes, or let's just restrict to objects, it's interesting because it's not all nouns. A great deal of it is modifiers, so adjectives and kind of ways to operate. And it's not all intersective adjectives. It's the kinds of adjectives where when you apply it to one noun, it conveys something different than when you apply it to a different noun. So I think thinking about these higher order, the denotations of some of these slightly higher order things and what those would correspond to in terms of features, 3D features is quite important and interesting. I think it's also worth flagging that different languages will cut up the same perceptual space quite differently. So in color, there are languages that only have 3 color distinctions and some that have 30, and exactly, how you cut it up, whether you have light blue, dark blue, like in Russian, or just one blue, is a pretty language dependent. So you, in some sense, will need features that can support the different ways that they're cut up, or prepositions, where maybe is even more relevant, right? If you have 2 objects, their relation to each other is described very differently in different languages. So, in and on are very different in English, but there are other languages that group those together. So I think thinking about kind of the spaces and the flexibility for cutting them up differently with different languages is a factor. But yeah, I don't know, what do you all 3D people think about what features could be there to support this?
I actually have a follow-up question about this question. So, okay, so the question is about what is a good 3D representation for grounding language. But my question is that whether it is really necessary to ground language with 3D representations. So I think when we say grounding, we kind of assuming that there's like a significant overlap. Yes, there is overlap on the information, but maybe they're also kind of describing very different things, right? So I think language actually describe a lot of things that do not directly captured in geometry, like and vice versa. So, and also, yeah, for example, a lot of 3D geometry information, we don't typically describe them in language because it's kind of trivial or this and that. So is that really necessary to kind of like build this grounding? Like why it's necessary? I think that's my question.
Sorry, do you mean, is it necessary for language to ground into 3D as opposed to 2D, or do you mean? Well,
let's just think about the example that you give in your talk is like grounding the language with like the CAD models of objects with their textures, right? So is that, I guess, of course there's necessarily like it's useful because there mutual information, but should we like think bigger that instead of just trying to match the mutual informations, should we focus more on like what's their difference, like the language describing things that the geometry do not provide?
That's fair. I do think that there are a lot of differences, like, vision. Geometry is kind of interesting because there's a lot of bits of geometry that are very, very hard to talk about. At the same time, there's kind of a rationale that says like, look, if it's important to people, we'll probably have a way of talking about it. And so you can kind of mine language for the big cuts in some sense of like, so maybe that's the rationale, but I kind of agree. There's an open question about how much coverage there is between the two.
Yeah. Do you think it's possible or useful to kind of explicitly model which part should be grounded, which part shouldn't? I guess that's another question. That's a great question. I'm not sure. I guess you could imagine a usage-based thing or something like Leo said, where like, the high order bits, the quantized bits maybe are the ones you expect to see in language. I don't know, do others have opinions?
I have one opinion because we have worked on grounding language in 3D, and it's definitely not about grounding what you see. For example, look at me now. I'm going to tell you that I balanced my cell phone on the top of my computer screen. Okay, so now you imagine the computer screen is thin. It's hard to balance your cell phone there. Do you do that? Or maybe I balance my cell phone on top of the open screen of my laptop. Okay, so that's what we mean by grounding. We mean that I talk to you and you reference representations that have perceptual, geometrical, and physical properties, and that you are able to simulate what I'm talking to you and figure out that how did he manage to do that? How did he put the cell phone there? How did he manage to get it to be there? That's what we mean by grounding. We don't mean like, okay, the black cell phone, the silver laptop and so on. Do you see? It means that I talk to you and you can understand what I'm talking about without you seeing actually. And to do that, going back to the question of the initial question, I do believe that the presentations are very similar to what Gordon mentioned and we've been discussing. They need physics, they need geometry, they need all these nice properties to be able to actually simulate the situation that language describes and draw the conclusions that it is hard, it's possible, or this is how it was done and so on.
It really does bring us back to the earlier conversation though, right? Like, I just for the sake of kind of concrete thing, and imagine that you did, you had natural language descriptions like the one Katerina just gave, and then you had, these like, I don't know, nerf functions or something paired, and you were like, oh my God, how am I going to generate a function from that natural language description? That seems like super hard and ridiculous. I mean, maybe somebody already did that yesterday, but the high level features that are the things you actually want the language to tell you are there somewhere.
But is that related to abstraction, being able to abstract from language, from visual appearance, from some physical PDE that describes a physical model? Or I haven't thought about it too much, but.
Yeah, that's kind of what I meant. I think it's that conversation you raised earlier about abstraction and priors. And
yeah, fantastic. So we're kind of running out of time, even though there's one more question here on the chat, which is directed to something Leo was saying earlier, in that he mentioned that there are discrete representations which are consistent across networks. And the question is then, would this necessitate a universal frozen decoder across vision tasks? I don't know, Leo, if you have any thoughts on this specific question from Alex in the chat. Alex, feel free to unmute yourself also.
I'm going to be short because I'm going to have to sign off, unfortunately. Sure. But I mean, there are ways to, I mean, you don't need an identical frozen decoder. You need decoder translators, essentially something that can map the decoder for A into something equivalent for a decoder for B. I think the challenge here is that related objects or object classes have shared structure, but it's not completely shared. So you need to understand what you can transfer and what you cannot. And we don't have a good representation for this because essentially our latent representations as vectors of scalars make everything the same we don't know which dimensions could be shareable or combinations of dimensions and which might not. And so kind of my sense is that we need more sophisticated latent spaces to be able to capture this aspect that there is partial commonality and partial difference. And guys, I'm sorry, I'm going to have to sign off.
Oh, that's fine. Thanks for joining us.
Contributions, and especially the speakers and the poster contributors.
Okay. Yeah, I think we're running short on time, but I think what Leo just said also relates to this idea of abstraction. And maybe even what Jitendra was saying earlier, that we don't need to model everything at the pixel level to really understand what's going on, but rather figure out a meaningful representation that abstracts that away. Could be a good challenge. So yeah, thanks again for joining everybody. And I'll maybe hand it over to one of the main organizers to say a few last words before we're closing this workshop. Srinath, do you want to take over or somebody else?
I'll take over. Thanks,
Okay,
Gordon.
Thanks.
Thanks for hosting the panel. It was I love the discussions, beautiful ideas, very thought-provoking. We're at the top of the hour and we're finishing our workshop. Good attendance, great talks. I want to wrap up by first thanking my fellow organizers, Professor Sanja Fidler, Leo Guibas, Tanner Schmid, Vincent Zitzman, Srinath Sridhar, Shubham Tulsiani, and Gordon. And I want to thank our invited speakers throughout the day. We heard amazing talks from Katerina, Noah, Yaron, Jitendra, Dima, Shuran, and Andrea. I want to thank our posters, presenters. We had amazing 20 presenters who also participated in the breakout sessions, and we had some great discussions there. On top of that, I want to just say that we'll put the recordings of the workshop online. So anyone who missed it or wants to go back to any of the talks is welcome to do that. And the posters will remain on the Gather Town link. If anyone wants to watch those, feel free to do so. We'd love to get feedback. If you guys, we are planning to do a third workshop at some point. So if you guys have any important feedback on stuff that worked better or worse, please write to any of the organizers. We'd be happy to get those. And with that, thank you guys again for joining us today, and have a great rest of your day. Bye-bye.
Thank you. Bye.
Thank you.
Thanks, everyone.
Thanks, everyone.
Bye-bye.